In this lesson, we want to talk about inverse trigonometric functions. All right, so before we get into the inverse trigonometric functions, I want to recap some things that we talked about earlier in the course. It's going to be really important that you understand this information in order to fully understand this lesson. So first and foremost, we discussed the idea of a one-to-one function. So in a one-to-one function, each x value corresponds to exactly one y value. And additionally, you could say in a one-to-one function, each y value corresponds to exactly one x value. So often you'll hear for each x there's one y, and then for each y there's one x. Now, when you have a one-to-one function, you can verify that using something called the horizontal line test. So for the horizontal line test, if you have the graph of a one-to-one function, no horizontal line will impact that graph in more than one location. So a common source of confusion when you work with inverses would be the notation that's involved. So I have here, if a function f is a one-to-one function, then the inverse of f is denoted as, here this is f inverse. So again, this is the inverse of my function f. Now, this right here is what you have to get straight. This is not an exponent of -1. That is a very common source of confusion. Later on in this lesson, when we get to inverse trigonometric functions, you'll see something like y is equal to the inverse sine of x, and that's one way to write it. We have a different way to write it, and I'll get to that later on. But you need to know that this is not an exponent of -1. This is telling me I have the inverse sine of x. Now, provided that your function, let's just call it f of x, is a one-to-one function, you're going to be able to find the inverse using this little procedure. So to find the f inverse of x from f of x, again, f of x is a one-to-one function here, we're going to replace f of x with y. We're going to swap x and y. Then you're going to solve for y. And then once you've done that, you're going to replace y with f inverse of x. So this right here, this swapping x and y, this leads to the following. So we have that the domain of f, so the domain, remember, as the set of allowable x values, will become the range of f inverse. So the range is the set of allowable y values. So again, the x's and the y's were switching places. So that's what's causing this. The domain of f, or the x values, will become the range of f inverse, or the y values. So the x's and the y's are switching places. Similarly, the range of f will become the domain of f inverse. Again, the x's and the y's are switching places. So this tells us if a comma b is on the graph of f, then b comma a is on the graph of f inverse. So notice that these guys switched roles. So here, this is your x, and then here it becomes your y. And then here, this is your y, and then here it becomes your x. So again, the domain of f becomes the range for f inverse, and the range of f becomes the domain for f inverse. So your x's become the y's, and the y's become the x's. Very important. And then I have here the graphs of f and f inverse are reflections across the line y equals x. So there are many cases where we're going to have a function that's not a one-to-one function, but we still want to find the inverse. So in that situation, what can we do? Well, let's start off with something that we did earlier in the course. We looked at the squaring function. So this graph right here is for f of x is equal to x squared. So clearly this is not a one-to-one function. Let's just use the horizontal line test real quick to prove that. So this would be the line y is equal to 4. Now, if you look at this horizontal line, it is impacting this graph of f of x equals x squared in two locations. So right here and then right here. So again, if you have the graph of a one-to-one function, no horizontal line will impact that graph in more than one location. So this right here will not be a one-to-one function. If you look at this point right here, from the origin, we're going 2 units to the left and 4 units up. So this is -2, 4. If I look at this point right here, from the origin, I'm going 2 units to the right and 4 units up. So this is going to be 2, 4. So the issue is that this y value of 4 is associated with two different x values. Here with -2 and here with +2. And that's coming from that squaring operation. If I plug in a 2 for x, 2 squared is 4. If I plug in a -2 for x, -2 squared is also 4. So when this happens, what can we do? Well, like we saw earlier in the course, we can impose a little domain restriction. So for this graph right here, we start with f of x equals x squared. So that's the squaring function. But you would notice that it seems like I've cut off anything to the left of 0. So basically, we would say that x here is greater than or equal to 0. So this is going to create a one-to-one function, and this is the key. The range is going to be the same. So we're going to see that's going to be important as we get into these trigonometric functions and the inverse trigonometric functions that we create from restricting the domain. So the range here is the same. Before it was from 0 to positive infinity, and now it's still from 0 to positive infinity. Now let's just prove that real quick. I'll just put in this same horizontal line here. So again, this is y is equal to 4. And notice that now, when I draw this line, it's going to impact the graph only in one location. And that's true for any horizontal line that you would draw here. So this is now the point 2, 4. My point, negative 2, 4, that was on the other one, where I didn't restrict the domain, that's gone because x can't be negative 2 here. X can only be 0 or anything larger. So I only get 2, 4. So basically, in the inverse, I'm going to have 4, 2. Right, so 2, 4, and then 4, 2. So for each x, there's one y, and now for each y, there's going to be one x. So I'll be able to find an inverse. Okay, so let's just go through that real quick. Hopefully you know how to do this from earlier in the course. If not, let's just go through it once so that later on it'll be easy. So basically, you start off by replacing f of x with y. So let me write here that we're going to find the inverse. And you would start by replacing, again, f of x with y. So y equals x squared. Then the next step is to swap x and y. So we're going to say that we have x is equal to y squared. So this y became x, this x became y. That's all you're doing. Then your next step, you're going to basically solve for y. So first I would write this as y squared equals x. As my personal preference goes, I like what I'm solving for to be on the left. And then I would use the square root property. So you would say that y is equal to plus or minus the square root of x. So here's where we have to pause and think. In this function right here that's domain restricted, f of x equals x squared, we said that x is greater than or equal to 0. Well, we know that the domain from this function right here becomes the range for the inverse. So specifically here, I would say that y is greater than or equal to 0. So I don't need this plus or minus here because I can't have the negative of the square root of x because I'm specifically saying that y is greater than or equal to 0. So I'm going to get rid of this plus or minus and say that y is going to be the principal square root of x. So let me replace this with y is equal to the principal square root of x, and I'll get rid of this. And then step 4 is just to replace your y with your f inverse of x. And so this is equal to the square root of x. All right, so before we move on, it might be helpful to look at this graphically. This is especially useful when you're trying to figure out if you got the right inverse. Remember that a function and its inverse are going to be reflections across the line y equals x. So you can always look at this graphically and see that. So this graph right here, for this guy in orange, this is our f of x equals x squared, where we said that x is greater than or equal to 0. If you're going to do this on Desmos, you want to do this as f of x equals x squared, and then you're going to open up some brackets and you're going to put in your restriction. So x is greater than or equal to 0, and then just close those and it'll give you this graph here in orange. Okay, then the graph in red, this is just the line y is equal to x, or you could put f of x equals x, whatever you want to do. And the graph in blue, this is our inverse. So f inverse of x is the square root of x. I'm just going to put this as g of x. So f of x and g of x, those are going to be inverses. And this is equal to just the square root of x. Now, what you can do is look at a few points and just prove a few things. So first off, let's just start with this point right here. So this point right here, I'm going 3 units to the right and 9 units up from the origin. So this is going to be the point. Let me arrow to this. So this would be 3, 9. Now again, if I reflect this across the line, y equals x, I'm going to get this point right here. So this point right here would be 9, 3. So notice that the x value, which was 3, is going to become the y value here. And the y value here, which is 9, is going to become the x value here. So the x's and the y's are switched. Then let's just do one more. So this point right here, if you look at it, is going to be 2, 4. So this point right here is 2, 4. And then if you look at, again, reflecting across the line y equals x, you're going to get this point right here. And now, instead of 2, 4, you're going to get 4, 2. So this is always something you can use if you're trying to figure out if you got the right inverse. It's very helpful to graph your function, graph your inverse, and graph the line y equals x. And just look at if your function and the inverse are reflections across the line y equals x, then you know you got the right one. All right, now let's move on and talk about how to find the inverse trigonometric functions. We're going to start off with how to find the inverse sine function. And so to do that, we're going to begin with our graph of f of x equals the sine of x, or we could say y is equal to the sine of x. So we studied this graph earlier in the course. At this point, you should know that the domain is a set of real numbers and the range is from -1 to +1. So let me write this out. So the domain is going to be the set of real numbers. So from -infinity to +infinity. So that means I can plug in any real number I want for x here. So a negative, 0, positive. As long as it's a real number, I'm good to go. Then in terms of the range, we can see that's from -1 to +1. And you should know that from the unit circle. So let's go ahead and put from -1 to +1. Clearly, this guy is not the graph of a one-to-one function. If I draw a little horizontal line like this, well, you can see that I'm going to hit here and here and here and here and here and here and here. And remember, this continues forever to the right and forever to the left. So I'm going to keep hitting over and over and over again. So obviously, this is not the graph of a one-to-one function. It fails the horizontal line test. So what can we do when we encounter this situation? Again, just like with the squaring function, we restricted the domain such that we had the same range. So let me actually erase this and show you what we're going to do. We're going to take a piece of this graph. So we're going to go from right here, this is -pi/2, to right here, this is pi/2. Let me write that a little bit more neatly. So again, this is -pi/2 here. So you're going to take right here to right here. So just a piece of that graph right there. And now it's going to pass the horizontal line test. So it'll be a one-to-one function. It'll have the same range from -1 to +1. So let me come to this graph here. It's a little bit easier to see things. So this is called the restricted sine function. So basically it's your sine function with a restricted domain. So we have y is equal to your sine of x. And then we would say that x is greater than or equal to -pi/2. And then less than or equal to pi/2. So obviously the domain is from -pi/2 to pi/2 with those guys included. Let me just write this out. So the domain is going to be from -pi/2 to pi/2 with both of those guys being included. And this is the key here. The range is the same. So if you go back to the y equals sine of x, again, the range is from -1 to +1. Well, here, even though we've restricted the domain, the range remains from -1 to +1. So let me write that the range is going to still be from -1 to +1. Okay, so now let's cover the inverse sine function. So we're going to start with the restricted sine function. So that's going to be this graph in orange. Let me just trace over what the computer drew here. So this is my graph in orange. A lot of stuff is overlapping here, so it's pretty hard to see it clearly. But this graph, again, is y is equal to my sine of x, where x is greater than or equal to -pi/2 and less than or equal to pi/2. So that's the restricted sine function. If you reflect it across the line, y equals x, you're going to generate this graph here in green. So let me go over that. So from here to here. So a lot of overlap here. You can do this on Desmos if you want a cleaner picture. But in terms of the video, I think it's going to come through at least good enough to where you can see what's going on. So this right here is going to be the graph of the inverse sine function. Typically, you'd write that as y is equal to the inverse sine of x, like that. You could also write this as y is equal to the arc sine of x. Although if you're in a trigonometry course, this is typically more common, but some books use this. It just depends. So you need to know both of those in case you run into one and not the other. Okay, so basically, like we saw earlier, you're just taking this point right here, which is from the restricted sine function, and you're reflecting it across the line, y equals x, to get this point right here on your inverse sine function. So notice that this x value of pi/2 becomes the y value of pi/2 here in the inverse, and the y value of 1 becomes the x value of 1 in the inverse. We can also take this point right here, and again, reflect it across the line y equals x to get this point right here. So you see this x value of -pi/2 becomes the y value of -pi/2, and then the y value of -1 becomes the x value of -1. Okay, so let's look at a cleaner graph here. So this is the graph of y is equal to your inverse sine of x. And you can see that the domain of this guy came from the range of your restricted sign function. Let me actually put a little border here, and let me write y is equal to the sine of x. And let me put that x is greater than or equal to negative pi over 2 and less than or equal to pi over 2. And let's consider that the domain of this guy, so the domain of this guy, is the same as the range from this guy. So the domain here is from -1 to +1. So this is going to be from -1 to +1. Well, here, if you look at the range, it's from -1 to +1. Then if we think about the range for this guy, so the range, this is coming from the domain of the restricted sign function. So it's going to be from negative pi over 2 to pi over 2. So from negative pi over 2 to pi over 2. And then the domain here, of course we know this at this point, but let's just write it one more time. So again, this is from negative pi over 2 to pi over 2. So just like we talked about, the domain from the restricted sign function becomes the range in the inverse. And then the range in the restricted sign function becomes the domain and the inverse. So the x's become the y's and the y's become the x's. All right, now let's look at a few sample problems. So we're going to start with y equals the inverse sine of 1/2. So we just want to figure out what is the value for y here. So if you were to key this into your calculator, so if you were to type in the inverse sine of 1/2, you would get pi over 6 if you're working with radians, or you would get 30 degrees if you had it set to degree mode. So why does it give you that answer? So why does it give you pi over 6 and not the 5 pi over 6 that you would see on the unit circle? So we can see that for pi over 6, I have a sine value of 1/2, but then also for 5 pi over 6, I have a sine value of 1/2 as well. Well, what's going on? Well, to see this, let's think about deriving the inverse algebraically. We saw a graphical representation of it, but now let's do it algebraically, and we'll get a little bit more insight into what's going on. So let's say you start with, again, y equals the sine of x. And of course, we need to make this 1-to-1 so we can have an inverse. So x is greater than or equal to negative pi over 2 and less than or equal to pi over 2. So to find the inverse, if you had f of x, you change it to y. Well, that's already done for us here. And then basically you'd swap x and y. So this y becomes x and is equal to the sine of this x becomes y. Okay, well now this domain is going to become the range. So this is y is greater than or equal to negative pi over 2 and less than or equal to pi over 2. Now this is a form that you're going to see in your textbook. What they'll say is from here, in order to solve it for y, we're just going to say that it's y is equal to the inverse sine of x. So this right here is just solved for y. It means the same thing as this. Now I'm going to concentrate on it in this form for right now. It's a little bit easier to think about it. So basically, let's say that we start with this right here. So the domain restricted sign function. We know that a point on that graph is going to be pi over 6, comma, 1/2. So where did I get that from? Well, first off, pi over 6 is within the domain. It's greater than or equal to negative pi over 2 and less than or equal to pi over 2. So if I plug that in for x, I get a true statement. So it's within the domain. And the sine of pi over 6 is 1/2. So this would be a point on the graph. Well, when I get to the inverse, these are switched. So now this is 1/2, comma, pi over 6. In other words, when I look at this guy, I am asking the question, let's say I plugged in a 1/2 here for x. I'm saying, what angle in the interval from negative pi over 2 to pi over 2 is going to have a sine value of 1/2? If we go to the unit circle, I'm going to look at this right here. So this is what I'm looking for right here. So this is pi over 2. And then this down here, if you're rotating clockwise, this is going to be negative pi over 2. So this is what you're looking for here. If your argument is positive, like we have here, we're going to be looking at things in quadrant 1. If your argument is negative, you're going to be looking at things in quadrant 4. Now, there's an exception to what I just said. If you have the inverse sine, so if you have the inverse sine of 1, that's going to give you pi over 2. And of course, that's a quadrantal angle. If you had something like the inverse sine of 0, that's going to give you 0. So 0 is not a positive number, but if you plug that in, you're going to get something that's a quadrantal angle. And then also the inverse sine of, let's say, negative 1, that's going to be negative pi over 2, and that's coterminal with 3 pi over 2. So again, these are quadrantal angles, but if I say something like the inverse sine function is going to give you something in quadrant 1 if the argument is positive, and quadrant 4 if the argument is negative, you need to just know these exceptions. Let me get rid of this real quick, and let's go back to what we were talking about. So here we have the inverse sine, so y equals the inverse sine of 1/2, or we wrote this as x is equal to the sine of y, where specifically y is greater than or equal to negative pi over 2 and less than or equal to pi over 2. So again, where in this interval am I going to have a sign value of 1/2? Well, again, this argument is positive, so I'm only going to look in the first quadrant, and I see that I have a sign value here of 1/2, and that is going to be right here at pi over 6. So that's why I'm getting this pi over 6, and I'm not getting this 5 pi over 6 here as an answer. If you notice, you have a sign value of 1/2 for 5 pi over 6. And a lot of students will always complain, well, why am I not getting the 5 pi over 6? You're not getting it because it's not within the range of the inverse sine function. So to answer this, if you have y equals the inverse sine of 1/2, let's just write the inverse sine of 1/2 is going to be equal to pi over 6. All right, let's look at y equals the inverse sine of a negative square root of 2 over 2. So this one's a little bit more tricky. Let's come down to the unit circle. Let me write y is equal to the inverse sine of negative square root of 2 over 2. Again, you can stick with it in this form if you want. You're just looking in quadrant 4 for an angle whose sine value is going to be negative square root of 2 over 2. That's what you're looking for. You can again write it as the sine of y is equal to x, where y is greater than or equal to negative pi over 2 and less than or equal to pi over 2. And of course, you could just plug in a negative square root of 2 over 2. So again, y is the angle in this interval where we have a sine value of negative square root of 2 over 2. Now, because this is negative, I want to work in quadrant 4. Let me just highlight the whole thing first. Let me highlight the whole thing first so we get comfortable with this. And basically, if I go into quadrant 4 and I'm looking for a sine value of negative square root of 2 over 2, it's going to be right there. So this is going to be at 7 pi over 4. Now, is 7 pi over 4 the answer? No. You cannot say that the inverse sine of the negative of the square root of 2 over 2 is equal to 7 pi over 4. That is incorrect because it's not in this interval. What you have to do is actually rotate clockwise here. Let me pick a good color here that's going to show up. So this right here, you need a clockwise rotation. So the reference angle there is pi over 4. So this rotation clockwise, this angle is going to be negative pi over 4. So this would be negative pi over 4 as the answer. Now, another way you can do this is a longer way, but essentially what you could do is you could figure out, okay, I'm going to be in quadrant 4, so I want this 7 pi over 4 answer, but I need to put it into this interval. Since I started here and rotated all the way around by 7 pi over 4, what I have to do is now rotate clockwise by 2 pi. So that's going to be me taking 7 pi over 4 and subtracting away 8 pi over 4 to get my negative pi over 4. So in other words, you're going to go this way, clockwise, by 2 pi. So that's just subtracting 2 pi away. So coming back here and finding a coterminal angle, so ending up right there. So now I'd get the angle that I want, which is going to be negative pi over 4. I think this is a little bit more complicated, but sometimes people need to do that to figure out what's going on. What I always do is figure out what the angle is. So in this case, okay, it's 7 pi over 4. The reference angle is pi over 4, and I know it's negative, so it's just negative pi over 4. I think that's pretty easy to understand. All right, now let's talk about the cancellation properties for sine. So these are some simple rules you can use to quickly evaluate things. So the first one's very straightforward. So you have something like the sine of the inverse sine of x. That's going to be equal to x for x is greater than or equal to negative 1 and less than or equal to positive 1. So why do we need this restriction here? So first off, if you consider the outer part here, so the sine of, so this right here is the argument for the sine function. Does it matter what I plug in for the sine function in terms of the domain? No, because it's all real numbers. So I can plug in whatever I want. A negative, 0, positive, whatever I want. The problem actually comes from the inverse sine function. So here, if I look at this x here, what can I plug in for that? Well, remember the domain of the inverse sine function is going to be from negative 1 to positive 1. So that's where you have to be careful. If you did something like the sine of the inverse sine of 2, well, you're not going to be able to get an answer there because the inverse sine of 2, you can't type that into your calculator and get an answer. It's just going to give you an error. So what you would want to do is make sure that it's within this interval here. And then if you had a problem like the sine of, let's say, the inverse sine, and then for this, let's say we go with what we just did. So let's say we plug in 1/2. Well, this is going to just give me 1/2. In other words, these guys are just going to cancel away, and I'll be left with this 1/2. If you want to do this the long way, the inverse sine of 1/2, we just saw that was pi over 6. So this would be the sine of pi over 6, which we know is 1/2. So I can just skip this step right here and just go straight to saying that the answer is 1/2. All right, so the next one is a little bit more challenging to understand. So what you want to concentrate on is the first part, so the sine of x. So think about that for a moment. We know that, again, the domain for the sine function, this is not a restricted sine function or anything like that. I can plug in whatever I want for x. It does not matter, any real number. So plug in whatever you want. The result of the sine of x is going to be from -1 to +1. Now, with the inverse sine function, remember, the domain, or what you can plug in, is going to be from -1 to +1. So I'm good to go in terms of plugging things in for the inverse sine function. I'm not going to run into any issues. But the problem is that the range, or the output for the inverse sine function, is only going to be from -π/2 to π/2. So if you're in that interval, you can just cancel this with this and say it's equal to x. If you're not, you need to evaluate the sine of x first and then take the inverse sine. So let's look at two examples. So the first one is, we have the inverse sine of the sine of -π/3. So to answer this, the first thing you would do is say, is -π/3 greater than or equal to -π/2 and less than or equal to π/2? Well, this part I know. I know that -π/3 is certainly less than π/2 because a negative is always less than a positive. Now, what if you compared this one? Well, the numerators are the same. Forget about the fact that they're negative for a moment. Let's say you had π/2 and π/3, and I just put a question mark here. So if I look at this, the numerators are the same, the denominators are different. So same numerator, that means that the larger denominator is going to belong to the smaller fraction. So I can say that this guy right here is greater than this guy right here. But now, if I multiply both sides by -1, that's going to change. So this right here, and this gets flipped. So now this guy, which was the larger fraction, because now that it's negative, it's going to actually be the smaller fraction because it's further to the left on the number line. So that means that -π/2 is less than -π/3. So this inequality is going to be true. So that means that I can just say that the answer here, let me slide this out of the way, is just going to be -π/3. If you go to the unit circle and you wanted to find the sine of -π/3, again, I'm just looking for an angle in quadrant 4 with a π/3 reference angle. So that's going to be right here at 5π/3. But again, I'm not thinking about it as 5π/3 because I'm rotating clockwise. So that's my -π/3 angle. So the sine of -π/3 is the same as the sine of 5π/3, the coterminal angle. So that's going to be the negative of the square root of 3/2. So if you went through and said, well, what is the inverse sine? So what is the inverse sine of the negative of the square root of 3/2? You're going to go right back to that -π/3. So again, if you're in this interval, you can just shortcut all that and just give this as the answer right away. So the answer here is just -π/3. All right, let's look at another one. So this one will give us a little bit of trouble. So we have the inverse sine of the sine of 5π/6. So can we just say the answer is 5π/6? No. And the reason for that is 5π/6 is not in the range of the inverse sine function. We cannot get that as an answer. So because of that, again, what you'd have to do is first find the sine of 5π/6. So coming to the unit circle, here's your 5π/6, and all of you know that that's 1/2. So basically you would have to transform this into the inverse sine of sine of 5π/6 is 1/2, and then we know that this is π/6, but again, if we just come back down, you're working here, and this guy is going to be positive, so you're looking in quadrant 1 for an angle with a sine value of 1/2. So you've got that right here, and that's going to be at π/6. So that's the angle I'm looking for. So coming back, we just answer π/6. So when this guy right here is not in the range, so from -π/2 to π/2 of your inverse sine function, you've got to do additional work. First, you're going to do the inside, so evaluate the sine of 5π/6. That gives me 1/2. Then take your inverse sine of 1/2, and that's going to give me π/6. All right, now let's move on and talk about finding the inverse cosine function. So the process is exactly the same as what we did for finding the inverse sine function. There's just a few differences in terms of what part of the graph we're going to take in order to create a one-to-one function. So we would start with the graph of y is equal to the cosine of x. So we've studied this graph before. We know that the domain is all real numbers, and the range is from -1 to +1. So let me write here that the domain is going to be the set of real numbers. So from negative infinity to positive infinity. So I can plug in whatever I want for x there. So a negative, 0, a positive, whatever I want as long as it's a real number. And then for the range, we can see that this is from -1 to +1 with both of those being included. Now again, this function is not a one-to-one function. You can see that from the graph. If I make myself a little horizontal line here, you're going to see that it hits here, and then here, and then here, and then here. And again, this graph continues forever to the right and forever to the left, so it's going to keep hitting over and over and over again. So obviously, this is not the graph of a one-to-one function. So again, what do? Well, we're going to restrict the domain such that we have the same range. So for this one, what we want to actually do is start at 0, so an x value of 0, and then go to an x value of pi. So this is the piece of the graph we want. So this is going to be from 0 to pi. And notice that your range is not going to change. It's still going to be from -1 to +1. So this would create a one-to-one function for us. And to see that more clearly, this is the graph of our restricted cosine function. So this is y is equal to the cosine of x, where x is greater than or equal to 0 and less than or equal to pi. So you can see this would be a one-to-one function now. And let me just write here for clarity that the domain, obviously it's right here, but let's just list it. So this is going to be from 0 to pi, where 0 and pi are both included. And then the range, this is the key here, it's going to be the same as your regular y equals the cosine of x. So it's still going to be from -1 to +1 with both of those guys being included. Now what we can do if we want to find our inverse is reflect this graph across the line y equals x. So if we start with this graph again in purple, this is the graph from the previous page. This is my y is equal to the cosine of x, where x is greater than or equal to 0 and less than or equal to pi. So again, the restricted cosine function, let me just go over this for clarity. So this graph right here, again, you're going from 0 to pi, and the range, and this is the key, is still from -1 to +1. So when you reflect this across the line, y equals x, that's this guy in orange here, you're going to get this graph that's in teal. So this guy right here is the graph for y equals the inverse cosine of x. So if you started with something like, let's say this point right here, which is 0, 1, and you reflect across the line y equals x, you're going to get to this point right here, which is 1, 0, and that's going to be on your inverse. So the x value of 0 becomes a y value of 0, and then a y value of 1 becomes an x value of 1. So those x's and y's are switched. Then if we look at this other point right here, which is pi, -1, again, if I reflect it across the line y equals x, I'm going to get this point right here, which is -1, pi. So here, the x value of pi becomes the y value of pi in the inverse, and then the y value of -1 becomes the x value of -1 in the inverse. To get a better look at this, we can see this graph on its own. So this is for y is equal to your inverse cosine of x. And let me put a little border, just like we did last time. Let me put the y is equal to the cosine of x, where x is greater than or equal to 0 and less than or equal to pi. And again, for this one, we know that the domain, because it's listed specifically right here, is going to be from 0 to pi. Well, notice that the range here for the inverse cosine function is going to be from 0 to pi. So let me write that the range for this one is going to be from 0 to pi. So the domain becomes the range, and the range is going to become the domain. So the range here, so the range in this case is going to be from -1 to +1, and you're going to see in the inverse, again, the domain now is from -1 to +1. So let me put that the domain is from -1 to +1. All right, let's look at a few problems now. So here we have y equals the inverse cosine of the negative of the square root of 3 over 2. So again, a lot of you can immediately say that the answer is going to be 5 pi over 6. But just to go through this the long way, so we understand where this stuff is coming from, what we want to do is think about this y equals the cosine of x. So just start with this, like we did graphically. And we're going to restrict the domain. So x is greater than or equal to 0 and less than or equal to pi. If you go through, this is going to get cut off. So let me just slide down here. We'll come back up. So if you go through and find the inverse of this domain restricted function, you swap the x and the y. So you end up with x is equal to the cosine of y. And of course, this right here, which is the domain, becomes the range. So now you have y is greater than or equal to 0 and less than or equal to pi. So if I have something like, let's say, the negative of the square root of 3 over 2 is equal to the cosine of y, where y is greater than or equal to 0 and less than or equal to pi. Well, when it's written this way, you can say that y is going to be the angle between 0 and pi, where 0 and pi are included, where your cosine value is negative square root of 3 over 2. Well, again, if you just think about the unit circle and we come down here, well, I'm working from 0 to pi. So now I'm looking here. And if your argument is positive, you're going to look in quadrant 1. And if it's negative, you're going to look in quadrant 2. Again, there are exceptions to what I just said, just like previously. If you have something like the inverse cosine of, let's say, 1, well, this is going to be 0. So that's going to be a quadrantal angle. If you have the inverse cosine of 0, and that's going to be pi over 2. So that's a quadrantal angle. And then lastly, if you had the inverse cosine of something like negative 1, well, that's going to be pi. So basically, other than these guys, you can say that if your argument is positive, you're looking in quadrant 1. If your argument is negative, you're looking in quadrant 2. The argument we have, let me get rid of this, is negative. So we're looking for the inverse cosine of the negative of the square root of 3 over 2. So that tells me I want to look in quadrant 2. So looking in quadrant 2, where cosine values are negative, I see that's going to occur right here. So there's my cosine value of negative square root of 3 over 2. And the angle that's associated with that is 5 pi over 6. So the result here would be 5 pi over 6. In other words, on the graph of this guy right here, the restricted cosine function, you have the point 5 pi over 6, comma, negative square root of 3 over 2. So when you get to the inverse cosine function, these guys are going to be swapped. So you're going to have negative square root of 3 over 2, comma, 5 pi over 6. So when we answer this, we basically just say that, and I think this is cut off too far, so let me just come down here, and I'll just answer it formally. I will say that if we have y is equal to the inverse cosine of the negative of the square root of 3 over 2, then we're going to say that this is equal to 5 pi over 6. All right, let's look at another one. So we have y equals the inverse cosine of negative square root of 2 over 2. So again, you can work off the unit circle. A lot of you know this off the top of your head, but we're working from 0 to pi. Now, because that guy was a negative argument, so in other words, we had y is equal to the inverse cosine of the negative of the square root of 2 over 2. Again, when this guy is negative, I want to work in quadrant 2. That's where cosine values are negative. So just find where you have a negative square root of 2 over 2 for the cosine value, and the y there is going to be the associated angle. So basically, I'm going to find that right here. Let me just highlight that. So you have a cosine value of a negative square root of 2 over 2 with your 3 pi. So with your 3 pi over 4. So the answer here for y is just going to be 3 pi over 4. Again, if you look at the restricted cosine function, so y equals the cosine of x, where x is greater than or equal to 0 and less than or equal to pi, well, a point on that graph is going to be 3 pi over 4, comma, negative square root of 2 over 2. So that's a point on the graph. So when we think about the graph of the inverse cosine function, so y equals the inverse cosine of x, well, these x and y values are going to be swapped. So now you have this negative square root of 2 over 2, and then comma 3 pi over 4. So the inverse cosine of negative square root of 2 over 2 is going to give me 3 pi over 4. All right, just like with sine, you have the cancellation properties for cosine and the inverse cosine function when you put those guys together. So basically, if you have something like the cosine of the inverse cosine of x, it's equal to x, but only for x being greater than or equal to negative 1 and less than or equal to positive 1. So the reason for that is, again, the domain for the inverse cosine function is going to be from negative 1 to positive 1. You can't take something like the inverse cosine of 2. Again, if you plug that into your calculator, you're going to get some kind of error. So what you would do, let's say we had something like, let me just slide down here real quick, the cosine of, let's say the inverse cosine of, let's say something like 1/2. Well, again, this right here would be in quadrant 1. So I'm thinking about where is the cosine value 1/2 in quadrant 1? Well, that's pi over 3. So this, going the long way, would end up being the cosine of pi over 3, and I'm right back to 1/2. So again, if this value satisfies this inequality, so it's greater than or equal to negative 1 and less than or equal to positive 1, you can just shortcut this process and immediately give the answer of 1/2. All right, so the other property involved is going to give you a lot of trouble if you're not paying attention. So the inverse cosine of the cosine of x equals x, but this is the key. This is only for x being greater than or equal to 0 and less than or equal to pi. Now, what's causing this? This is your regular cosine function on the inside. So we know that the domain is all real numbers. So really it doesn't matter what I plug in for x. It could be 0, could be negative, could be positive. It doesn't matter. We know that the range or the outputs here are going to be from -1 to +1, and those guys are going to be included. So let me actually just mark this out real quick so we can think about this. So I know that what I'm going to be plugging in here for the inverse cosine function is going to be from -1 to +1. And again, that is the domain of the inverse cosine function. So I'm okay there. I'm never going to violate the domain. So let me erase this, and now let's think about this. When I take the inverse cosine of something from -1 to +1, with those guys being included, I know that my range, or my set of output values, is going to be from 0 to pi. So that's why we have this for x is greater than or equal to 0 and less than or equal to pi. Now, if that was confusing, let me just give you an example here, and hopefully this will make sense. So here we have the inverse cosine of the cosine of 7 pi over 4. Now, 7 pi over 4 is not in the interval from 0 to pi, where 0 is included and pi is also included. If you go to the unit circle, again, this is where we're working right here. So this is from 0 to pi. Now, if we think about 7 pi over 4, that's down here. Okay, so that's not in that interval. So what you'd have to do is say that you have the inverse cosine of the cosine of 7 pi over 4. You need to evaluate this first. So the cosine of 7 pi over 4, that's going to give you square root of 2 over 2. So we're going to say this is the inverse cosine of the square root of 2 over 2. And again, looking in the correct interval here, you see where the cosine value is square root of 2 over 2, that's going to be right here, and that's going to be with pi over 4. So you'd want to answer pi over 4. It is incorrect to say that the answer is 7 pi over 4 because that is not within the range of the inverse cosine function. So you have to be very, very careful with that type of problem. If you had gotten the problem, the inverse cosine of, let's say, the cosine of pi over 4, well, in this particular case, now you're within that interval, so these would just cancel away, and you would say this is pi over 4. Again, if you go through it the long way, which is fine, you can still do that, the cosine of pi over 4 is square root of 2 over 2, and then the inverse cosine of square root of 2 over 2 will get you back to pi over 4. All right, now let's talk about the inverse tangent function. So we're going to use the exact same process that we used with the inverse sine function and the inverse cosine function. So we're going to start off with a graph that we already know about. So that is y is equal to the tangent of x. Now, when you graph this guy, hopefully you've seen this already, you know that you have a series of vertical asymptotes, and that's going to be at odd multiples of pi over 2. So something like this is at pi over 2, and then this guy right here is going to be 3 pi over 2, and this guy right here is going to be 5 pi over 2. And if you were going this way, so this right here would be negative pi over 2, and then this right here would be negative 3 pi over 2. And then this guy right here would be negative 5 pi over 2. So again, what causes that? Well, if you go back to the unit circle, if you look at something like pi over 2 or 3 pi over 2, the cosine value is 0. And this is going to be true for pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, so on and so forth. So a lot of books will just say odd multiples of pi over 2. So what happens is, when you look for the tangent of something like that, if the cosine value is 0, you have the sine value divided by the cosine value. And again, if you're trying to divide by 0, that's undefined. So coming back up, that's why you see these vertical asymptotes here. So for the domain, and I'm going to write this in set builder notation. So I'm going to say that it's the set of all x such that x is not equal to, we're going to start with pi over 2 and then just say plus pi n. And here specifically, n is just going to be any integer. So if you added pi to pi over 2, you would get 3 pi over 2. Then if you added, let's say, 2 pi to pi over 2, you would have 5 pi over 2, so on and so forth. Now, in terms of the range, there's no restriction, right? So this is from negative infinity to positive infinity. So for the range, we're going to go, I'll just use interval notation. It's a little bit easier. So from negative infinity to positive infinity. So basically all real numbers. Now, when we look at the graph of y equals the tangent of x, obviously this is not a one-to-one function. It fails the horizontal line test. So let me make a little horizontal line here, and it would hit here, and it would hit here, and here, and here, and here. And of course, this graph continues forever to the right and forever to the left. So it's going to hit over and over and over again. So obviously, this is not the graph of a one-to-one function. So what do? Well, just like before, we're just going to take a piece of this graph such that we have a restricted domain, but we keep the same range. So what we've chosen to do in this situation is go from negative pi over 2 to pi over 2, with those values being excluded because again, tangent of negative pi over 2 or tangent of pi over 2, that's undefined because you'd have division by 0. So this is the piece that we're going to take right here. So that's what we're looking for. And let me just show you that using a better graph. So this right here would be your y is equal to the tangent of x, where x is greater than, and this is strictly greater than, negative pi over 2, and less than, and that's strictly less than, pi over 2. So this is your restricted tangent function. And just like before, if you reflect that across the line, y equals x, you'll get your inverse tangent function. So this right here in orange, this is your y equals, again, the tangent of x, where x is greater than negative pi over 2 and less than pi over 2. And then the graph in green here, this is going to be your y is equal to the inverse tangent, so the inverse tangent of x. So let's go down to this little graph here where things are easier to see. So let's write that this is y equals the inverse tangent of x. And for the domain, you'll see that it's the set of real numbers. So I can plug in whatever I want for x there. There's no problems. So I'm going to say that my domain is just going to be from negative infinity to positive infinity. And if we think about where that comes from, well, think about the range of the restricted tangent function. It's from negative infinity to positive infinity. So when we get the inverse, the domain becomes the range and the range becomes the domain. So this range here from negative infinity to positive infinity became the domain here of negative infinity to positive infinity. Now, similarly, when we look at the range here, this is coming from the domain of the restricted tangent function, which was from negative pi over 2 to pi over 2, with those guys being excluded. So this is really important. You want a parenthesis here for negative pi over 2, it's not included, and then a parenthesis next to pi over 2 because it's not included. So this value up here and this value down here, they're not included. So you would have a horizontal asymptote here and also here. So these graphs will approach those values, but never actually touch them. Okay, let's take a look at some problems. So we have y equals the inverse tangent of square root of 3. So again, when I look at something like this, I always go y is equal to the tangent of x, and I'm going to say x is greater than negative pi over 2 and less than pi over 2. And again, I'm just going to swap x and y to find the inverse. So I'm going to say x is equal to the tangent of y, where specifically, again, this was the domain, so now it becomes the range. So y is greater than negative pi over 2 and less than pi over 2. So if I plug in a square root of 3 for x there, so we'd say the square root of 3 is equal to the tangent of y. And again, where y is greater than negative pi over 2 and less than pi over 2. Well, let's think about this for a moment. I'm asking for the angle in the interval from negative pi over 2 to pi over 2 such that the tangent value is going to be the square root of 3. Well, you can use special triangles. We'll go to the unit circle in a moment. If you look at a tangent value of square root of 3, so that's going to be right there. I don't think my highlighter really shows up there. So maybe I can use a different color like black. I think that might show up a little bit better. So basically you can see that's going to happen at 60 degrees, or if you want to convert this into radians, that's going to be pi over 3. Additionally, you can always go to the unit circle and use that. The values aren't directly there, but if you look at pi over 3, again, that's in your interval. You're working from negative pi over 2 to pi over 2. The key thing is here that pi over 2 and negative pi over 2 are not included. Okay, so it's not like sine where they are included. Here they're excluded. So if I look at that, that's within the interval. And again, if you look at the tangent of pi over 3, well, really quickly, you can just look at, well, it's the sine of pi over 3, which is the square root of 3 over 2, divided by the cosine of pi over 3, which is basically going to be 1/2. So times the reciprocal, which is 2 over 1. Those 2's cancel, and you get the square root of 3. So that tells me that the inverse tangent, so the inverse tangent of the square root of 3 is going to be pi over 3, because again, it's in this interval. So let's come back, and I'm just going to answer that this guy right here is going to be pi over 3. Okay, let's look at another one. So this will be real easy. We have y equals the inverse tangent of the negative of the square root of 3. So first off, what you could do to solve this problem, the inverse tangent function and the inverse sine function are odd functions. So you could say that this is equal to the negative of the inverse tangent of the square root of 3. And we saw earlier that the inverse tangent of the square root of 3 was pi over 3. So this would be the negative of pi over 3, or just negative pi over 3. So that's the quickest way to solve that, given the fact that you know that the inverse tangent of square root of 3 is pi over 3. Now the other way, let's just do this the longer way, just so we can see it. The first thing is, if I know that y is equal to the inverse tangent of the square root of 3 is going to be equal to pi over 3, we already know that, well then what I can do is go to my unit circle and look for an angle in quadrant 4 where tangent is negative, and I'm going to want a pi over 3 reference angle. So here I'm going to rotate clockwise to get to right there. So this is not going to be 5 pi over 3. It's going to be negative pi over 3. Again, you can start with 5 pi over 3 if you want and just subtract away 2 pi. So that's 6 pi over 3. And you can get the negative pi over 3 like that if you want. Again, it's up to you how you want to do things. But essentially, you want to make sure that you're in that interval, again, from negative pi over 2 to pi over 2. Let me highlight that real quick. So I'm going to make sure to not touch pi over 2 or negative pi over 2. Those are not included. So as long as you're in this interval, you're going to be good to go. So basically, because the tangent of negative pi over 3 is equal to the negative of the square root of 3, well, because, again, this is in that interval, you can say that the inverse tangent, so the inverse tangent of the negative of the square root of 3, that's going to be negative pi over 3. So coming back up, the answer here, once again, is negative pi over 3. All right, let's look at some cancellation properties with tangent and inverse tangent. So these are very similar to what we saw earlier. So the tangent of the inverse tangent of x is equal to x for any x that's a real number. So that's basically what this is saying. This says x is an element of the real numbers. Whenever you see this r that looks like this means the set of real numbers. So let me write that out. So the set of real numbers. And this right here, if you've never taken a course on sets, this just means is an element of. Now, when we think about the inverse tangent function, remember the domain is the set of real numbers. So I can plug in whatever I want there for x, and the output will be between negative pi over 2 and pi over 2, with those values being excluded. So that means, again, you could just mark this out and say, okay, well, the tangent of between negative pi over 2 and pi over 2, that's always going to be defined, so I won't really have any issues there. So I can just basically cancel things away and say that I just have x. So if you wanted to see an example of that, you could just quickly do something like the tangent of, let's say, the inverse tangent of, let's just go ahead and do something like maybe the square root of 3 over 3, something like that. I think most of you know that the inverse tangent of the square root of 3 over 3 is going to be pi over 6. So this would be the tangent of pi over 6. And again, the tangent of pi over 6 is going to get me back to the square root of 3 over 3. So you could have just shortcutted the process and just said the answer is square root of 3 over 3. All right, let's look at the other one, and this one is where people get into trouble. So the inverse tangent of x is equal to x for x is greater than negative pi over 2 and less than pi over 2. So let me walk you through this one. So basically, let's start off with the tangent of x, so the inside part here. We know that for this guy right here, x cannot be pi over 2, 3 pi over 2, 5 pi over 2. So you could say pi over 2 plus pi n, where n is any integer, or you could say something like odd multiples of pi over 2, whatever you want to do. But basically assuming that this guy right here, you don't plug in something that gives you undefined as a result, well, then we know that the range for the tangent of x is going to be all real numbers. So assuming that you didn't plug in something that violated the domain to where you got undefined, the result of this guy right here would be all real numbers. Now, when you take the inverse tangent, again, the domain is all real numbers. And when you plug in all real numbers for this guy, you're going to get basically between negative pi over 2 and pi over 2 as a result. So that's why we say this is for x is greater than negative pi over 2 and less than pi over 2, because again, that's from the range of the inverse tangent function. So let's look at an example. So here we have the inverse tangent of the tangent of 4 pi over 3. So the tangent of 4 pi over 3, that's defined, but it's not within that range from negative pi over 2 to pi over 2. So coming back to the unit circle, again, thinking about from pi over 2 to negative pi over 2, again, those guys are excluded, so I'm trying to stop short there. And maybe I touched there, so let me try this one more time. I want to make that crystal clear that pi over 2 and negative pi over 2 are not included. So you're looking at this angle right here, which is 4 pi over 3. So that's not in that interval. So what you would have to do is first say that I want the tangent of 4 pi over 3. Now this has a pi over 3 reference angle, and you're in quadrant 3. So we know that this would be equal to the tangent of pi over 3, because again, the tangent values are positive in quadrants 1 and 3. So essentially, if I look at this guy right here, the tangent of pi over 3, it's going to be the same as the tangent of 4 pi over 3. Again, the period for tangent is going to be pi. So the tangent value is going to be the same there. So this is going to be equal to, as we saw earlier, the square root of 3. So essentially, when we solve this problem, if we say something like the inverse tangent of the tangent of 4 pi over 3, what you need to do is the tangent of 4 pi over 3 first. So this is the inverse tangent of, again, that would be square root of 3. So square root of 3. And then this equals what? Well, where's the tangent value square root of 3 in this interval here? Well, it's going to be at pi over 3. So that puts me right back to pi over 3. So you got to be really careful with these types of problems. Now, again, if you had gotten the problem as something like, let's say, the inverse tangent of, and let's go tangent of negative pi over 3. We saw that earlier. Well, this guy right here is in your interval. So we know that that's going to be right here, again, rotating. Let me do this in a different color. So rotating clockwise like that. So that's my negative pi over 3. So I can just take that in this case. That'll be the answer. So this is just negative pi over 3. All right, now let's look at some problems that deal with the inverse cotangent function, the inverse secant function, and the inverse cosecant function. So these problems are pretty easy if you already understand the inverse sine function, the inverse cosine function, and the inverse tangent function. You can actually convert them over and use those guys to get your solution. So let me start with y is equal to the inverse cotangent. Let me make that a little bit cleaner there. Of x. If you're looking this up online, or if you're using a textbook that's different from mine, you might see a different graph. And the reason for that is very simple. When you derive this guy, you start off with y equals the cotangent of x. So we know that that guy right there is not a one-to-one function. We also know it's not defined for pi n, where n is any integer. Because if you have something like 0 or pi or 2 pi or 3 pi, your sine value is going to be 0, and you'd have division by 0, which is undefined. So what you could do is take a piece of that guy, let's say from 0 to pi, where 0 and pi are not included. And basically, if you restrict that domain there, you're going to get a one-to-one function. And if you reflect that across the line y equals x, you're going to get this graph here. So in this case, the domain is now going to come from the range of that guy. So you're going to have all real numbers. So from negative infinity to positive infinity. And then the range, again, is coming from the domain of that guy. So from 0 to pi, where 0 and pi are not included. So the way you can evaluate this is to say it's x is equal to the cotangent of y, where y is greater than 0 and less than pi. So again, 0 and pi are not included. Okay, let's look at a quick little problem, and I'm going to show you an issue that's going to come up if your argument is negative for the inverse cotangent function. So we have y equals the inverse cotangent of negative square root of 3. So first off, I know that basically I can say that this is x is equal to the cotangent of y, where y is greater than 0 and less than pi. Well, the x here is the negative of the square root of 3. So basically I'm asking for what angle between 0 and pi is going to have a cotangent value that's negative square root of 3. Again, if you come back to this little table, some people have this for cotangent already, but I'm just going to use this one. If you look at this value right here for 30 degrees or pi over 6 radians, well, the tangent, so the tangent of pi over 6 is going to be the square root of 3 over 3. So that tells me the cotangent of pi over 6 is going to be, again, take the reciprocal of this, so 3 over the square root of 3. Now, you could do this in different ways. You could rationalize the denominator, or a quicker way would be to say that 3 is the square root of 3 times the square root of 3. So you could do it that way if you want. So this would cancel, and you get the square root of 3. So pi over 6 would be my reference angle in quadrant 2. So in quadrant 2, what angle has a reference angle of pi over 6? Well, it's going to be 5 pi over 6. So this right here would just be equal to 5 pi over 6. Again, it's got to be within this interval for you to give that answer. Another way you could have done this is by using the inverse tangent function. So let's say you started with the inverse cotangent of your negative square root, and let me make that a little bit better, of 3. Can you say this is equal to the inverse tangent, so the inverse tangent of the reciprocal of this, so the negative of 1 over the square root of 3, if you rationalize the denominator, that is the square root of 3 over 3? Well, the answer to that question is no. You need to issue a little bit of a correction, because this right here, so this right here is going to give you something in quadrant 4 rotating clockwise. So this guy right here would give you this guy right here. So this would be negative pi over 6. So a pi over 6 reference angle in quadrant 4, and you've got to rotate clockwise. But the answer is actually going to be right here at 5 pi over 6, because with the inverse cotangent function, I'm working from 0 to pi. So I'm working right here. So what you would want to do is make yourself a little correction and add pi. So I'm going to add pi so I can swing around right there. And that's going to give me the correct answer. So I'm going to add pi to issue a correction here. And so this would be negative pi over 6 plus pi. Let's write that as 6 pi over 6. And so that would be equal to the 5 pi over 6. That is the correct answer. So if you're using your calculator, you need to be aware of this. If your argument is positive, you're going to be in quadrant 1, so you're okay there. You don't have to issue a correction because the inverse tangent of something that's positive is going to give you something in quadrant 1 as well. But if this guy is negative, you're getting something in quadrant 4 for the inverse tangent function, and you're getting something in quadrant 2 for the inverse cotangent function, so you have to be very, very careful and issue a correction there. Now, if you do the inverse cotangent of 0, you're just going to end up getting pi over 2 as an answer, so that's one you just need to memorize. All right, so the next graph is going to be for the inverse secant function. So y equals your inverse secant of x. So if you look at the domain, so this one, let's just do it in interval notation. So from negative infinity to negative 1. So let's go from negative infinity up to and including negative 1. So again, this is included here. You have a point there. This would be negative 1 comma pi. And then basically the union with positive 1 is included and out to positive infinity. So basically the values between and not including negative 1 and positive 1, those are excluded from the domain. So then for the range, let me write that down here. So for the range, you can see that this guy is going to be from 0 to pi, where basically this pi over 2, let me write this in so this is not confusing. So this is pi over 2 here. That's not going to be included. Let me write up here that this is going to be pi. So the range you're going to have, let me move this up a little bit so it fits, basically from 0 and including 0, going up to and excluding pi over 2, and then the union with, you're going to have, again, pi over 2 is excluded, going up to and including pi. Okay, let's take a look at a little sample problem. We're going to convert this over and solve it very quickly. So here we have y equals the inverse secant of square root of 2. So essentially what I'm going to do is actually say that this is equal to the inverse cosine of, I'm just going to take the reciprocal of this, so 1 over the square root of 2. So if you rationalize the denominator there, this becomes the square root of 2 over 2. And so this, we know, is going to be pi over 4. So for these problems, you don't have to issue a correction. Basically, you're just going to key it in like this. So if you have the inverse secant of something, you basically are going to take the reciprocal of that value and have the inverse cosine of that, and that's how you're going to get your answer. All right, let's take a look at the inverse cosecant function. So again, with the inverse cotangent function, the inverse secant function, and the inverse cosecant function, it might look different in your book or your online resource. So just telling you that in advance. So this guy right here for the domain, pretty easy to see. Basically, it's going to be from negative infinity up to and including negative 1. So this right here, this is a point that's included. So this would be negative 1 comma negative pi over 2. And then basically the union with this point right here, this is positive 1 comma pi over 2. So basically, you're going to take from positive 1 out to positive infinity. So that's your domain. And then in terms of your range, well, that's going to be from negative pi over 2 to pi over 2, where you're going to exclude 0. So basically, let's say we have from negative pi over 2, and then we're going to go up to and exclude 0. And then the union with, again, we're excluding 0, and we're going up to pi over 2. So pi over 2 and negative pi over 2 are included, but 0 here, that's going to be excluded. Okay, let's look at a problem. So here we have y equals the inverse cosecant of a negative 2 times square root of 3 over 3. Again, all you have to do for this problem is say this is equal to, I'm going to use my inverse sine function. So my inverse sine function, and I'm just going to take the reciprocal of the argument here. So it's going to be the negative of 3 over 2 times the square root of 3. So let me go ahead and write this as the square root of 3 times the square root of 3. And I'm going to cancel this with this. And so this becomes the negative of square root of 3 over 2. So the negative of the square root of 3 over 2. And this one, you might benefit a little bit from the unit circle. So again, with the inverse sine function, you're working in quadrants 1 and 4. If you're in quadrant 4, you've got to rotate clockwise. So where is my sine value? Negative square root of 3 over 2. It's going to be right there at 5 pi over 3. But again, you've got to rotate clockwise. So the reference angle there is pi over 3. So you'd say this is negative pi over 3. So that's what you want for your answer. Let me just move this down here. This would be equal to negative pi over 3. So these types of problems are really easy if you already understand the inverse sine function. All right, now let's move on and look at some typical examples for this section. So what if you see something like the inverse sine of the tangent of negative pi over 4? Well, the idea for this type of problem is to evaluate this part first. So what's inside, or what's going to be the argument for the inverse sine function. And so you would say, what is the tangent of negative pi over 4? A lot of you know that's negative 1. But again, just in case you don't, you're going to look at your unit circle and you're going to say, well, where is negative pi over 4? Well, again, I'm looking in quadrant 4 and I want a pi over 4 reference angle. So that's going to be right here at 7 pi over 4. But what I'm doing is I'm rotating clockwise. So I want this guy right here. Again, rotating clockwise. Let me do this in a different color here so this shows up really well. So this right here is the angle that I'm looking for, negative pi over 4. Now, of course, this is coterminal with 7 pi over 4. So if I want the tangent of negative pi over 4, I can just say that's equal to the tangent of this 7 pi over 4, and I could just grab that from the unit circle. Again, here you want the sine value, which is negative square root of 2 over 2, divided by the cosine value, which is square root of 2 over 2. So I'm dividing opposites, so I'm going to get negative 1 as a result. So coming back up, this would be the inverse sine of this right here is negative 1. And again, a lot of you already know this is going to be negative pi over 2. But again, because we just started with this section, let me get rid of this. You're thinking about where your sine value is negative 1. So that's going to be right here. But again, that's not in the interval of the inverse sine function. So I can't give this 3 pi over 2 as a result. So what I want to do is think about rotating clockwise. So clockwise like this. And basically, that's going to give me an angle that is negative pi over 2. And of course, that's coterminal with 3 pi over 2. So the sine value is going to be the same. It's going to be negative 1. So coming back up, I want to give an answer here that's going to be negative pi over 2. All right, let's look at another common type of problem for this section. So you might see something like the tangent of the inverse sine of 3/4. So what can you do for this type of problem? Well, of course, you could pull out your calculator and you can key in the tangent of the inverse sine of 3/4, and it will give you an approximation. But in most cases, you're asked to find the exact value. So for that, what I recommend is to make a little substitution for this part right here. So the inside right here, which is the argument for the tangent function, you're going to let something like, let's say, theta be equal to this guy right here. So the inverse sine. So the inverse sine of 3/4. And so since theta is equal to this, I can say that now I'm trying to figure out what is the tangent of theta. So I'm just going to say for right now, this equals what? So let me slide down and let's think about, do we have enough information to figure out what the tangent of theta is? Well, of course we do. First off, we know that if theta is equal to the inverse sine of 3/4, then we can say, so I'm going to put then, we can say that the sine of this angle theta is equal to, my sine value is 3/4. Again, if the sine of theta is 3/4, well then the inverse sine of 3/4 is going to get me back to theta. Now we also know that if sine is positive, I'm going to be in quadrants 1 or 2. But specifically here, because I'm working with this inverse sine function and the argument is positive here, I know I'm going to be in quadrant 1. This is always going to be true unless you have the inverse sine of positive 1, which is pi over 2. That's a quadrantal angle, but that's the only exception. So for this particular case, I know that theta is in quadrant 1. And I went over my border a little bit. So let me put the border like this. And so now I can go back to what I talked about earlier on in the course when we said that, okay, if the sine of theta is equal to 3/4, well, that 3 is going to be your opposite or your y, and that 4 is going to be your hypotenuse or your r. So if I want to figure out the tangent of theta, remember this is going to be your y, or your opposite, over your x, which is your adjacent. So I already know that y is 3. So I can just plug that in right now and say this is 3. And I just need to figure out what is x. So you're going to use your Pythagorean theorem. You don't have to do this, but I went ahead and made a little sketch. So remember, for the Pythagorean theorem, you have x squared plus y squared is equal to r squared. So in this case, we know that the y, or the opposite side, is 3. So I'm just going to plug that in there. We know that the r, or the hypotenuse, is 4. So I'm going to plug that in there. We're going to find that the x, or the adjacent side, is going to be square root of 7. Right now, I don't know that. I'm going to solve for that. So here I would have x squared plus 3 squared is 9. And this equals 4 squared, that's 16. So what I'm going to do is subtract 9 away from each side of the equation. And so this right here is going to cancel. You'll have x squared is equal to 16 minus 9 is 7. Now, by the square root property, you would say that x is equal to plus or minus the square root of 7. Now, I'm in quadrant 1, where x values are positive, so I don't need the plus or minus here. X is going to be the principal square root of 7. So now I know that the adjacent side here, or the unknown x, is going to be square root of 7. And just coming back up, I'm going to put that this right here is the square root of 7. And let me move this over here. I can just answer that this right here is 3 over the square root of 7. So 3 over the square root of 7. And of course, you would want to rationalize the denominator, so times the square root of 7 over the square root of 7. So my final answer here for the tangent of the inverse sine of 3/4 is going to be 3 times the square root of 7 over 7. All right, now let's look at another type of problem. So this one is just a little bit more tedious than the previous problem. So we have the sine of the inverse sine of 1/2 plus the inverse tangent of -3. So for sure, you're going to get a problem like this in your textbook. And what you want to do is start off by asking, can I replace anything in my problem? So in other words, I know that the inverse sine of 1/2 is pi over 6. Let me just come down to the unit circle. Again, this is new for us. I know a lot of you already know that. But again, I'm working from negative pi over 2 to pi over 2. And I am asking the question, what is the inverse sine? So what is the inverse sine of 1/2? So I'm looking for a sine value of 1/2, so that's going to occur right here. And so what I want for the associated angle is pi over 6. So the sine of pi over 6 is 1/2, so the inverse sine of 1/2 is going to be pi over 6. Again, it's got to be in this interval from negative pi over 2 to pi over 2. So this right here is going to be pi over 6. So coming back up here, I'm just going to replace this with pi over 6. So this is the sine of your pi over 6 plus, now this one, I'm going to make a substitution for it. Let me just write it in for right now. So the inverse tangent of -3. Okay, so just like in the previous problem, we have something here where we're going to make a little substitution. So you have the inverse tangent of -3. Let me slide down here real quick. And I'm just going to put that we are going to let something like beta be equal to the inverse tangent of -3. So what I'm going to do is replace this right here with beta. So I'm going to say that now I'm looking for the sine of pi over 6 plus beta. Remember, when we think about this beta here, if we let beta be equal to the inverse tangent of -3, that tells me that the tangent of beta is equal to -3. Now, where is beta? Remember, the inverse tangent function is going to give you something in quadrant 4, rotating clockwise if the argument is negative. So that tells me, let me put a little border here, that beta is in quadrant 4. Okay, so we're going to use that in a little while. So the first thing is I'm going to grab this and copy it, and I'm going to go to another page, and let me paste this in here. When you have the sine of a plus b, in this case it's pi over 6 plus beta, but the sine of a plus b is equal to the sine of a times the cosine of b plus the cosine of a times the sine of b. This is your sum identity for sine that we talked about earlier in the course. So we're going to say that this sine of, you have this pi over 6 plus beta, this is equal to the sine of the first guy, which is pi over 6, and then times the cosine of the second guy, which is beta, and then plus the cosine of the first guy, which is pi over 6, and then times the sine of the last guy, which is beta. So the sine of beta. So this equals what? In terms of the sine of pi over 6, we know that's a half, and the cosine of pi over 6, that's square root of 3 over 2. Most of you don't need this at this point, but again, if you don't have a unit circle, here's pi over 6, so the sine value is 1/2, and the cosine value is square root of 3 over 2. So let me come back up here. So the sine of pi over 6 is 1/2, and then times your cosine of beta, and then plus the cosine of pi over 6 is the square root of 3 over 2, and then times your sine of beta. So what I need to do is I need to figure out what is the cosine of beta. So the cosine of beta is, again, that's your adjacent over your hypotenuse, or we say the x over the r. And then what is the sine of beta? So the sine of beta is equal to your opposite over your hypotenuse, or your y over your r. Well, let's go back up and let's remember that we know that the tangent of beta is equal to -3. You can go ahead and say that this is -3 over 1. So this right here is the y value. It's going to be -3 because, again, we're in quadrant 4. So the y values are going to be negative and the x values are going to be positive. And this right here will be your x value. So that's +1. So let's come down here, and I'm just going to write in that the tangent of beta is equal to -3 over 1. Again, this is your y, and this is your x. So we can come through here and say that x is 1, so I know this is a 1, and then y is -3, so I know this is -3. Now, how do we get r? Again, go back to the x squared plus y squared equals r squared. And again, you can make a sketch. It's not necessary, but you can do it. So let's put x squared plus y squared equals r squared. We're going to find out that r, or this hypotenuse here, is square root of 10. But to get that, x, or your adjacent, is going to be +1. So this is 1 squared plus your y, or your opposite, is going to be -3. Remember, you're in quadrant 4, so the y values are negative. So this is -3. Make sure to wrap that. And this is going to be squared. And this equals your r being squared. So that's going to be for your hypotenuse, that guy being squared. Okay, so this is pretty straightforward. 1 squared is 1. And then plus -3. Again, this is wrapped, being squared. That's +9. And this equals r squared. So you get r squared is equal to 10. Again, by the square root property, you get r is equal to plus or minus the square root of 10. Now your r is always positive. So this is just the principal square root of 10. So your x is 1, your y is -3, and then your r is going to be square root of 10. So coming back up, if I know that r is square root of 10, I'm just going to replace that here. So this is square root of 10. And then this right here is square root of 10. Okay, I'm going to get rid of this. We don't need this anymore. And I'm going to rationalize the denominator in each case. So this is times the square root of 10 over the square root of 10. So this equals the square root of 10 over 10. And then here times the square root of 10 over the square root of 10. So this equals -3 times the square root of 10 over 10. Okay, so I just need to replace here and here. So what I'm going to have, let me put equals. You have 1/2 times the cosine of beta is the square root of 10 over 10. And then plus you have the square root of 3 over 2 times the sine of beta. That's -3 times the square root of 10 over 10. So this equals, I would just multiply and say this is the square root of 10 over 20. Just multiplying 1 times the square root of 10, that's square root of 10, and 2 times 10 is 20. So then you have plus, you have the square root of 3 times -3 times square root of 10. So let's go ahead and write that as a negative here. And I'll put 3 times the square root of 30. Square root of 3 times square root of 10 is square root of 30. And you really can't simplify that any further because 30 is 6 times 5, 6 is 2 times 3. So you really can't do anything more with that. So then this is over. 2 times 10, that's going to be 20. So what I'm going to do is write this with a common denominator. So I'm going to say this is the square root of 10 minus 3 times the square root of 30 over the common denominator of 20. All right, so let's come back up here to the top. And let me just paste this in. So I'm going to say that the sine of the inverse sine of 1/2 plus the inverse tangent of -3 is going to be equal to this square root of 10 minus 3 times square root of 30 over 20. In this lesson, we want to talk about solving trigonometric equations using linear methods. All right, so let's start off with the easiest possible scenario. We're going to solve some trigonometric equations, again, with these linear methods. Let's say you had something like 2 plus 4 times the sine of theta is equal to 4. So what we're trying to do here, we're trying to find values of theta, okay, that I could plug in here and make the equation true. Now, before I go through this, let's just look at something from basic algebra, so we'll remember this. If I had something like 2 plus 4x is equal to 4, how would I solve this? Well, I'm trying to find values for x that make the equation true, right? So I would first try to isolate x. So I would subtract 2 away from each side of the equation. And so this is going to cancel. I would say 4x is equal to 2, divide both sides by 4, and I get that x is equal to 1/2, okay? So I plug a 1/2 in there, and basically you have what? You have 2 plus, basically 4 times 1/2 is 2, so 2 plus 2 gives me 4, so that is the correct solution. With this guy, it's not as straightforward. It's not as easy because remember, you're plugging in an angle measure there. Sine of that guy would give you a number, okay? So you're looking for sine of some value. I can already tell you that this needs to be 1/2 for this to be true. So where is sine of theta equal to 1/2? Okay, that's what you're going to be looking for. But to solve this fully, let me subtract 2 away from each side of the equation. This cancels. We get 4 times the sine of theta is equal to 2. We divide both sides by 4. And basically, we're going to get that the sine of theta, again, is equal to 1/2. Okay? So from this guy right here, this is where you need to basically do a little bit of detective work. Okay? There are so many ways to solve this. It's not even funny. You might want to use a calculator and use your inverse sine function. You might want to use the unit circle. There's a lot of different things that you could do. You could use the special triangles that you remember, all kinds of ways. So let me talk about 2 ways that you can solve this. First, let's think about the unit circle approach. So if you are lucky and you get an easier problem where basically you can find this from the unit circle, you can go to the unit circle. If I'm looking for sine of theta is equal to 1/2, well, you can look for the y coordinate and find out where it's 1/2. Okay, so for 30 degrees or pi over 6 in terms of radians, the y coordinate is 1/2, right? So that tells me that sine of 30 degrees is equal to 1/2. Then also, I know that sine is positive in quadrant 2. So remember, when we think about reference angles, if the reference angle is 30 degrees, then sine of that guy is also going to be 1/2, right? So where would I have a reference angle of 30 degrees? Well, with 150 degrees, right? Because 180 degrees minus 150 degrees, the reference angle would be 30 degrees. So sine of 150 degrees, and I'm messing up my writing there, so sine of 150 degrees would also be 1/2, right? And you can see that here. This is 1/2, this is 150 degrees, or 5 pi over 6 if you're talking about radians. Now, when you talk about solutions over the interval from, if you're thinking about 0 to 360 degrees, your solutions would be 30 degrees and 150 degrees. But when you think about a general solution, remember, when you think about sine and cosine, the period is 360 degrees or 2 pi, okay? So that means if I started here and I rotated around 360 degrees, well, instead of 30 degrees, now I'd have 390 degrees, and sine of 390 degrees would also be 1/2, okay? If I added 360 degrees again, then sine of, in that case, 750 degrees would also be 1/2, so on and so forth. Same thing with 150 degrees. If I add 360 degrees, I'm going to be at 510 degrees. Sine of that guy would be 1/2 as well, okay? So let's take that information and come back here and give a solution, okay? So first, let's pretend we're restricting the domain. So 0 to 360 degrees, or again, you might see this in terms of radians. So you might see 0 to 2 pi in terms of radians. Whatever you get, you want to match that in terms of your answer, okay? So if you get degrees, put degrees. If you get radians, put radians, okay? So in this case, I'll just do both. So in this particular case, I'll say that theta is equal to, we had 30 degrees and then also 150 degrees. And again, the reference angle for both of those is going to be 30 degrees. And then if we look at, in terms of radians, we could say theta is equal to pi over 6. This is 30 degrees in terms of radians. And then 5 pi over 6. This is 150 degrees in terms of radians. Now, this is the solution for the restricted domain. If you want a general solution, so let me put the general solution. Okay, so this is going to keep working as we either rotate clockwise or counterclockwise. So remember, if you go 360 degrees, doesn't matter which direction. If you go negative direction, so you're going clockwise, or you go the positive direction, so you're going counterclockwise, you're going to keep getting these guys. Okay, so I'm going to start with, let me make some set braces here. Okay, this is typically how you'll see it. I'm going to take this solution. You could do it degrees or you could do it radians. I'll do both. So 30 degrees. Plus the 360 degrees, okay? When you go around, again, you're going to get that same value, and then times n, where n is just any integer, okay? And then I'm going to do 150 degrees, and then plus this 360 degrees. Let me slide all of this down, because it's not going to fit. So let me move this down, and let me put this comma back where it should be, right there. Okay, so this, I'll close my set braces and I forgot my n. So let me put the n there. Okay, so that's your general solution in terms of degrees. With radians, you would say pi over 6 plus, remember, 360 degrees is just 2 pi. Okay, so I'm going to put 2 pi n, and then I'll do 5 pi over 6 plus 2 pi n. Okay, so there's your general solution. There's your solution for having this domain restriction, okay, where basically you're between 0 and 2 pi, or if you think about this in terms of degrees, 0 and 360 degrees. Now, let's talk about another way that you could have gotten this answer. In a lot of cases, especially harder cases, you're not going to be able to use the unit circle, okay? So what you want to do is use your inverse sine function. So let me use a fresh sheet here. Let's say I looked on my calculator and I did inverse sine of, in this particular case, we were looking at a half, okay? So you punch this into your calculator, and we already know you're only going to get one value, right? You're just going to get 30 degrees, okay? But again, if I think about sine of theta is equal to 1/2, there's an infinite number of angle measures there that's going to be true for this. And if I have one of them, then I can find all of them, again, because where is sine positive? It's positive in quadrants 1 and 2, okay? So I have the answer from quadrant 1. I have my answer from quadrant 1. It's going to be 30 degrees. And again, it repeats. So 360 degrees in either direction. So if I go plus 360 degrees or if I go minus 360 degrees, I'm going to, again, run into another solution. But in quadrant 2, I just need an angle where the reference angle is 30 degrees, okay? So again, that's going to be found by taking 180 degrees. So I would take 180 degrees, okay, minus 30 degrees, and that gives me 150 degrees, okay? So this is the angle I'm looking for. So in quadrant 2, I get 150 degrees. So that's another way that you could solve this. You could also use special triangles if you wanted to, okay? So there's a lot of different ways to think about this guy. Okay, let's look at another example. So we have the cosine of theta now instead of the sine of theta. So we have -4 minus 4 times the cosine of theta is equal to -3 minus 2 times the cosine of theta. And again, if you were working with this, let's say you had something like -4 minus 4x is equal to -3 minus 2x. Well, I'd want to get all the terms with x on one side, all the numbers on the other. Same thing here. I'm going to get all the terms with cosine of theta involved on one side, all the numbers to the other. So let me add 4 to both sides, okay? And let me add 2 cosine theta to both sides, okay? And basically, we see that over here, this is going to cancel. Over here, this is going to cancel. So I have -4 plus 2, which is -2, times the cosine of theta is equal to -3 plus 4, which is 1, okay? To isolate this guy, I'm going to divide both sides by -2, and I'm basically going to find that the cosine of theta is equal to -1/2. Again, another easy problem where you can get this from the unit circle, but let's go ahead and use our inverse cosine function. So let's go cosine inverse of -1/2, and let's do a little bit of detective work. If you punch that in on a calculator, you're going to get 120 in terms of degrees, okay? So let me erase this so I can drag this up. We'll have a little bit of room, okay? Let me bring this up. And let's think about this. So I have 120 degrees there, okay? So in terms of the reference angle for that, remember, if you're in quadrant 2, the reference angle is 180 degrees minus your angle, which is 120 degrees. So this is going to be 60 degrees. So this is my reference angle, okay? So what I want to do now, again, because this is negative here, cosine is negative in quadrants 2 and 3. So I have my quadrant 2 solution. My quadrant 2 solution is 120 degrees. For my quadrant 3 solution, I want to think about an angle in quadrant 3, okay, that has a reference angle of 60 degrees. How do I find that? Well, in quadrant 3, I would want to take 180 degrees, and I would want to add to that 60 degrees, which is my reference angle, okay, which would give me 240 degrees. Okay, this is 240 degrees. And the reason that works is, again, if I had a 240 degree angle and I said, hey, what's the reference angle? You would subtract 180 degrees to get 60 degrees, okay? So this is my answer in quadrant 2. This is my answer in quadrant 3, okay? Now, again, if you wanted a general solution, so let's pretend that first you got a domain restriction from 0 to 360 degrees, like this. And then also in terms of radians, we have 0 to 2 pi, okay, like this. So for the degrees, you would just put that theta is equal to 120 degrees, okay, and then 240 degrees. And then for your general solution, again, all you have to do in this particular case is, let's use some set braces here, and we'll say 120 degrees plus 360 degrees times n, where n is any integer, and then you'd have 240 degrees plus 360 degrees times n, where n is any integer. Okay, if you want to do this in terms of radians, we can do that as well, no problem. So we would say something like theta is equal to, within this domain, 120 degrees is going to be 2 pi over 3, okay? And then we also have 240 degrees, which is going to be 4 pi over 3, okay? For the general solution, I just go 2 pi over 3 plus 2 pi n, and then I go 4 pi over 3 plus 2 pi n. Okay, so again, the period for cosine and sine is 360 degrees or 2 pi in terms of radians. So that's what you want to add. So you have 2 pi, and then n is just any integer. Okay, so that's how you want to do that. Now, if you wanted to solve this more quickly, especially if an easy problem, use the unit circle. So where's the x value, -1/2? Well, again, you come over here. -1/2 is 120 degrees or 2 pi over 3 radians, okay? And then also 240 degrees or 4 pi over 3 radians, you got -1/2 again is the x value, okay? So this is the quickest way to do it. The other way is something you need to understand because in some situations you're not going to be able to use the unit circle. They're going to at some point give you harder problems. Okay, let's look at one more problem, and this one has tangent involved. Remember, the period for tangent is now going to be pi, okay, or 180 degrees. So you have to keep that in mind here. So if I have something like the negative of the square root of 3 plus 4 minus tangent of theta is equal to 4 plus 8 times the tangent of theta, well, immediately I can just get rid of the 4 from each side, right? Same thing on each side, just get rid of it. And what I want to do now, let me go ahead and subtract 8 times the tangent of theta away from each side of this guy. So I forgot my 8. So minus 8 times the tangent of theta, okay? So this will cancel out over here, okay? And I'm just going to add 3 times the square root of 3 to both sides. So what I'm going to end up with is, you can put a -1 there. You'll say you have -9 times the tangent of theta is equal to 3 times the square root of 3. Divide both sides by -9, okay? Let me scroll down just a little bit, and I'll say that I have the tangent of theta is equal to, the 3 is going to cancel with the 9. This is a 1, this is a 3. So let's say the negative of the square root of 3 over 3. Okay, so now with tangent, it is a little bit more challenging to think about these. You could use your special triangles in this particular case and just think about the square root of 3 over 3. The tangent of 30 degrees is square root of 3 over 3. So let me just write this over here. The tangent of 30 degrees is equal to the square root of 3 over 3. So again, I would say that tangent is going to be negative where? Let me draw this out here so we remember this. So we remember all students take calculus. So tangent is negative in quadrants 4 and 2, okay? So let's think about this. In quadrant 2, where would I have a 30-degree reference angle? Again, if I take 180 degrees and I subtract off 30 degrees, that gives me 150 degrees, okay? My reference angle here for a 150-degree angle would be 30 degrees. So my value here, if I did tangent of 150 degrees, because it's negative, I would get the negative square root of 3 over 3, okay? So let me erase this for a second. Let me just put one answer here. So theta here would be 150 degrees, or again, if you want to write this in terms of radians, this is 5 pi over 6, okay? Whatever you want to do. So let me erase this for a second. Let's think about in quadrant 4. So remember I said the period when you work with tangent is 180 degrees. So I can just add 180 degrees to this, okay? So 150 degrees plus 180 degrees is going to be 330 degrees, okay? Also, what you could have done, and this is 11 pi over 6 in terms of radians, also what you could have done is, again, look for a 30-degree reference angle in quadrant 4. So in quadrant 4, I would just go 360 degrees minus 30 degrees is going to give me 330 degrees. So this is the angle I'm looking for. All right, so obviously these would be your solutions if you had a domain restriction, okay? But if you didn't have a domain restriction, let me just write this over here. So this is 0 to 360 degrees, and this one is 0 to 2 pi, okay, in terms of radians. If you didn't have a domain restriction, you have to be careful because a lot of students will come through here. They're used to working with sine and cosine. So they go 150 degrees plus 360 degrees times n. Okay, this is actually wrong. Okay, the period for tangent is 180 degrees. So you want to put 180 degrees like this. Now, do you need to list 330 degrees plus 180 degrees times n? No, you do not. And the reason for this is if you go back to this one right here, let's say n is 1. Well, you're basically adding 150 degrees to 180 degrees, you get to 330 degrees. So you don't need to put this guy in here, it's just overkill. Okay, just put it like this and be done with it. Okay, then the other one over here for radians, you're just going to put 5 pi over 6 plus you're going to do pi, okay, which is 180 degrees in terms of radians, times n. Okay, that's all you need to do because again, if you added basically 1, you could get a common denominator and say it's 6 over 6. So if you had 6 pi over 6 plus 5 pi over 6, you would get 11 pi over 6, okay? So again, it's overkill to list both of them in that case. You just want to list it like this as simply as you possibly can. In this lesson, we want to talk about solving trigonometric equations by factoring. All right, so now we're just going to look at the next scenario. We already talked about how to solve these basic trigonometric equations using linear methods. Now we're just going to be factoring. So we have 3 times cosine theta plus 2 times cosine squared theta equals -1. So a very easy problem. You want to get this. If you see something with a squared term in it, you want to think about factoring right away. Okay, that's usually how you're going to solve that. And you want to think about getting it in the form of ax squared plus bx plus c equals 0. Okay, remember this is a quadratic and you're able to solve this by factoring and then setting each factor equal to 0, right? That's the 0 factor property. So I'm going to do the same thing here. I'm going to move this to the left basically. So I'm going to say I have 2 times cosine squared theta and then plus this 3 times cosine of theta. And I can add 1 to both sides of the equation. So say plus 1 and this equals 0. So if I can factor the left side, again, I can use that 0 factor property. There is a tremendous roadblock to factoring this when you first start. I don't know why it is, but when I work with students, and I'm just going to do it on the first one, I tell them just make a little substitution. So in this case, you're working with cosine of theta. So just let something like u be equal to the cosine of theta. Okay, so everywhere you see cosine of theta, replace it with u. So here I have cosine squared theta, which is basically cosine of theta squared. So I would say I have 2u squared plus, in this case, 3u, and then plus 1 equals 0. So from here, could I factor this and solve it using factoring? Yes, of course I could. So this guy is a prime number, and this guy is 1. So this is really easy to factor. This is going to be 2u, and this is going to be u. We know that off the top. And we know that because this is positive 1 and all the signs are positive, the only possibility is that this would be 1 and this would be 1. So basically you would check this and say, okay, well 2u times u is 2u squared. The outer would be 2u, the inner would be u. So those combined together would give me the 3u, and the last would be 1 times 1, which is 1. So we're good to go. So you could have factored this the same way using the same principles with the cosine of theta in there. But again, I use u there just to avoid the little roadblock of first factoring a trigonometric expression like this. So what I want to do now is because u is cosine of theta, I just want to plug back in. So I'm going to say 2 times, everywhere there's a u, I'm plugging in a cosine of theta, then plus 1, and then times, you have your cosine of theta, plus 1, and this equals 0. So now that we've got this guy factored, let's set each factor equal to 0, and let's see if we can get a solution. So I'm going to start with this one. I'm going to say 2 times cosine of theta plus 1 equals 0. Let's subtract 1 away from each side of the equation. We're going to get 2 times cosine of theta is equal to -1. Divide both sides by 2, and I'm going to get that the cosine of theta is equal to -1/2. So you're going to see the same numbers pop up over and over again. You probably at this point know that the values for this in terms of degrees would be 120 degrees and 240 degrees. But I'll go to the unit circle in a moment and show you. So let me just erase this, kind of make this a little bit more neat. And I'll just say that cosine of theta is equal to -1/2. Let me just slide this over just a little bit. And I'll delete this from here. And I'm going to go down to the unit circle all at once. So let's do this side now. So we have cosine of theta. Basically, you're just subtracting 1 away from each side. So let's do the full thing. So plus 1 equals 0. Subtract 1 away from each side. You get cosine of theta is equal to -1. You probably know already this happens at 180 degrees or pi if you're thinking about radians. So let's move this up and say we have cosine of theta is equal to -1. So let's go to the unit circle real quick and get all of our solutions. Again, you can also do this using your calculator. You can do it with special triangles. There's so many ways to do it. But for the first two, they're very easy. I'm going to give you a final problem where you have to use your calculator. There's no other choice. Okay, so we'll see that. So let's go down to the unit circle. So again, if we're looking for cosine of theta is equal to -1/2, and then cosine of theta is equal to -1, where you're looking for an x value of -1/2. So that's going to happen here, again, at 120 degrees or 2 pi over 3 radians. And then also, remember, this guy would have a reference angle of 60 degrees. So you would want 240 degrees because that also has a reference angle of 60 degrees. So this is your -1/2 there. Again, 240 degrees or 4 pi over 3 radians. So let's write 120 degrees. And then I'm going to write 240 degrees out here. I'll put a little space here because I'm going to put this 180 degrees here for the -1, right? So -1 is your x value there. So let's put 180 degrees there. And let's just put the radians in there as well. Generally, you're going to give your answer based on the restriction you get, right? If they tell you the interval is between 0 and 360 degrees, you put degrees. If they tell you 0 to 2 pi, you put your radians. So let's go ahead and put, we have 2 pi over 3. We have pi, and then we have 4 pi over 3. So let's go ahead and copy this. We're going to need that. And we're back here. So let me just go ahead and paste this in. Bring this over here. So this is going to be our solution. Again, if you restrict the domain, so for this one, let's say that we restrict the domain from 0 degrees to 360 degrees. Okay, so basically in that interval, for this one, this is going to be if you restrict it from 0 to 2 pi, okay, in terms of radians. So based on what you get, that's how you're going to get your answer. If you're asked to get a general solution, remember, these guys are going to repeat, right? So with the sine or cosine, if you're working with one of those, the period, okay, is going to be 360 degrees or 2 pi in terms of radians. So just take this. If you wanted a general solution, so let's put general solution here. You would take these guys. So I'm going to say 120 degrees plus 360 degrees times n, where n is just any integer. You're just going to take all of them. So then 180 degrees plus 360 degrees times n. And then lastly, 240 degrees plus 360 degrees times n. Okay, let me close the set braces. Then for this one, remember 360 degrees is like 2 pi in terms of radians. So what I want to do here is say 2 pi over 3, and then plus, we'll have 2 pi times n. Okay, so n is any integer. Same thing, so pi plus 2 pi n, and then lastly 4 pi over 3 plus 2 pi n. So we have our general solution here, and then we have our solution where basically we're in an interval. You could say you're restricting the domain. All right, for the next one, let's look at 4 equals sine of beta plus 2 times sine squared beta plus 3. Again, if you have something squared and then something to the first power, I'm always thinking factoring, right? I'm always thinking ax squared plus bx plus c equals 0. So I'm going to write it like that. I'm going to first, let's go ahead and flip the sides. I want everything to be on the left side that I'm working with. So let's go ahead and say we have 2 times sine squared beta plus, let's say, sine of beta. I'm going to subtract 4 away from each side of the equation. So this would end up being basically -1 over here, because if I subtract 4 away from each side, this would be -1, and this equals 0. So now what I have here, I should be able to factor. So again, if you're struggling with this, if you just can't get past the mental roadblock, go ahead and take sine of beta and set that equal to a variable like u. But I think we can get past it, right? So I'm just going to put sine of beta here and sine of beta here to start. Now this 2 in front, that's a prime number, so I've got to stick that in one of these, so I'm just going to stick it here. So we have 2 times sine of beta times sine of beta, which will give me 2 times sine squared beta. Okay, so that works. Now we have alternating signs here. Let's think about this. We have a -1 as a final term, so it has to be 1 times 1, but we have to think about the signs there. Is it going to be plus here and minus here, or vice versa? Well, the outer here would be 2 times sine of beta, but it would be negative. And then the inner would be plus the sine of beta. So that's not going to work because the middle term's positive, okay? So that means I need a plus here and a minus here. So let's erase this. And now you see it works out, right? Because the outer would be 2 times sine of beta. And then the inner would be minus sine of beta. And so if I do the subtraction, I get my plus sine of beta, and then -1 times +1 is -1. So we have correctly factored this guy. Same thing. So 2 times sine of beta -1, setting that equal to 0. Let's go ahead and solve it. Add 1 to each side of the equation. you get 2 times sine of beta is equal to 1. And I'm going to divide each part by 2 here. And basically I get that the sine of beta is equal to 1/2. So let's erase this. And you see these values so often, it's almost like you start dreaming about them. We know that this is going to be 30 degrees or 150 degrees. Again, if we're in that interval from 0 to 360 degrees, or you could say pi over 6 or 5 pi over 6 in terms of radians. So let me write this over here. So sine of beta equals 1/2. So right now I know beta is equal to, well, let me just do this in solution set notation. We know we have 30 degrees and we have 150 degrees. Okay, so far that's what we got. Let me put this in terms of radians also. So let's go pi over 6 and then 5 pi over 6. So what's going to be the result from over here? Let me draw a little line. We have the sine of beta plus 1 equals 0. Again, we're just going to subtract 1 away from each side. So the sine of beta is equal to -1. And again, if you know your unit circle, this is basically going to give us 270 degrees or 3 pi over 2. So let's get rid of this and let's put 270 degrees. And then over here, let's put 3 pi over 2. Let me just erase this real quick. And let me just drag this out of the way. So we'll put this over here. So let's put or. And then let's come down here. And again, the more you reference the unit circle, the more you work with it, the more you memorize it. Again, we were looking for sine of beta to be equal to 1/2. So that's going to be here. You're looking for your y value, so 30 degrees or pi over 6. And then if I go in quadrant 2 where sine is positive, again, what angle is going to have a reference angle of 30 degrees? 150 degrees. So it's going to be here. Okay, it's 150 degrees or 5 pi over 6. Then if you're looking for a y value of -1, it's going to be at 270 degrees or here, or again, 3 pi over 2 in terms of radians. Okay, so let's talk about the general solution. This might not be obvious, but when you look at these, sometimes they're going to have this pattern. I know when we work with sine or cosine, they repeat every 360 degrees. But if you notice this one, if you started, let's say you went through and you say, okay, well, 30 degrees plus 360 degrees is 390 degrees. Then 150 degrees plus 360 degrees is 510 degrees. And then 270 degrees plus 360 degrees is 630 degrees. So I want you to notice that everything that I have here is just differing by 120 degrees. So if I start here and go here, I added 120 degrees, I added 120 degrees, I added 120 degrees, so on and so forth. For a general solution, in this particular case, I can say 30 degrees, okay, plus I know the period of sine is 360 degrees, but because of this, I can say 120 degrees times n. So 30 degrees plus 120 degrees times n, this would be a simpler way to write this. And then for this guy, if you want to put this in terms of radians, let's go ahead and just say that you have pi over 6. Plus, you're going to do 120 degrees in terms of radians, so that's 2 pi over 3. So 2 pi over 3. And then times n. Okay, so let's close that up. So this would be our general solution, and then this is if we had a domain restriction. So let's say from 0 to 360 degrees. And then here, let's do from 0 to 2 pi. All right, let's look at one that's much more challenging. So here, we're not going to be able to use our fancy unit circle. I think we can on one part, but on the other we can't. So we have tangent squared beta plus tangent of beta minus 2 equals 0. So same deal, I'm going to be able to factor this. And I'm just going to set this up. It's already in line for me the way I want it. So I'm just going to put the tangent of beta and the tangent of beta. So I basically need a +1 and a -2. So how am I going to get that? Well, basically I want to do +2 and -1. So this guy is factored. Pretty easy to do that. Let's go ahead and start with the easier one. So let me start with the tangent of beta minus 1 equals 0. So we'll say the tangent of beta, if I add 1 to each side, would be equal to 1. So where's the tangent of beta equal to 1? You might remember from your special triangles that one solution here would be 45 degrees. Remember, tangent is positive in quadrants 1 and 3. Remember all students take calculus. So it's positive in quadrants 1 and 3. Okay, so I need to find the quadrant 3 solution. So I want the angle in quadrant 3 with a 45-degree reference angle. So I can go ahead and do 180 degrees plus 45 degrees, which is going to give me 225 degrees. So let me put 225 degrees to finish that up, and then I can erase it. So let's put beta is equal to 45 degrees or 225 degrees. In terms of radians, you could write it like this. You could put pi over 4. and then you could do 5 pi over 4. So that takes care of this part. Now over here, this is where we're going to struggle a little bit. So we have the tangent of beta plus 2. We're going to set that equal to 0. So let's go down here and get a lot of room. We'll come back up. So the tangent of beta plus 2 is equal to 0. Let me subtract 2 away from each side of the equation. I get the tangent of beta is equal to -2. So there's nothing you can pull from special triangles or the unit circle where you're going to figure this out. Okay, so what I would do here is go through and basically use your inverse tangent function on your calculator. Okay, go ahead and use this guy. Okay, and I'm going to use +2, not -2. If you punch this up, you're going to get 63 point, and I'm going to round this, let's say 4, 3. So this is in terms of degrees. So now what this is telling me is that the reference angle with wherever I need to go is going to be 63.43 degrees. Now tangent of beta here is negative. Where is tangent negative? It's negative in quadrants 2 and 4. So I'm looking for a solution in quadrants 2 and in quadrants 4. And what I want is the angle with a reference angle of 63.43 degrees. So in quadrant 2, I would do 180 degrees minus 63.43 degrees, which I'll say is 116.57. So let's go ahead and write this as 116.57 degrees. And then in quadrant 4, I would do 360 degrees minus this 63.43 degrees. And that would give me 296. Let me write this down. So 296.57 degrees. So let's erase all of this. We don't need it anymore. And let's just bring this up here. And I'm going to combine all of this for one solution. So let me get this over here. And let me come up here. And I'm basically going to say, and let me kind of drag this over here. So I'm going to do one for degrees and one for radians. So beta could be 45 degrees, 225 degrees. You could have 116.57 degrees. And this is an approximation. So maybe you want to notate that this is approximately here. And then this is an approximation also. So 296.57 degrees. And then in terms of radians, if you wanted to convert this over, again, for each of these, you would multiply by, you have degrees here. So you want degrees down here. And then you want pi up here. So you would basically say that the degrees are going to cancel. So let me just show that real quick. 116.57 divided by 180. And then I'm just going to multiply it by pi. And I'm just going to round this off and say it's about 2.034. So let me slide this down. And I'll just say it's about 2.034. So let's get rid of this one. And let's do this one. So let's move this up. And basically we're going to multiply it by, again, you want pi over 180 degrees. We know that the degrees here are going to cancel. And basically I'm doing the same thing on my calculator. 296.57 divided by 180, then times pi. So let's just go ahead and say this is going to be 5.176. So 5.176. And again, you just want to show some way like, hey, this is an approximation. So I'll just put approximately like this, just showing that this is not an exact value. Now remember, if you're working with tangent, the period is 180 degrees or it's pi radians. Okay, so this would be for, in the case of from 0 to 360 in terms of degrees, and I made that terribly. Okay, so 360 degrees. And then this would be basically from 0, let me put my degree symbol there, 0 to 2 pi. And then for the general solution, I'm going to take 45 degrees. So let's go ahead and say 45 degrees. Plus, I'm going to do 180 degrees times n. And then I have another guy here, so I'm going to do 116.57 degrees plus 180 degrees times n. So again, this is an approximation. This is an approximation. It is not an exact value. Depending on your teacher, you might have to show that in some way. So that's why I put this here and this here and this here and this here. That's just my way of notating. This isn't standard. This is my way of notating that, hey, this is an approximation. It's not an exact value. So then down here, for this guy, I would start with pi over 4 and then plus the pi times n. And then for this one, I would take my 2.034 and then plus my pi n, okay, like this. Now again, if you want to just notate that this is an approximation and this is an approximation, just to let your teacher fully know that you're aware that this is an approximation and not an exact value. All right, let's take a look at one more problem. So somewhere in your textbook, they're going to tell you that you don't want to divide both sides of an equation by a trigonometric function, such as the cosine of beta. So when you do this, you could potentially remove some of your solutions. These are going to be solutions that make the divisor 0. So what I'm going to do is solve this in two different ways, and I'll show you how this can cause problems. So the first way is the correct way, and that's with factoring. So if you have the cosine of beta times the cotangent of beta, and this equals the cosine of beta, you could subtract the cosine of beta away from each side of the equation. So over here, this would cancel, and you'll have 0. So on the left, you would have the cosine of beta, then times the cotangent of beta, and then minus this cosine of beta. And what I'm going to do, because we're going to factor this out, let me put times 1 so nobody gets lost. And I'm going to set this equal to 0. Let me actually get rid of this because we're going to come back up and use that in a moment. So let me slide down here just a little bit. And I'm just going to factor out the cosine of beta. So this right here is going to get pulled out in front of some parentheses. So you have the cosine of beta times the quantity. Inside, you would have the cotangent of beta. And then minus, if you pull this out, you would have your 1, and then close that down, and this equals 0. So we're now going to solve this using the zero product property, or you can call it the zero factor property. So for that, I'm going to take the cosine of beta and set that equal to 0. Then I'll say or. I'm going to take this other factor, so the cotangent of beta, minus 1, and set that equal to 0. Well, for this one, you could add 1 to both sides. So the cotangent of beta would be equal to 1. And we know that the tangent of beta is equal to 1 over the cotangent of beta. So the tangent of beta here would be 1 over 1, which is 1. So let me write this as the tangent of beta equals 1. So the first one is the cosine of beta equals 0. So I'm looking on the unit circle for an x-coordinate of 0. So that's going to occur right there at pi over 2, or 90 degrees. And then right there at 3 pi over 2, or 270 degrees. Now for the tangent of beta equals 1, we've seen this several times already. We know that in the first quadrant, this is going to be pi over 4. Again, if you skip the other problems, you could just do the inverse tangent function with 1 as the argument. You'll get pi over 4, or 45 degrees. You could also think about this with the definition of tangent. So you could say that the tangent of beta is equal to the sine of beta over the cosine of beta. And in this case, if you replace beta with that angle, which is pi over 4, you can go to the unit circle and actually see why we're getting a value of 1. And that's because we have the same non-zero number divided by itself. The sine value is square root of 2 over 2. The cosine value is square root of 2 over 2. So square root of 2 over 2 divided by square root of 2 over 2 will give you 1. And then the period for tangent is pi. So if I add pi radians, or 180 degrees, that's going to give me my solution that's in quadrant 3. So that's going to be at 5 pi over 4. And the tangent of 5 pi over 4, again, you would have the same non-zero number divided by itself. And so you would get 1. So let me get rid of this. And let me highlight this over here as 5 pi over 4, or 225 degrees. And I'll get rid of this and this and this. So if you wanted to write out your solution, you could say that beta is equal to, let's start with pi over 4, and then let's go to pi over 2, and then let's go to 5 pi over 4, and then let's go to 3 pi over 2. If you want to work with degrees, we could say that this is 45 degrees, this is 90 degrees, this is 225 degrees, and then lastly 270 degrees. Okay, let me grab this real quick, and let me come back up here and paste this in here. And I'm just going to show you real quick that these solutions all work, just so that when we get to the next part, you're not lost in terms of whether we did it correctly or not. So the first solution was pi over 4. So let's plug that in there, and there, and there. And let me make that a little bit better there. Let me slide this out of the way so we can fit this. We know that the cotangent of pi over 4 is 1, and the cosine of pi over 4 is square root of 2 over 2. So this would be the square root of 2 over 2 times 1 is equal to the square root of 2 over 2. So that is a valid solution. Now, similarly, if you do 5 pi over 4, the only thing that's going to change is the cosine of 5 pi over 4, that's going to be a negative square root of 2 over 2. So if I did 5 pi over 4, 5 pi over 4, and 5 pi over 4, this would be negative square root of 2 over 2 times 1 equals negative square root of 2 over 2. So that one's going to work as well, because you get the negative of the square root of 2 over 2 equals the negative of the square root of 2 over 2. Now, the other ones are going to make the cosine of beta equal to 0. So whether you did pi over 2 or 3 pi over 2, when you plug that in, let me just do pi over 2, you're going to get 0 equals 0. And let me make that a little bit better there. So cosine of pi over 2 is 0. Cotangent of pi over 2 is actually also 0. So you would get 0 is equal to, over here, cosine of pi over 2 is 0. So this one would work, and so would this one. It's the same thing. So you can see these solutions work in our interval. So from 0 and including 0 going out to 2 pi is excluded. And then for this one, you would have from 0 degrees where that's included, going out to 360 degrees where that's excluded. Okay, let me get rid of this. And let me show you what can happen if you solve this in a different way. So let's say instead of factoring, I decided I was going to divide both sides of the equation by the cosine of beta. So let's divide this side by cosine of beta, and let's divide this side by cosine of beta. And you're going to see a problem happen. So this would cancel with this, and you'd have the cotangent of beta is equal to, well, this would cancel with this, and I have a 1. So it equals 1. Okay, well, we know this turns into the tangent of beta equals 1, and we know we get this solution right here of pi over 4, and we get this solution right here, which is 5 pi over 4. But what happened to these solutions right here of pi over 2 and 3 pi over 2? Well, those are the solutions that make this divisor 0. Cosine of pi over 2 is 0. Cosine of 3 pi over 2 is 0. So that's what's going on. You're going to potentially remove solutions if you use this strategy. So what we want to do is stick to factoring when we try to solve this type of problem, because you're not going to run into these types of issues. So I just want to note real quick, for those of you that are interested, you can look at this problem on Desmos. What you would want to do is go back to the fact that you have the cosine of beta, I'm just going to call it the cosine of x, times the cotangent of x is equal to the cosine of x. Now, what you're going to end up doing is graphing this guy on the left and this guy on the right separately. So the graph in red is y equals the cosine of x times the cotangent of x, and the graph in green is y equals the cosine of x. So if you want to solve it this way, you're looking for the points of intersection between those two graphs. So you're basically asking the question, for which x values are the y values going to be the same? Those are going to satisfy the equation. So the ones we found pi over 4, we found pi over 2, we found 5 pi over 4, and then we found 3 pi over 2. So you can continue with that if you want. This is something you can look at on Desmos on your own if you want a visual representation of what's going on. In this lesson, we want to talk about solving trigonometric equations using square roots, squaring, and identities. All right, so let's go ahead and start off with 4 times sine squared beta minus 1 equals 0. So just like we've been doing before, we're going to add 1 to both sides of the equation. We're going to have 4 times sine squared beta is equal to 1, okay? So what I want to do now, remember, you're always trying to isolate your trigonometric expression. So I want sine of beta by itself. So what I'm going to do here is just divide both sides by 4, okay? And so that's going to give me the sine squared beta is equal to 1/4, okay? Let me scroll down just a little bit and get some room. So now, because this guy is squared, I want to take the square root of each side. Remember how this works. If I take the square root of the left, on the right, I want to go plus or minus, right, to account for the positive or the negative. So I'm going to say that the sine of beta is equal to plus or minus the square root of 1/4, okay? If you simplify this, you'll say the sine of beta is equal to, you'll go plus or minus, the square root of 1 is 1, and the square root of 4 is 2. So you can basically say this is 1/2, okay? So let me actually erase all of this, and let's come up to the top and just paste this back in here. So we know this gives us 2 scenarios, right? So I want to split this up and say the sine of beta is equal to 1/2, or the sine of beta is equal to the negative of 1/2. So let me erase this now, okay? So we have our 2 guys there. So basically what I'd want to do is go to my unit circle. I know at this point a lot of you already have it memorized, but some don't. So let's go down and let's look for where the sine of beta is equal to 1/2, and then also where the sine of beta is equal to negative 1/2. So basically you're looking for your y coordinate to be 1/2 or negative 1/2. So that's going to happen here, okay? That's also going to happen as we go around. It's going to happen here. As we go around, it's going to happen here. And then as we go around, it's also going to happen here, okay? So notice everywhere where I circled has a 30-degree reference angle, right? So basically it's going to be, if you want to put this in terms of radians or degrees, we'll just do both. So 30 degrees, then you have 150 degrees. You also have your 210 degrees. And then you have your 330 degrees. Okay, so that's in terms of degrees. And then in terms of radians, you would have your pi over 6. Okay, you would have your 5 pi over 6. You would have your 7 pi over 6. And then lastly, you would have your 11 pi, okay, over 6. So these would be your solutions if you said between 0 and 360 degrees, or also if you said between 0 and 2 pi in terms of radians. So let's just cut this away. I'm just going to cut this, come back up here and paste this in, okay? So these are going to be, again, our solutions. Let me just erase this nonsense here. These are going to be our solutions for basically if you restricted this over an interval. Again, you have from 0 degrees to 360 degrees. That's this guy right here. And then this guy right here would be from 0 to 2 pi, okay? So sometimes they ask you this question to solve over a specific interval. And then other times they'll say, hey, what's the general solution? So if we want the general solution, let's just put this right here really quickly. Remember, when you work with sine, the period is going to be 360 degrees. But what you notice here is that as you jump here from 30 degrees to 210 degrees, you're increasing by 180 degrees, okay? So I would start this by saying I have 30 degrees plus 180 degrees times some integer n. And then you'd have 150 degrees, so 150 degrees plus this 180 degrees, okay, times n, because again, if you look at 150 degrees and 330 degrees, those are different by 180 degrees, okay? And what's causing this, if we go back to the unit circle, if I circle this one again, you'll notice that these guys are across from each other. This is 180 degrees, right? So basically, these are across from each other and these are across from each other, okay? So you can basically say that you start with 30 degrees and you add 180 degrees to get your next solution. Then you add 180 degrees again, you get to the next solution, so on and so forth. If you started with 150 degrees, you add 180 degrees to get your next solution, then 180 degrees again, so on and so forth. Okay. If you wanted to put this again in terms of radians, we're going to use the same concept. Here I'm going to go pi over 6, so basically your 30 degrees. Then plus 180 degrees in terms of radians is going to be pi, okay? So you're just going to do pi times n. And then for 150 degrees, this is going to be 5 pi over 6, so 5 pi over 6. And then I'm just going to go plus my pi times n. Okay, so here's all the solutions that you could possibly want. You have your degrees across that interval from 0 degrees to 360 degrees, and then you have your radians across that interval from 0 to 2 pi, and then you have your general solutions. So they're just basically, if they didn't ask you to solve over an interval, this is how you'd want to list this for degrees and then for radians. All right, let's take a look at another example. So here's one where we're going to need to use some identities. So we have the negative of cosine squared beta minus 2 times sine of beta is equal to negative 2. So notice that you have sine here and then also cosine here, and cosine specifically is squared, okay? So what you're meant to think about, if we go back to our worksheet or our little handout on the identities, if you go to the Pythagorean identities, remember cosine squared theta is the same as 1 minus sine squared theta, okay? So you want to look for possibilities there where you can substitute things in. So remember the negative here. This is a big deal. If you have a negative there, you're putting a negative. Put this in parentheses, what I'm going to do, because the negative's got to get distributed to everything. So I'm going to go 1 minus my sine squared beta. Okay, again, that's in parentheses. Then minus your 2 times your sine of beta is equal to negative 2. Okay, distribute the negative to everything. So I'll say negative 1 and then plus sine squared beta. Then minus 2 times sine of beta is equal to negative 2. Okay, so from here, we already know what to do. We want to end up with sine of beta equals some number, and then we want to solve, right? So I'm going to tell you in advance this is factorable. If you have something that is quadratic in form, if it's not factorable, you can use the quadratic formula, okay? But here we're going to be able to factor. So what I'm going to do is I'm going to add 2 to both sides of the equation, and I'm just going to rearrange things. I want the squared term all the way to the left, so I'm just going to say that I have sine squared beta, and then this is gone. I'm going to put 0 here. Okay, over here, I'm going to put minus 2 times the sine of beta, and then if I have negative 1 plus 2, that's positive 1. Okay, so this equals 0. And the idea here is that I can factor the left side. Okay, so I can factor this. Again, if it's a roadblock for you when you're trying to factor these guys, go ahead and take something like u, okay, and say sine of beta equals u. And then it's just like if you were trying to factor u squared minus 2u plus 1. Okay, if that was equal to 0, you could solve that in a breeze, right? It's just a roadblock because we're now dealing with trigonometry. So how could we factor this guy right here? And again, if it's troubling you, just look at this one. Well, first off, if I had sine squared beta, and there's nothing out here, there's basically a 1, well, I'm going to have the sine of beta times the sine of beta. Okay, so that's my first term in each case. Now, for this part right here, again, you're just looking at the -2 and the +1. Okay, so I need two numbers that are going to multiply together to give me +1, but sum to -2. Well, that's going to be -1 and -1. Okay, so let's go ahead and get rid of this. And basically, we could write this, okay, as the sine of beta minus 1 quantity squared. Okay, so this equals 0. And the reason I write it like this is you can write it like this or this. Remember, this is basically from special factoring. When you think about this, it's really only going to be one of these guys that we have to set equal to 0, right? Because you have a duplicate solution. So basically, all I want to do here is just, again, take one of these and say sine of beta minus 1 is equal to 0. I'm going to go ahead and add 1 to both sides and just say the sine of beta is equal to 1. Okay, now this is going to be really easy to solve for us. Where does the sine of beta equal 1? Well, if we're looking for the sine of beta equals 1, well, again, where's the y-coordinate 1? Well, right here, right? So at 90 degrees or pi over 2 in terms of radians. And that's basically the only place there. So your general solution would just be you rotating around another 360 degrees before you get there, okay? So let me go back up. So let's just put our solution here. So again, if we're in the interval, if they give you degrees, you want to answer in degrees. So if they say over the interval, you have 0 degrees and then to 360 degrees. Again, if you get this, then your answer should be in degrees and you'd want to put 90 degrees here, okay? If you got an answer or if you got a test question where, let's say it was with radians, so let's say they said 0 to 2 pi like this, okay? Then now you want to give your answer in radians. So you could say beta is equal to pi over 2, or you could do the solution set notation. Just ask your teacher what they want, okay? So I'm just going to do this, so pi over 2, okay? So that's my solution basically in these intervals. Now, again, a general solution is where we keep thinking about when we just keep rotating around and around and around. So basically your general solution, if it's in terms of degrees, well, it would be 90 degrees plus another full rotation is 360 degrees times some integer n, okay? And then for the radians, you just use this pi over 2, and then plus, again, one full rotation in terms of radians is 2 pi, so you would do 2 pi and then times some integer n, okay? So this is your general solution here. Sometimes they ask for that. And then these are your solutions if you have a specified interval. Sometimes they ask for that. Okay, so let's look at a very, I would say challenging, but a very tedious type of problem now. This one involves squaring, and you'll recall from basic algebra, if you square both sides of an equation, you lose information. And so you have to basically check your solutions in the original equation, right? You sometimes get these extraneous solutions, and so they're not going to work as solutions to the original equation, okay? So we're going to see that here, and we're going to see that it just takes a long time to go through everything. So we have the negative of cosine theta is equal to the square root of 3 times the sine of theta. Okay, so the first thing I'm going to do is square both sides, okay, because I want to get rid of this radical, and also I have cosine and sine, so I'm thinking Pythagorean identity, okay? So I'm going to square both sides. So let me write this as the negative of cosine of theta, okay? This is going to be squared. This equals the square root of 3 times the sine of theta. This is going to be squared, okay? So the negative is going to go away. Negative squared is just going to be a positive, right? -1 times -1 is +1. Then cosine of theta squared, we could just say this is cosine squared theta like this. Over here, the square root of 3 being squared is 3. Sine of theta being squared is just sine squared theta, okay? So at this point, we know that cosine squared theta is 1 minus sine squared theta, okay? So let's just go ahead and make that substitution. I'll say this is 1 minus sine squared theta is equal to 3 times sine squared theta, okay? So let's scroll down and get some room going. All right, and I'm just going to subtract 3 times sine squared theta from both sides of the equation, and this is going to cancel, and I'm just going to put 0 here. So I'm going to have 1 minus, remember, you can treat this as a -1. So -1 minus 3 or -1 plus -3, however you want to think about this. This is going to be -4. Okay, so basically -4 times sine squared theta is equal to 0. Okay, so how are we going to solve this? I want you to think back again to basic algebra. Okay, this is where your skills really come into play. Let's say it's something like a squared minus b squared. How would you factor this? Remember, this is the difference of squares. So it's a plus b, okay, that quantity times a minus b, that quantity. Well, here you have the difference of squares, right? I could write this out and say that this is 1 squared minus, you could do 2 times the sine of theta, okay, quantity squared like this, and this equals 0, okay? So now it's apparent, or it's very clear, that this is the difference of squares. Sometimes you have to rewrite things like that. So this would be 1 plus 2 times the sine of theta times 1 minus 2 times the sine of theta, okay? And we'll set this equal to 0. So basically, I'm going to take each one of these guys and set it equal to 0. So I would have 1 plus 2 times the sine of theta is equal to 0. Or you'd have 1 minus 2 times the sine of theta is equal to 0. Let's go ahead and solve. They're very easy to solve. I subtract away 1 from each side over here, and over here, and over here. And this is going to cancel, and this is going to cancel, okay? So over here I have 2 times the sine of theta is equal to negative 1. Over here I have, and let me put the or, I have negative 2 times the sine of theta is equal to negative 1, okay? So basically at this point, I'm just going to divide this by 2, okay, and this by 2, and then this by 2, or this is negative 2 over here, and this by negative 2. Okay, so this cancels, and I have sine of theta is equal to the negative 1/2. Then or over here, this is going to cancel, right? And you have negative divided by negative, so that's positive. So you get the sine of theta is equal to 1/2, right? So you can condense this down and say, basically, you have plus or minus 1/2. Okay, so let's get rid of this. And let's just copy this real quick. Let's go to a fresh sheet. So we have a lot of room to work, because the problem here is you're going to get all these solutions, okay? So if the sine of theta is 1/2, or it's negative 1/2, remember, we already went through this. So let me write this again. So sine of theta is 1/2, or sine of theta is negative 1/2. Basically, you would have a 30-degree reference angle in each case, right? So you would have here, and then basically you go around, you'd have here, and then you go around and you would have right here, and then you go around and you would have right here, okay? So we already know this because we saw a problem with this earlier, but basically 30 degrees, 150 degrees, 210 degrees, and 330 degrees, okay? So let me write this down. So we have our 30 degrees, we have our 150 degrees, we have our 210 degrees, and then we have our 330 degrees, okay? And I'll write it in radians when we finish up. So let me just keep this in degrees for now. Let me cut this away, and let me just paste this in right here, okay? Let me get rid of all this nonsense. Now, when we square both sides of an equation, the solutions here that we get are proposed solutions. So we have to get our original equation going so we can check it. So negative cosine of theta, okay, is equal to the square root of 3 times the sine of theta. Okay, so we're just going to use degrees. You can use radians, it doesn't matter. You're going to plug in for theta, okay? So basically, if I plugged in 30 degrees here and 30 degrees here, what would we get? Well, again, I could go back and forth between the unit circle, but a lot of you already know that the sine of 30 degrees is 1/2, okay? So this is going to be 1/2. So this would give me the square root of 3 over 2. So let's just write that as the square root of 3 over 2. Okay, over here, I'd have the negative of cosine of 30 degrees. Well, the cosine of 30 degrees, you know, is a positive number, right? Because 30 degrees is in quadrant 1. All of these guys are going to be positive in quadrant 1, right? So there's no way this can be true because this is the negative of a positive number, okay? So you can go ahead and mark this out. The actual answer here is square root of 3 over 2, right? But it's the negative of that. So it's the negative of the square root of 3 over 2 is equal to the square root of 3 over 2, so that's false, right? So that solution does not work. Okay, for the next one, let me erase this and set this back up. So we had the cosine, or the negative of the cosine of theta, is equal to, we had the square root of 3 times the sine of theta. So we know that the sine of, if I put in 150 degrees here, we know the sine of 150 degrees is basically 1/2, right? Because the sine of 30 degrees is 1/2. The sine of 150 degrees, because sine is positive in quadrant 2, 150 degrees has a 30-degree reference angle, so this is 1/2 as well, right? So this is basically going to be the square root of 3 over 2, okay? Over here, if you think about the cosine of 150 degrees, remember cosine is negative in quadrant 2. Okay, so this will save you a little bit of work. You'd have the negative of a negative, which is positive, so you know this is probably going to work, right? So the cosine of 150 degrees, we know that this guy is going to be the negative of the square root of 3 over 2. Okay, but you have the negative of the negative, so be really careful. So the negative of the square root of 3 over 2. So if I apply the negative, I basically would have the square root of 3 over 2 is equal to the square root of 3 over 2, okay? So this one checks out. So 150 degrees is a valid solution. Then for 210 degrees, let's go ahead and set this back up. And I probably shouldn't erase this each time, but it's the negative of the cosine of theta is equal to the square root of 3 times the sine of theta. So 210 degrees, if you put this in here, okay, and you put this in here, again, we know that the reference angle is 30 degrees, right? So what is the sine of 30 degrees? Well, it's going to be 1/2, but we're in quadrant 3 now, so we know this is negative. So basically this is negative 1/2. So this would be the square root of 3 times negative 1/2, so square root of 3 over 2, and this is negative, okay? So over here, 210, again, this many degrees, I know that I have a reference angle of 30 degrees, so the cosine of 30 degrees is square root of 3 over 2, and because this guy is in quadrant 3, cosine is negative, so this is the negative of the square root of 3 over 2, so this isn't going to work out, right? Because again, if I apply the negative, this becomes positive, so again, we have one that doesn't work. So this one doesn't work. And then for 330 degrees, let me just do this one last one. So the negative of cosine of, let's just go ahead and say 330 degrees, is equal to, you have the square root of 3 times your sine of 330 degrees. Again, I've got a 30 degree reference angle, and I'm in quadrant 4. So I know this is negative 1/2, right? So you might as well just put negative square root of 3 over 2, okay, like this, and I'll just put this out here. Okay, so over here, again, I have a 30 degree reference angle, but cosine is positive, okay, in quadrant 4. So I would say square root of 3 over 2. So square root of 3 over 2, but it's the negative of that because I've got this negative hanging out. So these guys are equal, so this one does work out, okay? So your two valid solutions here are 150 degrees or 330 degrees, okay, in terms of degrees. And then if you're working with radians, it's 5 pi over 6 or then 11 pi over 6. So let's go ahead and write our solution here. We'll say from the interval, if you're in this interval 0 degrees and then 360 degrees, we'll say the solution set is basically 150 degrees, okay, and then 330 degrees only, okay, so just those two guys. And then if I'm in this interval from 0 to 2 pi, okay, if they give it to you like this, always answer based on what they give you as the interval, okay? If they don't give you anything, then you can just ask your teacher like, hey, what do you want this in? So basically, at this point, I want to do my radians, so I'll go ahead and say that this is 5 pi over 6, and then 11 pi over 6. Let me close that down. And then again, if you want a general solution, you want to realize here that you can just add 180 degrees each time. Again, I know the period for sine is 360 degrees, but you have to pay attention to this type of stuff if you're writing a general solution. So the general solution here would be, let's go ahead and say 150 degrees plus 180 degrees times n. Okay, so you don't want to do 360 degrees there because, again, if I add 180 degrees, I get to 330 degrees. Then if I add 180 degrees to that, I'm going to be at 150 degrees plus 360 degrees, which is 510 degrees, so on and so forth, okay? And then in terms of radians, I'm going to go ahead and say that it's 5 pi over 6 plus 180 degrees is going to be pi radians and then times n. Okay, so these are your general solutions, and then these are your solutions if you're given a specific interval to solve over. Just get with your teacher in terms of what you need to do. In this lesson, we want to talk about solving trigonometric equations with half angles. All right, so let's start off with a very easy example. So we have the sine of beta over 2 is equal to the square root of 2 minus the sine of beta over 2. We have a little domain restriction, or you could say you're solving over an interval. In this case, it's from 0 to 2 pi, with 0 being included. Okay, now I want to make something perfectly clear. You are solving for beta, okay? So you want to plug something in here for beta, so basically here and here, and you want the result of this to be true, okay? You are not, in the end, solving for beta over 2, but we need to use beta over 2 in order to get a solution, okay? So what we're going to have to do, and let me write this down here, I'll show you, we need to basically change this up just a little bit, and I'll explain why. So let me rewrite this real fast. I'm going to say that I have the sine of beta over 2 is equal to the square root of 2 minus the sine of beta over 2, okay? So the first thing I'd want to do is get that trigonometric expression by itself. And in order to do that, I'm just going to add the sine of beta over 2 to both sides of the equation, okay? So that's how I'm going to get things started. So let me scroll down just a little bit here, get some room going. And I'm just going to show this cancels over here. So sine of beta over 2 plus sine of beta over 2 is 2 times the sine of beta over 2. And this equals now the square root of 2, okay? If I want to isolate this completely, I'm multiplying this by 2, okay? So I can just divide both sides by 2, and then I'll take care of that. So I'll divide this side by 2 and this side by 2. And basically, this is going to cancel with this, okay? So that's gone. And I've isolated the sine, and let me make that a little bit better. So it's the sine of beta over 2. So that's on my left side. On the right side, I have the square root of 2 over 2, okay? So let's pause for a minute. I'm actually going to erase all this. And let's think about what we have. We have this right here, which is beta over 2, and we have the sine of that guy, and we're saying that it's equal to the square root of 2 over 2. So before we start thinking about how we're going to solve this, let's first modify our little domain to work with what we're working with here. We're working with beta over 2. So I'm going to write this as an inequality. I'm going to say that 0 is less than or equal to. I'm going to do this beta guy here, which is less than 2 pi, okay? Because that's what we're initially working with. Again, this is for beta. So now we have beta over 2, so we divide everything by 2 here, okay, to consider the interval here. So this is just going to be 0, this will be beta over 2, and this is just going to be pi, okay? So essentially what I'm looking for here is I'm looking for where beta over 2, sine of that guy, would be square root of 2 over 2. Now, in this particular case, if you think about square root of 2 over 2 in terms of sine, if you go to your unit circle, you can see in quadrant 1, you have square root of 2 over 2 here with pi over 4 in terms of radians, or 45 degrees with degrees. And then you would want a 45-degree reference angle in quadrant 2, okay? So in terms of degrees, that's going to be 135 degrees, or 3 pi over 4 in terms of radians, right? So right here, okay? And you can see this right here. Okay, so that's pretty obvious, and you can see that that falls in line with our interval for beta over 2 because it's from 0 to pi, okay? So we're going to take pi over 4 and 3 pi over 4. So I'm going to say that the sine of pi over 4 is equal to the square root of 2 over 2, and also that the sine of 3 pi over 4, okay, is equal to the square root of 2 over 2. Okay, so what I want to think about here, now that I have everything set up, remember, you can set these guys equal to each other because I know that the sine of pi over 4 is equal to the square root of 2 over 2. And I know that beta over 2, sine of that guy, is equal to the square root of 2 over 2. So what I can do here is set up a little equation so that I can solve for beta, right? So let me do this over here. I'm going to say that beta over 2 is going to be equal to pi over 4. Because again, sine of this guy produces this, and sine of this guy produces this. So I can set these two equal to each other in order to get a solution for beta. Okay, so that's why that's going on. Okay, so let's scroll down just a little bit to get some room. I'm going to put or here. I'm going to do the same thing with this. So beta over 2 is equal to the 3 pi over 4. Okay, and all I need to do here, it's very simple to get a solution. I'm just going to end up multiplying both sides by 2. Okay, so this is basically going to be what? This is going to cancel. I'll have beta is equal to, the 2 would cancel the 4 and give me a 2 down here, so pi over 2. And then over here, basically I'm multiplying both sides by 2. And so this is going to cancel, and this is going to cancel, give me 2 here. So we'll say, or beta is equal to my 3 pi over 2. Okay. So these are our two solutions in terms of radians, and they're within our domain or our restrictions. So I'm going to do this in solution set notation. So I'm just going to put pi over 2 and then comma 3 pi over 2. Okay. So we're not asked for the general solution here, so we don't need to worry about that. If you were asked for the general solution, remember your period here is different because you're dividing by 2. So basically the period here is 4 pi, okay, not 2 pi. Okay, so you got to remember that. All right, so one thing I want you to do is pause the video, go ahead and plug pi over 2 in for beta in each case, and verify that basically these solutions do work. You can just do one of them. I'm going to just say, trust me that they both work, but just pause the video and see that for yourself, that if you plug in pi over 2 right here, okay, so you have pi over 2 divided by 2, and right here, pi over 2 divided by 2, that basically you would get a true statement. The left side would be equal to the right side. Okay. Let's take a look at another example. So this one is slightly more complex. Not more complex, but more tedious because you do need to use an identity, and then there's some squaring involved. So we have the negative cosine of theta is equal to negative 2 plus 3 times the sine of theta over 2. Again, when you think about these things, if you end up with cosine and then sine, you're going to be thinking about an identity, right? So if I think about sine of theta over 2, if I go back to my handout on the identities, and we come down here, let's go all the way down to where we get to the half angle identities, and it was the last one we talked about. So here's the one for sine. So you have sine of a over 2. In our case, we're working with theta. So let's say sine of theta over 2 is equal to plus or minus your square root of 1 minus the cosine of theta over 2. Okay, so let's go back and let's just make a little replacement. Okay, so I'm going to put the negative of cosine of theta is equal to, I'm going to have negative 2. And then I'm going to have plus, you've got your 3 here that's multiplying this. So keep in mind that basically you have that plus or minus. I'm going to put this in front. So I'm going to do plus or minus like this, and then the 3, and then times that little guy, which was the square root of 1 minus the cosine of theta, and this was over 2, okay? So all I did was I plugged in for sine of theta over 2, just using the half angle identity, okay? That's all I did. Now, what I want to do here, remember, if you have a radical somewhere, you're going to end up having to square, okay? And in order to do that, you first want to isolate this guy, okay? So what I would do here is I would first add 2 to both sides, okay? And let's scroll down just a little bit. So I'm just going to say that I have 2 minus the cosine of theta is equal to, this is canceled over here, so I have plus or minus 3 times the square root of 1 minus cosine of theta over 2. Now I can square both sides, okay? So I can get rid of this radical. So I'm going to square this side, and I'm going to square this side, okay? When you square the plus or minus, you don't have to worry about it because basically you can think about this as negative 1 being squared, that's going to be positive 1, and a positive, you square it, it's still positive, okay? So you can basically forget about that. So over here, I'm going to use my special product formula and say it's the first one squared, so 2 squared is 4. And then minus, it's 2 times the first guy times the second guy. So 2 times 2 is 4. And then times cosine of theta, and then plus the last guy squared, so this is just cosine squared theta, okay? And we'll rearrange this in a moment. I know this is not how we usually write this. We'll put equals. Again, don't worry about the plus or minus, that's gone. 3 squared is going to be 9, and then it's multiplied by this guy right here squared. I'm just removing the radical, okay? So basically you have this 1 minus the cosine of theta over 2. Now be careful here because 9 is multiplying this whole thing, okay? If you end up distributing this to the numerator, make sure you use parentheses, okay? Very important. What I'm going to do first is rearrange things. So I'm going to put this as cosine squared theta, okay? Then minus 4 times cosine of theta, and then basically plus 4, okay? So I've got all my signs right. I want to make sure on that. And then this equals, let's do 9 times 1 minus cosine of theta like this, okay? Because the 9 is multiplying the 1 and also the negative cosine of theta. Then this is over 2, okay? So now what I'm going to do is I'm going to multiply both sides by 2 so that I can clear this denominator, okay? So basically this comes here and cancels here. And here I'm just going to put a 2, okay, being multiplied by everything there. So you'd have 2 times the cosine squared theta. And then I would basically have minus 8 times the cosine of theta. And then plus I would have 8. And this equals, the 2's canceled. So just let's go ahead and distribute this. So 9 minus 9 times the cosine of theta. Okay. So far, so good. Let's scroll down just a little bit more. Okay. So what I want to do here is basically subtract 9 away from each side of the equation and also add 9 times the cosine of theta to each side of the equation, okay? So basically what this is going to do is give me a 0 on the right, okay? You can see where I'm going with this. I'm going to end up factoring and using the zero product property. So on the left, I have my 2 times the cosine squared theta, and then basically I have negative 8 cosine of theta plus 9 cosine of theta. So this is going to be plus cosine of theta, or you could say plus 1 times the cosine of theta, whatever you want to do there. And then basically 8 minus 9 is negative 1, and this equals 0, okay? So the idea here is that, of course, if you wanted to, you could use the quadratic formula, but we have something that is factorable. So let me go ahead and cut this away, put that in there. So I'm just going to factor the left side here. Again, if you have trouble factoring this, I see a lot of students having trouble, write it as 2u squared plus u minus 1 equals 0. You can factor that no problem, right? You think about this as 2u and u, and then the last guy here is a negative 1, right? So that tells me I need mixed signs here. This guy is going to be positive. So what I want to do is put a plus 1 here and a minus 1 here, right? Because the outer would be 2u and the inner would be minus u, so that would give me the correct plus u there, okay? Now, once you've factored it like this, you can just put your cosine of theta in for u, okay? So let's come back in here, replace this with cosine of theta, and your roadblock is gone. Okay, so 2 times cosine of theta there. Okay, so a little trick for you. Now, I'm going to set each one of these equal to 0 and solve. Let me just get rid of this. We don't need this anymore. So I'll say 2 times the cosine of theta minus 1 equals 0. Or I'll say the cosine of theta plus 1 equals 0. Let me scroll down and get a little room going here. So basically, I'm going to add 1 to both sides. And this is going to give me 2 times the cosine of theta is equal to 1. Okay, I'm going to now divide both sides by 2. And I get cosine of theta is equal to 1/2, okay? Over here, let me go ahead and put or, and I'll put or. And then over here, I'm just going to say minus 1 minus 1. So the cosine of theta is equal to negative 1. And I guess I don't really need another one there, so let's put this over here. Well, I guess I could write it down here. So cosine of theta equals negative 1. Okay, so you see what we're doing here. We basically have to solve this guy and then this guy. So where's cosine going to be equal to 1/2? Remember, cosine is positive in quadrants 1 and 4. And we know that cosine of 60 degrees, okay, is a half. So basically, you would want a 60-degree reference angle in quadrant 4, so that would be 300 degrees, right? So you'd want 60 degrees and then 300 degrees. Again, if you're still looking at your unit circle, it's no big deal, right? This is a half here, so you see it's 60 degrees or pi over 3 in terms of radians. And then over here, you'd be in quadrant 4, so you have a half here, 300 degrees or 5 pi over 3 in terms of radians, okay? So again, if you need to use the unit circle, keep doing it. You will memorize it eventually. Now, while we're down here, I might as well note that basically pi, okay, cosine of pi is going to give you -1. So let's go back up, and let me erase the degrees, and let me say that theta here would be equal to your pi over 3, and then it would be 5 pi over 3, and then it would also be pi, right? So this covers these solutions from these guys. Now, in order to make the video a little bit shorter, a little bit more concise, I'm not going to check these solutions. When you square both sides of an equation, we know from basic algebra that there's the possibility of extraneous solutions, right? Solutions that won't work in the original equation. I have already checked this. I know that these guys are going to work. I can say that the solution set here is pi over 3, okay? And then I'll say pi, and then I'll say 5 pi over 3 like this, okay? So these solutions do work in the original equation. In the next example, we'll see where it doesn't, okay? So let's go to that now. All right, let's look at another example here. So we have the square root of 3 times the cosine of theta over 2 is equal to 1 plus the cosine of theta, okay? Again, same interval from 0 to 2 pi, 0 is included. Again, if you see something like this, you have cosine of this and cosine of this, well, you can go ahead and use your identity. So we come back here. Now, cosine of, in this case, would be theta, theta over 2, is plus or minus the square root of 1 plus the cosine of theta over 2. So let's just make a little substitution here. I'll say the square root of 3, okay, and I'll put the plus or minus out in front of here, then times my square root of 1, in this case, it's plus the cosine of theta. Remember, if it's sine, then it's minus. If it's cosine, it's plus. And then this is over 2. And this equals your 1 plus your cosine of theta, okay? So again, all I need to do here is just square both sides. So let's square this side, and let's square this side, okay? And over here, the plus and minus, forget about it, it's gone. Square root of 3 squared is 3. This guy, if I square it, I'm basically going to end up with the radicand. So this is 1 plus the cosine of theta over 2. And to speed this up, let me just wrap this in parentheses and put this like this. And let's put equals over here. I'm going to flip these. I'm just going to put the cosine of theta plus 1, so it makes it easier. So cosine of theta plus 1 like this. So this would be the cosine squared theta, first guy squared, plus 2 times the first guy times the second guy. So it's basically just 2 times cosine of theta, and then plus the last guy squared, so that would be 1, okay? So over here now, all we need to do is basically multiply everything by 2, right? So this would cancel. Let me show this visibly. And let's go over here and do this. So now I have 3 times 1, which is 3, plus 3 times the cosine of theta. And this equals 2 times the cosine squared theta, plus you'd have 4 cosine, and I messed that up. So cosine of theta, and then plus 2 times 1 is 2. So from here, because I have a squared term, I want to think about either factoring or using the quadratic formula. This one's going to be factorable, so we'll be safe there. Basically, let's move everything to the left because that's where I like it. So let's subtract 2. So basically, this is going to be 1. Let's go ahead and subtract 4 times the cosine of theta. So minus 4 times the cosine of theta. So this is going to be negative cosine of theta. And then let's subtract 2 times cosine squared theta. So I'm running out of room over here, so let's just kind of put this over here. So minus 2 times cosine squared of theta. I know this is kind of getting a little messy, but let's just write it neatly now. So we'll put this out in front. We'll put negative 2 times cosine squared theta. And then we'll put minus cosine of theta. Then we'll put plus 1. And of course, everything's gone from over here, so this equals 0. If you want, for factoring, a lot of people do not like to factor with a leading coefficient that's negative. You can multiply everything by -1, so this becomes positive. This becomes positive, this becomes negative, and it has no effect on 0, okay? So basically, if I want to factor this, again, you can use that trick with u if you want. I don't really need to do it, so I'm just going to put 2 times cosine of theta and cosine of theta, okay, because this times this would give me this. Now, the final guy is -1. So that can only come from +1 times -1. We know that this guy right here is positive, so that means I want to put plus 1 here and minus 1 here, right? Because the outer would be 2 times cosine of theta, the inner would be minus cosine of theta, so that would combine and give you this, okay? So let's go ahead and copy this and paste this in another sheet. And again, I'm just going to use my zero product property. I'm going to say 2 times the cosine of theta minus 1 equals 0, or the cosine of theta plus 1 equals 0. So I'm going to add 1 to both sides over here, and I'll have 2 times the cosine of theta is equal to 1, divide both sides by 2, and again we get this cosine of theta is equal to a half. So we already know that that's going to occur basically at 60 degrees, right? Or a reference angle of 60 degrees in quadrant 4, which is 300 degrees. Let me just drag this up here. We'll say that theta here is 5 pi over 3, or actually let's do this first. So we'll do pi over 3, or then 5 pi over 3. So again, this guy right here is your 60 degrees. This guy right here is going to be your 300 degrees. Okay, so then okay, and I'll just put a comma here. For this one, it's really simple. I just go minus 1 here, minus 1 here. So we have the cosine of theta is equal to -1. We already know this is going to be pi. Okay, so we've seen this before. So this is exactly the same solution that we got in the last section, or the last example, but basically now you're going to see that one of them is not going to work. So let's actually erase all of this. We know it's a pain to check solutions, but it's absolutely necessary in this case. So my original equation is the square root of 3 multiplied by the cosine of theta over 2, okay? And then basically you have is equal to 1 plus the cosine of theta. So what do I have here to start? Let's go square root of 3 times, you would have the cosine of, basically you would have pi over 3 divided by 2. So it's like multiplying by a half. So it's the cosine of pi over 6. And the cosine of pi over 6, remember pi over 6 is 30 degrees, so that's going to be square root of 3 over 2. So let me just write this over here for reference. So cosine of pi over 6 is square root of 3 over 2, okay? So let me erase this, and I'm going to put square root of 3 over 2. This equals 1 plus the cosine of theta. In this case, we're working with our pi over 3. Let me write this in. So the cosine of pi over 3. And we already know that this is 60 degrees here, so this would be 1/2, okay? So what is 1 plus a half? Most of you know this would be 2 over 2 here. So 2 over 2 plus 1 over 2 would be 3 over 2, or basically 3/2. Now, if I do square root of 3 times square root of 3, that is 3, okay? So this does give me 3/2. So the first solution is valid. So this one you can put a big fat check, okay? The next one you're going to see a problem with. So let's go ahead and erase this and try again. So we have the square root of 3 times, I'm putting 5 pi over 3 in here. Remember, if I do 5 pi over 3, let me erase this. We're not going to need this anymore. So if I do 5 pi over 3, and then divided by 2, it's like having cosine of 5 pi over 6. Now 5 pi over 6 is 150 degrees, so that has a 30-degree reference angle, and it's in quadrant 2, so it would be the negative of the square root of 3 over 2, okay? So this is the negative of the square root of 3 over 2, okay? Over here I have 1 plus the cosine of 5 pi over 3, and we already know this is going to be a half, right? So we know this is a half, this ends up being 3/2. And you can see this is not going to work out because of the sign, right? Square root of 3 times square root of 3 is still 3, but now it's going to be basically negative of 3/2 equals 3/2. So this is false, right? This does not work. So this is what I mean by checking the solutions. If you don't check them, there's a chance, it's not going to happen every time, but there's a chance that you report a wrong answer, okay? Something that doesn't work in the original equation. Now this last one's going to work. If I put a pi over 2 in here, remember pi over 2 is 90 degrees, and cosine of 90 degrees is 0, right? So if I did square root of 3 times 0, well, that's 0, right? So you can basically say this is 0 over here. And then on this part, I have 1 plus the cosine of pi, and the cosine of pi, or the cosine of 180 degrees, is going to be -1. So what is 1 plus -1? That's going to be 0. So you get 0 equals 0, so this one checks out as well, okay? So let's go ahead and erase this, and we can finally write our solution set. I know this is super tedious, but it's just something you have to do. So we end up with pi over 3, okay? And then we end up with pi. These are the only two solutions in the interval we're given, from 0 degrees, or from actually 0 in terms of radians, out to 2 pi in terms of radians. So 0 is included, 2 pi is not. In this lesson, we want to talk about solving trigonometric equations with multiple angles. All right, let's take a look at the first problem. So here we have the cosine of 2 beta is equal to -10 cosine squared beta plus 8. Now we just want to solve this from 0 to 2 pi, where 0 is included and 2 pi is excluded. Now when you look at this, if I'm trying to get cosine of beta equals some number, here you have cosine of 2 beta, here you have cosine squared beta. So this one right here is going to be the immediate problem for us because you want to write this in terms of the cosine of beta, again, equals some number in the end. So what you would want to do is use a little identity to plug in for this guy. And coming down here, this is the one I'm going to work with. If you have cosine of 2 theta or 2 beta, whatever you're working with, you have 3 different formulas you can choose from. I'm going to work with this one. So what I'm going to do is say the cosine of 2 beta is equal to 2 cosine squared beta minus 1. So I'm just matching this formula here. I'm just taking the beta in the place of theta. And basically now you have cosine of 2 beta and cosine of 2 beta. So those match. And what you can do is take this guy right here and you could just plug it in for this guy right here. And that's going to give me cosine squared beta over here and cosine squared beta over here. So that's what I want. So let's write this as 2 cosine squared beta minus 1, again, just taking this and plugging it in for this. So that's how I get this left side now. So this equals, on the right, nothing's going to change. So this is just negative 10 cosine squared beta and then plus 8. Okay, at this point, I want to get cosine of beta equals some number. If you have a squared guy involved, then you should be thinking about factoring, or in some cases, the quadratic formula. But for this particular problem, you could actually solve it using the square root property, and it's going to be a lot faster. You could solve this with factoring if you want to, but it's going to take a little bit more time. So what I'm going to do is isolate cosine squared beta on one side and then have a number on the other side so I can use the square root property. So I'm going to add 10 cosine squared beta to both sides of the equation, just like that. And so right here, this is going to cancel. And then the other thing I'm going to do is add 1 to both sides of the equation. So this is going to cancel. So on the left, you have 2 cosine squared beta, then plus 10 cosine squared beta. That is 12 cosine squared beta. And this equals 8 plus 1 is going to be 9. Now, what you would want to do, since 12 is multiplying the cosine squared beta there, you would divide both sides of the equation by 12. So you want cosine squared beta by itself to use the square root property. Okay, so this right here is going to cancel, and you get cosine squared beta is equal to, for 9 over 12, again, each is divisible by 3, so 9 divided by 3 is going to be 3, and 12 divided by 3 is going to be 4. So this is cosine squared beta is equal to 3/4, and now we can use our square root property. Again, if we have something like, let's say, x squared equals 3/4, then by the square root property, we can say x is equal to plus or minus the square root of 3/4. So that's the square root of 3 over the square root of 4, which is 2. So x would be equal to plus or minus the square root of 3 over 2. Well, here it's the same thing. I'm just going to get that cosine of beta is equal to plus or minus the square root of 3/4. And again, this becomes the square root here of 3 over the square root of 4. And the square root of 3 really can't do anything with that, but the square root of 4 is going to be 2. So the cosine of beta is equal to plus or minus the square root of 3 over 2. Okay, let's come to the unit circle, and let's actually write this as the cosine of beta is equal to the square root of 3 over 2, and then I'm going to write or the cosine of beta is equal to the negative of the square root of 3 over 2. So for beta here, we're going to look in quadrants 1 and 4, where cosine is positive, and I'm looking for an x-coordinate of square root of 3 over 2. So right here at pi over 6, and then coming down here, it's going to be at 11 pi over 6. So notice it's pi over 6 here, and then a pi over 6 reference angle here at 11 pi over 6. Then if I'm looking for cosine of beta to be equal to negative square root of 3 over 2, well, I'm looking in quadrants 2 and 3, where cosine is negative. So you can just think about a pi over 6 reference angle, or again, you could just look for that x-coordinate of negative square root of 3 over 2. So that's going to be right here at 5 pi over 6, again, pi over 6 reference angle, and then right here at 7 pi over 6, again, pi over 6 reference angle. So because we're working in the interval where beta is greater than or equal to 0 and less than 2 pi, we can just list these 4 solutions and be done with it. So we're going to say that beta is equal to, we have pi over 6, we have 5 pi over 6, and then we have 7 pi over 6, and then lastly, we have 11 pi over 6. All right, let's take a look at the next problem. So here we have 4 sine of beta cosine of beta equals the square root of 3. We want to solve this over the interval from 0 to 2 pi, where 0 is included and 2 pi is excluded. So the first thing is when you look at this equation, it might not be immediately obvious what you can do, but if we look at our identities, again, you have something like this double angle identity, the sine of 2 theta equals 2 sine of theta cosine of theta, which you can use to solve this equation. So I'm going to write this as the sine of 2 beta is equal to 2 sine of beta cosine of beta. Come back up here and paste this in. Now, this might not be immediately obvious, but we're going to take this right here and match it with this right here. Now, right now you have this 4 right here, and you have this 2 right here. So you've got to rewrite this to where it's going to match. So this is just straight multiplication. So for 4, I could really write that as 2 times 2. So I could say that this is 2 times, and then it would be 2 sine of beta cosine of beta, and this equals the square root of 3. So this 2 times 2 sine of beta cosine of beta gets me back to 4 sine of beta cosine of beta. So I haven't done anything illegal. If you look at this guy right here, now it matches this guy right here perfectly. 2 sine of beta cosine of beta, 2 sine of beta cosine of beta. So that means I can legally take this right here and I can plug it in for this right here. So what that's going to do for me is I'm going to have 2 sine of 2 beta equals the square root of 3. So I'll be able to get it to sine of 2 beta equals some number, and I'll be able to get a solution. So let's go down and make a little substitution here. So I'm going to have my 2, don't forget about that. And then what is it multiplying? Again, for this, I'm plugging in this. So I'm going to have my sine of 2 beta, and this equals my square root of 3. All right, so just like I said, we want to get sine of 2 beta equals some number. Right now you have 2 that's multiplying the sine of 2 beta. So let's divide both sides of the equation by 2. So this is going to cancel, and we're going to get the sine of 2 beta is equal to the square root of 3 over 2. All right, there are quite a few ways you could solve this. What I'm going to do is stick to the method that the book uses because we're solving over a specific interval. We're not giving the general solution. So I'm going to start with the interval we were given. So we have beta is greater than or equal to 0 and less than 2 pi. Well, right now I have 2 beta. So I'm going to multiply each part of this inequality here by 2. So 0 times 2 is still 0, and this is less than or equal to. Beta times 2 is 2 beta. So now this matches this, and then this is less than 2 pi times 2 is 4 pi. So right now I'm going to work in this interval because, again, I have the sine of 2 beta, not the sine of beta. So that's why I'm adjusting this interval. So let me move this up here, and we're going to think about where are the sine values square root of 3 over 2 in this interval right here. So let's start with the standard interval. So just going from 0 to 2 pi, 0 included, 2 pi excluded, and that's going to give you a pi over 3 solution. So there's your square root of 3 over 2 for the y value, and then here's your square root of 3 over 2 for the y value as well. So that's at 2 pi over 3. But again, to get all of the solutions in this interval, what you have to do is take those solutions and you have to add 2 pi to them in order to get all the solutions in this interval. So I'm going to take and list pi over 3, and then let me list 2 pi over 3. And then what I would have to do is, again, take pi over 3, so pi over 3, and I've got to swing around by another 2 pi. So let me go plus 2 pi, so that's 6 pi over 3 if I get a common denominator. Let me make that 3 a little bit better. So that's 7 pi over 3. So let's put that up there. So that's 7 pi over 3. So again, starting here, just swinging around by another 2 pi. You've got to do the same thing here. So you're going to swing around by another 2 pi. So let's put this as 2 pi over 3 plus, again, 6 pi over 3. So 6 pi over 3 is, again, 2 pi written with a common denominator. So this would be 8 pi over 3. So 8 pi over 3. So that's basically all you have to do for this part. The only thing is you have not solved for beta. You've solved for 2 beta. So in other words, you could say that 2 beta is equal to this right here. Let me just drag this down. And I don't know if that's going to fit. And let me just grab this real quick and paste this in and go to another page. So basically, if you want to solve for beta, you would divide everything by 2, or you could multiply everything by a half. So in other words, you could say that beta is equal to, you'd have pi over 3 times 1/2. So that would be pi over 6. So pi over 6. And then you'd have 2 pi over 3 times 1/2. So the 2's would cancel there. So that would be pi over 3. So pi over 3. And then you'd have 7 pi over 3 times 1/2. That would give you 7 pi over 6. And then lastly, you'd have 8 pi over 3 times 1/2. So here, 8 divided by 2 would give you 4. So this would end up being 4 pi. So 4 pi over 3. So these are your solutions in terms of beta. So if you plug those back into the original equation, they will work. And they are in our interval where beta is greater than or equal to 0 and less than 2 pi. So beta is pi over 6, pi over 3, 7 pi over 6, and then 4 pi over 3. All right, let's take a look at another problem. So we have -9/2 is equal to -4 plus the cosine of beta plus 7 pi over 4. We're solving this over the interval from 0 to 2 pi, where 0 is included and 2 pi is excluded. So I'm going to get cosine of beta plus 7 pi over 4 by itself. So that'll be on one side. There'll be a single number on the other side. So that's the first goal. So let me write this as -4 plus cosine of beta plus 7 pi over 4. And then this would be equal to, you have this -9/2. Now, if I want cosine of beta plus 7 pi over 4 on one side by itself, I've got to get rid of this -4 here that I'm adding to this. So I'm going to just add 4 to both sides of the equation. This will cancel. And on the left, I have what I want. So this is the cosine of this beta plus 7 pi over 4. And this equals, over here I would get a common denominator. So let's write 4 as 8 over 2. I'm just going to multiply by 2 over 2 to do that. So again, this would be 8 over 2. So 8 over 2. And -9 plus 8, that's -1. So this would be over the common denominator of 2. So this is equal to -1/2. Now this is the part where people tend to get confused. Essentially what you're going to do is adjust your interval. You don't have beta. So if you were solving cosine of beta equals -1/2, well then I could go through and I could say, well, where's the x-coordinate -1/2? Where you're going to have right here at 2 pi over 3. And then you come over here, and that's going to be at 4 pi over 3. We don't have that, though. We have this beta plus 7 pi over 4. We don't have beta. Well, I can adjust that interval. We had beta is greater than or equal to 0 and less than 2 pi. Well, instead of beta, I have beta plus 7 pi over 4. Okay, well, I'm just going to add 7 pi over 4 to each part. So 0 plus 7 pi over 4 is 7 pi over 4. This is less than or equal to beta plus 7 pi over 4 is beta plus 7 pi over 4. So this matches this, and this is less than 2 pi plus 7 pi over 4. So if we do 7 pi over 4 plus, let's go 8 pi over 4, just writing 2 pi with the common denominator, this would be 15 pi, so 15 pi over 4. So 15 pi over 4. So if we had cosine of beta equals -1/2, again, I would have this 2 pi over 3 and this 4 pi over 3. But in this case, we have the cosine of beta plus 7 pi over 4. So when I adjust this interval to this one right here, let me get rid of this one right here so this is crystal clear. What I'm going to do is look for where the cosine value is -1/2 in this interval. So you would start at 7 pi over 4. So in other words, you've already swung around by 7 pi over 4, and then you want to swing around by another 2 pi to end up at 15 pi over 4, even though that's not included. So you're going to catch this guy right here and this guy right here again, but it's not going to be 2 pi over 3 or 4 pi over 3. It's going to be you adding 2 pi to those angles. So what you would do is you would say that beta plus 7 pi over 4 would be equal to, you're going to take this 2 pi over 3, so 2 pi over 3, but now you've got to add 2 pi to that. So that's going to be me adding 6 pi over 3. So that would give me 8 pi over 3. So you can get rid of these middle steps here and just say this is equal to 8 pi over 3. We'll solve this for beta in a moment. Let's just do the other one. So then again, you have this beta plus 7 pi over 4 is equal to, again, you're going to take this 4 pi over 3. So this 4 pi over 3, and then you're going to add 2 pi. So you're going to say this is plus 6 pi over 3. So this gives you 10 pi over 3. Let me move this down here so this is more clear. Now, I know the first time you do this, this is super confusing, but just think about the fact that, again, you started here at 7 pi over 4. That's where the interval is beginning. So if I'm starting here, by the time I swing around, this is not 2 pi over 3. This is 2 pi over 3 plus 2 pi. So that gives me that 8 pi over 3. And then as I continue, this is not 4 pi over 3. This is going to be 4 pi over 3 plus 2 pi. So that's that 10 pi over 3. So you've got to adjust things because we're not solving cosine of beta equals negative 1/2. We are solving cosine of beta plus 7 pi over 4 equals negative 1/2. So everything got adjusted. So let's go ahead and grab this. And I'm just going to come down here and we can solve these pretty easily. So let's go OR there. I'm going to subtract 7 pi over 4 away from each side of the equation over here. So this is going to cancel. You're going to have beta is equal to 8 pi over 3 and then minus 7 pi over 4. You need a common denominator, so let's multiply by 4 over 4. Let's multiply this by 3 over 3. So this would be 32 pi over 12. So 32 pi over 12, 21 pi. So 21 pi over 12. So this would give me 11 pi, so 11 pi over 12. So that's one solution. Let me get rid of this and just write this as beta is equal to 11 pi over 12. And let me solve this one now. So I'm going to subtract 7 pi over 4 away from each side of the equation. So that cancels. You get beta is equal to, let's go 10 pi over 3. I'm going to just multiply this by 4 over 4 now to get a common denominator, and then minus 7 pi over 4 times 3 over 3. So we will say that beta is equal to 10 pi times 4 is going to be 40 pi, and this is over 12, and then minus 7 pi times 3 is 21 pi. So 21 pi, and this is over 4 times 3 is 12. So 40 pi minus 21 pi is 19 pi. So this is 19 pi over 12. Let me just put a comma here and put 19 pi over 12. So those are your solutions in that given interval, again, where beta is greater than or equal to 0 and less than 2 pi. Okay, let's take a look at another problem. So here we have the cosine of 6x is equal to negative sine of 4x plus the cosine of 2x. So here we're going to solve over this interval from 0 to pi, where 0 is included and pi is excluded. When you solve a problem like this that involves these sum to product identities, in most cases, you're not going to solve that over an interval because there's just too many solutions. You will give the general solution. Let me start this problem off as saying we have the cosine of 6x. I'm going to add the sine of 4x to both sides, and I'm going to subtract the cosine of 2x away from each side. So let me subtract away the cosine of 2x first. So I have this. And then I'm going to add sine of 4x. And then we're going to say this equals 0. Okay, let's grab this real quick. And let's come down here. So I have our little identities set up for us. So these are the, again, sum to product identities. So we have this cosine of A minus cosine of B. Here you have cosine of 6x. So 6x is your A minus cosine of 2x. So 2x is your B. Let me actually slide this down. And I'll write this out first, and then we'll plug in. So if you had the cosine of 6x minus the cosine of 2x, so I'm just going to do this part right here. This is equal to negative 2, and then sine of, you have a plus b over 2. So this plus this. So 6x plus 2x over 2. And then you have your sine of a minus b over 2. So 6x minus 2x. So 6x minus 2x, again, this is over 2. 6x plus 2x is 8x. So this right here would be 8x over 2. So this 8 would cancel with this 2 and give me a 4. So this would be 4x right here. So let's write that like that. I'm just going to wrap this for clarity. And then here, 6x minus 2x is 4x. And so this would be 4x over 2, which is 2x. So let's write the sine of 2x. Now, since this right here matches this right here, we can take this guy right here and plug it in for this right here. Now, why are we doing that? Notice you'd have a sine, and then you have a sine. And more specifically, you have this 4x here and this 4x here. So we're going to be able to actually solve this with factoring. So let's come down a little bit and let's plug in. So this goes in here. So negative 2, and then sine of, you have your 4x, and then sine of, you have your 2x, and then plus your sine of 4x, and this equals 0. So you have your sine of 4x and your sine of 4x. So we are going to factor that out. So let's factor that out. So out in front of some parentheses, you would have the sine of 4x, and then inside, you would have negative 2 sine of 2x. So negative 2 sine of 2x, and then plus, if this gets pulled out, you're going to have a 1, and then this equals 0. Now, at this point, you can use your zero products property. So you can say that the sine of 4x is equal to 0, or we're going to do this one. So negative 2 sine of 2x plus 1 equals 0. In this particular case, you have sine of something. It doesn't matter what it is. In this case, it's 4x equals 0 or some number. This is okay. For this, when you want to clean it up, you would want sine of 2x equals some number. So let's go ahead and subtract 1 away from each side. This cancels. So actually, let me just erase it so we can save some space here. And then I would divide both sides by negative 2. So this would cancel. So you're going to get the sine of 2x is equal to 1/2. So positive 1/2. Now, here's where you need to make a decision. Again, in most cases, you're going to solve for the general solution. And when I solve for the general solution, I like to use a substitution technique. So you can do it this way if you want. If you're solving over an interval, you can do it the normal way that we've been doing it by adjusting our interval. So instead of sine of 4x equals 0, for this particular one, I'm going to let u be equal to 4x. Now this has nothing to do with this. So actually, let me cut this away and put this on another page so nobody's lost, because people will get confused. So now I can solve this, let me get rid of this or, by saying that I have the sine of u is equal to 0. So if I look at the sine of u equals 0, using my unit circle, let me write this in. So the sine of u equals 0. So if you look at this guy is 0, so that's at 0, and then this guy is 0, that's at pi. So you could write that u, in terms of the general solution, is equal to 0 plus 2 pi n, and then you could say pi plus 2 pi n, where n is any integer, because things are going to repeat every 2 pi in terms of u. Now, what you could actually do is write this as 2 pi n, and then pi plus 2 pi n, but you would notice that actually you can combine those solutions and make it a little bit more concise, because things are happening every pi. So in other words, I could just write this as pi n. So I could write this as pi n, because if I plugged in a 0 for n, I'd have 0. If I plugged in a 1, I'd have pi. If I plugged in a 2, I'd have 2 pi. At 3, I'd have 3 pi, so on and so forth. So this is the general solution in terms of u. So let's come back up, and let's say that u is equal to pi n. Now, we let u be equal to 4x. So all I have to do is plug in a 4x for u. So 4x is equal to pi n, and then just solve for x. How do I do that? I divide both sides by 4. So this would cancel, and you're going to get that x is equal to pi over 4 times n. So let me get rid of this and bring this over here. So x is equal to pi over 4 times n. Now, we will get our solution in the interval in a moment. Let me get rid of this, and let me come down here and solve this. So I'm going to use u again, but it's only in terms of this. It has nothing to do with what we did before. And actually, so nobody gets lost, let me just pick something else. Let me let w, so nobody is confused, be equal to 2x. So now I want to solve the sine of w is equal to 1/2. Come back to the unit circle, and let's think about this. Again, sine of w equals 1/2. Well, we know how to solve that. We know that solutions are going to repeat every 2 pi. So where's the y-coordinate 1/2? So right here at pi over 6, and then that's going to be right here at 5 pi over 6. So we can say that w is equal to pi over 6 plus, again, these solutions repeat every 2 pi. Again, this is in terms of w. So we're going to say 2 pi n, and then we're going to have 5 pi over 6 plus 2 pi n. Again, things are happening every 2 pi in terms of w. Okay, so in terms of w. So let's grab this. All right, so let's come back here. Let's get rid of this. And now w is 2x. So all you have to do is go back and say, okay, well, 2x is equal to, we have pi over 6, and then plus, you have 2 pi n. The other one is 2x is equal to 5 pi over 6 plus 2 pi n. Let me get rid of this. And actually, I probably should slide these over a little bit because I have to do some multiplication here. Let me make that border a little bit better. And let me slide this down just a little bit and slide this up just a little bit. Now, we have 2x, not x. So if you want x by itself, you can divide everything by 2, but because we have a fraction involved, it's better to multiply by 1/2. It's just a little bit easier to do it that way. Let me get rid of this border here. So multiply by 1/2, and then multiply by 1/2. So we know that this would cancel and just give me x is equal to pi over 6 times 1/2 is pi over 12. and then plus 1/2 times 2 pi n. The 2's would cancel. You just have pi n. So get rid of this. So that's one guy there. Let me move this over. And then this guy, I'm going to do the same thing. So let me move this up. I'm going to multiply this by 1/2, multiply this by 1/2, and multiply this by 1/2. So we're going to see that the 2's are going to cancel. You're going to have x is equal to, if you have 5 pi over 6 times 1/2, well, we would have 5 pi over 12, and then plus, again, the 2's would cancel, so you're going to get pi n. So let me get rid of this, and actually this color really doesn't show up very well. So let me change this and say that x is equal to pi over 12 plus pi n, and then we have 5 pi over 12 plus pi n. Okay, let me bring this back here, and now let's put our solution together. So right now I'm giving you the general solution, and then I'll give you the solution over an interval. So for the general solution, you're going to take this one. So we're going to say that we have pi over 4 times n. Then if we think about this one, we have pi over 12 plus pi n. And then this one is 5 pi over 12 plus pi n. That's our general solution. Now, if we want to go with the solution where x is greater than or equal to 0 and less than pi, well, again, you're going to start here and plug in a 0 for n. So that would give you, let's go x is equal to 0. And if I plugged in a 1, I'd have pi over 4. If I plugged in a 2, I'd have 2 pi over 4, which is pi over 2. If I plugged in a 3, I'd have 3 pi over 4. If I plugged in a 4, I'd have 4 pi over 4, which is pi, and that's not in this interval, so I'm going to stop there. And then these, you would have pi over 12 if you plugged in a 0 there. And then if you add pi, you're not going to be in this interval. So then this one, I would have 5 pi over 12, so 5 pi over 12. Again, if I add pi, I'm not going to be in this interval. So these are your solutions in this interval. So 0, pi over 4, pi over 2, 3 pi over 4, pi over 12, and then 5 pi over 12. Okay, so I want to think about this graphically with you. If you're struggling with finding the general solution, this can be extremely helpful, although it's extremely time-consuming to think about this with a graph. So we have y equals the cosine of 6x minus the cosine of 2x plus the sine of 4x. So this was my equation. It's just that instead of y, we had 0 over here. So if I plugged in a 0 for y, so in other words, if I had 0 is equal to the cosine of 6x minus the cosine of 2x plus the sine of 4x, all I'm doing is I'm saying, for which x values am I going to get a y value of 0? Well, where is y 0 when I'm thinking about this on the coordinate plane? Well, that's on the x-axis, right? So that's where y is 0. So anywhere where I cross the x-axis or have an x-intercept, I'm going to have a solution for this equation. So thinking about this, where x is greater than or equal to 0 and less than pi, I get this graph right here. Now, in a moment, we're going to talk about the fact that the period for this guy is going to be pi. We discussed this in the last practice test. Maybe you didn't watch the video for that, but I'll explain where this is coming from in a moment. So that means that I can go from 0 to pi, and I'm going to include 0 and exclude pi, and any solutions I find will actually repeat in that next cycle. So I could just take that solution and add pi. But you're going to see that you can condense some of those solutions that make it a little bit simpler. And let's just start with what we have. So notice that you have this 0 here, so that matches this one. I'm going to skip this one over for a moment. So we have this pi over 4, so that's there. I'm going to skip this one, so this is pi over 2, so that's there. And then I'm going to go to this one, which is 3 pi over 4. Now, if you think about those solutions, you have 0, and then you have pi over 4, and then you have pi over 2, and then you have 3 pi over 4. Again, you could go through and say plus pi n, and then plus pi n, and then plus pi n, and then plus pi n. That is valid. But what's happening is, if you add pi to this, let me just show if I added pi, this would get me to pi. If I added pi to this, I would be adding 4 pi over 4, so this would get me to 5 pi over 4. If I added pi to this, that would get me plus 2 pi over 2, so that would be 3 pi over 2. And then if I added pi to this, I would add 4 pi over 4, so that would get me to 7 pi over 4. Well, if you go through here and you just look at these first guys here, so it would be a jump of pi over 4 each time. So 0 plus pi over 4 is pi over 4. Pi over 4 plus pi over 4 is pi over 2. Pi over 2 plus pi over 4 is 3 pi over 4. 3 pi over 4 plus pi over 4 is pi. Pi plus pi over 4 is 5 pi over 4. 5 pi over 4 plus pi over 4 is 3 pi over 2. 3 pi over 2 plus pi over 4 is 7 pi over 4, and so on and so forth. So that's why we got that pi over 4 times n with the general solution. So we have this pi over 4 times n. Then the other ones, you really can't do anything with them other than to say that you have pi over 12. So that's this one right here, and then just plus pi n. So it's just going to repeat in the next cycle. So this is pi over 12 plus pi n. Let me slide this down. And then the other one, we have 5 pi over 12, so that's this here. So again, that's just going to repeat in the next cycle. So 5 pi over 12 plus pi n. All right, let's come to the graph. Now, these solutions are extremely hard to read, so you probably need to follow me on Desmos or something like that in order to fully see everything. But I'm just going to first talk about the period for this guy. I'm going to let you visually see that and explain where it's coming from. So in the practice tests for the last lesson, we talked about the fact that if you had something like y equals the cosine of 6x minus the cosine of 2x plus the sine of 4x, if you wanted the period for this, then basically you would think about the least common multiple of the periods. So how do you get the least common multiple of the periods? So this right here, you'd think about it as, let's just say you had y equals the cosine of 6x. What's the period? Well, it's going to be 2 pi over 6, right? 2 pi over 6, which is pi over 3. So pi over 3. Again, that's coming from that formula. If you have y is equal to the cosine of bx, well, it's 2 pi, which is the standard period for cosine, divided by b. So here it's 2 pi divided by 6, so that gives me pi over 3. It's the same thing if you run into sine, right? So sine and cosine is the same thing. So let's do this one. So this is the cosine of 2x. So that's 2 pi over 2. So that gives me just pi. And then for this one, it's the sine of 4x. So that's 2 pi over 4. So that's pi over 2. So we have not discussed how to find the least common multiple of fractions. So in other words, let's say I said, what is the least common multiple of 1/3, 1, and 1/2? Well, some of you know that it's going to be 1, but others don't. Now, there's a formula you can use for it, but it's a little bit complicated, actually, if you ask me. I think it's a little bit faster to just list things. So if you had something like pi over 3, all you're doing is you're multiplying it by 1, then 2, then 3, then 4. You're generating some multiples. So times 1, it would just be pi over 3. And then times 2, it would be 2 pi over 3. And then times 3, it would be 3 pi over 3, which of course is just pi. And then we could just do one more. So times 4, it would be 4 pi over 3. Let me put a border. For this one, if it's pi, well, that's real easy. Multiply by 1, you get pi, then 2 pi, then 3 pi. Let's stop at 4 pi. Then for the other one, you have pi over 2. So let's go times 1, it's pi over 2. Times 2, it's 2 pi over 2, which of course is going to just be pi. And then times 3, it's 3 pi over 2. Times 4, it's going to be 2 pi. And you could stop there. If you look at the least common multiple here, well, looking through, what do I have that's common to everything? You have pi, you have pi, and you have pi. So in other words, if you had 1/3, if you had 1, and you had 1/2, the LCM would be 1. But in this case, we have pi over 3, which can be thought of as 1/3 times pi. You have pi, which can be thought of as 1 pi. And then pi over 2, which you could think of as 1/2 times pi. So the least common multiple there is pi. So that tells me that the period for this graph here is going to be pi. Let me get rid of this. And let me actually trace this out so you can see it. If you want to follow me, type in x is equal to pi like this in Desmos. It's going to fix it for you and give you a pi like that. You're going to get a vertical line. And you can go x equals 2 pi, and then x equals 3 pi, so on and so forth. You're going to get these vertical lines, and it's going to really allow you to see the period of this guy. So I'm just going to trace from 0 to pi, and then we'll see that this is going to repeat from pi to 2 pi. So this right here, this is going to be one cycle for this graph. So this is one cycle. So from 0 to pi. And then again, if I went from pi to 2 pi, the same thing is going to repeat. So basically, I come up, come down, come back up, come down, come back up. So this is way up here. This is exactly matching what happened in the last cycle. So you can see that these two match and the period is going to be pi. So this tells me that things that happen from 0 to pi, 0 included, pi excluded, would happen again from pi to 2 pi, pi included, 2 pi excluded. So that's how we ended up on the last page where I did this where you could see the solutions more clearly, and looks like I erased my 5 pi over 12. But as I was saying, it just shows you that solutions that happen in this cycle will repeat in the next cycle. So you could take your 0 plus pi n. You could take your pi over 12 plus pi n. You could take your pi over 4 plus pi n, so on and so forth. It's just that the 0, pi over 4, pi over 2, 3 pi over 4, those guys can be condensed into this form right here. So the pi over 4 times n, where n is any integer. And then for your pi over 12, well, you really can't do any better than just saying plus pi n. So you have your pi over 12, you add pi, that gets you to that 13 pi over 12. I know you can't see it, but it's right there. And then 5 pi over 12, again, if you add pi, you're going to be at that 17 pi over 12. Again, I know it's hard to see, but just follow it on Desmos if you want to look at it. So this is our general solution. Again, if you want to play around with the graph on Desmos, you can visually see this, and it'll help you to understand the concept of the general solution and how things are repeating. In this lesson, we want to talk about solving trigonometric equations with inverse trigonometric functions. All right, before we start looking at any equations, I want to review some concepts that are going to be important for today's lesson. So these are going to come from our lesson on inverse trigonometric functions. So I'm going to let f be a one-to-one function. What does it mean to have a one-to-one function? Again, if you go back to the definition of a function, you have a relation where for each x, there's one y. So you would look at the graph of the relation, and it needs to pass the vertical line test, so no vertical line would impact the graph in more than one location. And if it passes that, you have a function. So for each x, there's one y. Now, when you think about a one-to-one function, you start with a function, and you apply another rule where you say, now also, for each y, there's one x. So for that, you would check it with the horizontal line test. So no horizontal line would impact the graph of a one-to-one function in more than one location. If it does, that's not a one-to-one function. If it doesn't, then you're good to go and you have a one-to-one function. And if you have a one-to-one function, you can generate an inverse. So let's say f is your one-to-one function. The way you would notate your inverse, you would say it was f inverse like this. So again, this is not an exponent of -1. This is the inverse of my function f. The way you generate your inverse is you swap your x's and your y's. So the domain, or the set of allowable x values for f, becomes the range, or the set of allowable y values for f inverse. And then the range for f becomes the domain for f inverse. So in other words, if I look at a point on f, and let's say it's 3, 2, when I go to the inverse, these guys are going to be swapped. So the x will become the y, and the y will become the x. So this would be 2, 3. So your x value of 3 becomes your y value of 3, and that could be a lot better there. And then your y value of 2 will become your x value of 2 in the inverse. So following this thought process here, where the domain becomes the range and the range becomes the domain, what happens is when you look at your function and you compose it with its inverse, you're going to have this little cancellation that happens where you can say these guys are going to undo each other. So f of f inverse of x is equal to x for every x in the domain of f inverse. And then f inverse of f of x is equal to x for every x in the domain of f. So this is something we're going to use today when we're solving our trigonometric equations. So as a practical example, just using what we have here, let's say you had f of f inverse of, let's say, 2. So using this right here, it should be equal to 2. So I can just give an answer of 2 right away. But if you wanted to prove this, you can go about it the long way. So you could say, what is f inverse of 2? Well, I come up here and I say, okay, here's an x value of 2. If I plug that in, I know that my output, or my y value, is going to be 3. So what I want to do is say that this is now f of 3. Okay, well, what is f of 3? Well, again, if I look at my x value of 3, the associated y value is going to be 2 now. So this is going to be 2. So again, f of f inverse of 2 is going to give me 2 at the end of the day. I can shortcut this and not go through this inside part. Now, when I look at the other one, in that case, we have f inverse of, let's say, f of 3. Well, again, I already know that this is going to give me 3. If I go about this the long way, again, if I start on the inside of this guy right here, well, what is f of 3? F of 3 is 2. So this would be f inverse of 2, and f inverse of 2 is going to be 3. So these guys are just undoing each other. Again, f of f inverse of x is equal to x as long as x is in the domain of f inverse, and then f inverse of f of x is equal to x, again, as long as x is in the domain of f. All right, let's continue reviewing our lesson on inverse trigonometric functions. So if we look at the graph of y equals the sine of x, we can see the domain is from -infinity to +infinity, and the range is from -1 to +1, with both being included. We can also see that it's not a one-to-one function. It would fail the horizontal line test. So if we want to find the inverse sine function, we can't start with just y equals the sine of x. We have to do something called imposing a domain restriction, and we're going to come up with this, what we call restricted sine function. So y equals the sine of x, where x is going to be greater than or equal to -pi/2 and less than or equal to pi/2. So I have this listed as the domain from negative pi over 2 to pi over 2 with both being included. So when you restrict the domain, you end up with a one-to-one function with the same range. So the range is still the same from -1 to +1 with both being included. When you start with a restricted sign function and you swap the x's and the y's, you're going to generate your inverse sign function. So y equals the inverse sine of x, so you could say y equals the arc sine of x. And now the domain, which is from -1 to +1, both being included, is coming from the range of your restricted sign function. And then the range from negative pi over 2 to pi over 2, again, both being included, is coming from your domain of the restricted sign function. Now, the reason it's important to know all that, when you start using the cancellation properties with sine, you need to understand when you're composing sine with its inverse, when are you going to be able to cancel things? So in other words, we like to cancel this with this and say, okay, well, the result of this is just going to be equal to x. But this is only true if x is in the domain of the inverse sine function. And the domain of the inverse sine function is from -1 to +1 with both being included. So the sine of the inverse sine of x is equal to x for x being greater than or equal to -1 and less than or equal to +1. If you pull out your calculator and you try to do sine of the inverse sine of 2, that is not going to give you 2 as a result. It's going to give you an error because 2 is not in the domain of the inverse sine function. All right, the next one is a little bit more challenging to understand. You can explain it with two different approaches. So if you have something like the inverse sine of the sine of x is equal to x, this is only valid for x being greater than or equal to negative pi over 2 and less than or equal to pi over 2. So this is actually pretty important to understand. The first way to think about it is, let's say you look at the sine of x, that is not the restricted sign function. So we know that for this guy, the domain is all real numbers, and plugging something in from -infinity to +infinity is going to give you a result that's going to be from -1 to +1. So I'm just going to mark that out and say that what's going to be plugged in for the inverse sine function is going to be from -1 to +1. Well, you know that that's the domain for the inverse sine function. And I know that the range is going to be from negative pi over 2 to pi over 2. So basically, I'm always going to get something out of this guy right here that's from negative pi over 2 to pi over 2. But what's going to happen is if you don't plug in something for x in this interval right here, you can't just cancel. You'd have to evaluate the sine of x first and then take the inverse sine of that. If you think about it from the other approach, you could say that these guys are only going to undo each other if you're working with the domain from the restricted sign function, which is where x is greater than or equal to negative pi over 2 and less than or equal to pi over 2. If you're within that domain, well, then the inverse sine of the sine of x is going to give you x. These guys are going to undo each other. Okay, using a similar thought process, again, when we start with y equals the cosine of x, it's not a one-to-one function, so we restrict the domain to where x is greater than or equal to 0 and less than or equal to pi. You're going to have the same range, so from -1 to +1, both being included. So again, if you start with that restricted cosine function and you swap the x's and the y's, you're going to get your inverse cosine function, so y equals inverse cosine of x, or y equals arc cosine of x, if you want to say it that way. Your domain is from -1 to +1, both being included, coming from the range of the restricted cosine function, and then the range is from 0 to pi, both being included. That's coming from the domain of the restricted cosine function. So here's something like the cosine of the inverse cosine of x is equal to x, for x being greater than or equal to -1 and less than or equal to +1. Again, you've got to be within the domain of the inverse cosine function for this to work. And then for this one, the inverse cosine of the cosine of x is going to be equal to x, for x being greater than or equal to 0 and less than or equal to pi. So again, you've got to be within the domain of the restricted cosine function for this to work. Again, the other way to think about this, you could say that the cosine of x, the domain for that is all real numbers. So I can plug in whatever I want, but the issue is, if it's not in this interval here, I've got to evaluate that first before I take the inverse cosine of it, because the inverse cosine is only going to give me something from 0 to pi, with both guys being included. So these guys will undo each other as long as x is in the domain of the restricted cosine function, so again, being greater than or equal to 0 and less than or equal to pi. And for the last one, we look at the tangent of x, so y equals the tangent of x, again, not a one-to-one function. You restrict the domain to where x is strictly greater than negative pi over 2 and strictly less than pi over 2. So negative pi over 2 and pi over 2 are not included. And then when you look at the range, it's going to be all real numbers. So when you swap the x's and the y's, you get your inverse tangent function. So y equals the inverse tangent of x, or y equals the arc tangent of x. So the domain is all real numbers, again, coming from the range of the restricted tangent function. And then the range is going to be from negative pi over 2 to pi over 2. Again, these guys are excluded here. Remember that the tangent of pi over 2 or the tangent of negative pi over 2, those are undefined because the cosine of pi over 2 is 0, and you'd have division by 0, which is undefined. So when we think about the range here, this is coming from the domain of the restricted tangent function. All right, so this first one one's really easy to understand. So the tangent of the inverse tangent of x is equal to x for any x that is a real number. So that's what this means. This means x is an element of the set of real numbers. And basically, if you think about the domain of the inverse tangent function, again, it's all real numbers. So that's why we can plug in whatever we want here, and these guys will undo each other. When we think about this one, again, this is the one that's more tricky to understand. So the inverse tangent of the tangent of x, this is equal to x for x being greater than negative pi over 2 and less than pi over 2. So this x is going to be in the domain of the restricted tangent function if you want these guys to undo each other. All right, let's take a look at a few sample problems. So suppose you're given the inverse cosine of the cosine of pi over 6. The first question you would ask is this angle pi over 6 in the domain of the restricted cosine function? If it is, these guys are going to undo each other. So in other words, is pi over 6 greater than or equal to 0? Well, yeah, that part's true. And less than or equal to pi? Well, yeah, that's true as well. So I can go ahead and say that this would cancel away with this, and I'm just left with that pi over 6, so that's going to be my answer. If you wanted to look at this on the unit circle, again, you would start, let's say we had the inverse cosine of the cosine of pi over 6. And we're going to do this the long way. So we're going to start on the inside, and basically we would say, what is the cosine of pi over 6? So I come to pi over 6, that's right here. The x-coordinate is my cosine value, so that's square root of 3 over 2. So now we want the inverse cosine of the square root of 3 over 2. When I think about the inverse cosine function, again, I'm going to work from 0 to pi, where 0 and pi are both included. So I'm just going to ask the question, what angle has a cosine value of square root of 3 over 2 in this interval from 0 to pi, where 0 and pi are both included? Well, we already know that that's going to be pi over 6. Here's your cosine value of square root of 3 over 2. So you're just reversing what you just did. You found the cosine of pi over 6, and that was square root of 3 over 2. Well, now the inverse cosine of square root of 3 over 2 is going to get you back to pi over 6. So this right here is your answer. And again, if you see something like the inverse cosine of the cosine of pi over 6, because this pi over 6 is in the domain of the restricted cosine function, or you can also say the range of the inverse cosine function, you can go ahead and just shortcut this process and say this is going to cancel with this, so they'll undo each other, and you're going to be left with this pi over 6 as your answer. Okay, let's look at another example. So here we have the inverse cosine of the cosine of 5 pi over 4. This is the one where a lot of people would make a mistake. So if you give the answer as 5 pi over 4, that is incorrect. In other words, you can't just cancel here because this 5 pi over 4, if you go to the unit circle, that's going to be right here. So that is not within the domain of the restricted cosine function or the range of the inverse cosine function. Again, you're thinking about this from 0 to pi, where both 0 and pi are included. So what you have to do for this particular problem, you have to go about it the long way. So you have to say this is the inverse cosine of the cosine of 5 pi over 4. Okay, so what is the cosine of 5 pi over 4? Well, if I come over here, that's going to be the negative of the square root of 2 over 2. Okay, so now I have the inverse cosine of the negative of the square root of 2 over 2. Okay, so what is the inverse cosine of the negative of the square root of 2 over 2? So if this guy is negative, I want to be in quadrant 2, where cosine is negative, and I'm looking for where I have a cosine value of negative square root of 2 over 2. So that's going to be right here, and that's going to be at 3 pi over 4. So this would be equal to 3 pi over 4. Now, if you had gotten the inverse cosine of the cosine of 3 pi over 4, again, because this 3 pi over 4 is in the domain of the restricted cosine function, or you could say the range of the inverse cosine function, in this particular situation, you can cancel this with this. Those will undo each other. And then basically you're left with that angle of 3 pi over 4. When you get a situation like this, because this is not within the domain of the restricted cosine function or the range of the inverse cosine function, you have to do more work. You have to first evaluate the cosine of 5 pi over 4, which is negative square root of 2 over 2. Then you take the inverse cosine of negative square root of 2 over 2, and that's going to give you this angle in quadrant 2, which is 3 pi over 4. All right, let's take a look at one more of these. So here we have the inverse sine of the sine of 6 pi over 5. Now, when we get this problem, again, I'm always asking, is this guy going to undo this guy? In other words, are these guys going to cancel away and just give me 6 pi over 5 as my answer? And here you're going to say no, because for this to work that way, you have to have this 6 pi over 5 being in the domain of the restricted sine function or the range of the inverse sine function, and it's not. If you think about, let's say, the range of the inverse sine function, again, you're working from negative pi over 2 to pi over 2, so you've got to be there. when you think about 6 pi over 5, that's not directly on the unit circle. I've sketched it in. So let me put 6 pi over 5, and you might be scratching your head saying, well, where's that angle at? And you can do some analysis and think about, okay, well, it's going to end up being in quadrant 3. So I'm just going to write this one out, and I'll give you an easier way to do that by converting it into degrees in a moment. So this would be greater than pi and less than 3 pi over 2. So that tells me I have an angle in quadrant 3. So let me just put that this is in quadrant 3. Now, an easier way to do that, if you're struggling with that, you can always convert it over into degrees. Way easier to do. So I'm just going to say it's 6 pi over 5 times, I'm going to go 180 degrees over pi. And so basically the pi's are going to cancel. And so 180 divided by 5 is 36. And so you'd have 6 times 36, that's 216. And now this is in terms of degrees. So this is 216 degrees. So I think a lot of people will find this easier to work with. And also immediately you know that this is going to be in quadrant 3. Whereas with 6 pi over 5, you really have to think about it because it's in terms of radians. I've already sketched this in to help us out. So this guy in orange, which I'm not sure if it comes through so well. So I'm going to try to do a rough trace over what I did. So this would be your angle right here. So this is what I'm looking at. So that's my 6 pi over 5. Now I know that the sine of 6 pi over 5 is going to be negative because it's in quadrant 3. I also know that the reference angle is going to be pi over 5. And the way I figure that out is if I'm in quadrant 3, I take my angle, which is 6 pi over 5, and I subtract away pi. So I'll do that as 5 pi over 5, and that gives me pi over 5. So this guy right here, this reference angle, so this piece right here, that's going to be pi over 5. Now, I know that sine is negative, again, in quadrants 3 and 4. So all I have to do is come over into quadrant 4 and find an angle with a reference angle of pi over 5. But again, I don't want to do this. I don't want this angle right here because I want to rotate clockwise in quadrant 4 when I have a negative argument for my inverse sine function. So I want this guy right here. So I'm going to draw over this, maybe use a different color. So this guy right here, that is going to be negative pi over 5. So I've got my pi over 5 reference angle. So now I want to convert my problem over to where I use something that's going to be in the range of the inverse sine function. So let me get rid of all of this. I think we're ready to go. And all we have to do now is say that the inverse sine of the sine of 6 pi over 5 would be equal to the inverse sine of, again, I'm going to convert this over into an angle that's in the range of the inverse sine function. And so I'm going to say it's the sine of negative pi over 5. Because again, the sine of 6 pi over 5 and the sine of negative pi over 5, those are both going to be the same value. They're both in quadrants where sine is negative, so they're negative in quadrants 3 and 4, and the reference angle is pi over 5 in each case. So all I have to do now is give my answer, as these guys are going to cancel, and I'm left with that angle, which is negative pi over 5. All right, let's take a look at a few examples where we're going to solve some trigonometric equations using inverse trigonometric functions and the cancellation properties that we talked about earlier. So suppose you had something like negative 5 plus 1/2 tangent of negative 2x plus 5 pi over 4, and this equals negative 11/2. Now we want to solve this over the interval from 0 to 2 pi, where 0 is included and 2 pi is excluded. Now earlier in this section, we talked about how we could solve equations of this form, but here we're going to use a different approach. So let me copy the problem. So negative 5 plus 1/2, and then we have our tangent of, this is negative 2x plus 5 pi over 4, and this equals negative 11/2. So let me go ahead and grab this real quick. Just remember the interval that we're solving over. I'm going to come here to a fresh sheet so we have a little bit of room to work. So the idea here is still the same. You want to isolate the tangent of something. In this case, it's negative 2x plus 5 pi over 4. So you want to isolate that on one side. You want a number on the other. So what I'm going to do is add 5 to both sides of the equation. So over here, this is going to cancel away. And I'm going to have 1/2 tangent of negative 2x plus 5 pi over 4. And this would be equal to, over here I have a negative 11/2, and then plus, for 5, let's write that with a common denominator. So let's multiply by 2 over 2. So this would be 10/2. And then now I can add negative 11 plus 10, that's negative 1, put that over the common denominator of 2. So this would give me negative 1/2. Now again, if my goal is to isolate this guy right here, I have to think about the fact that I have that 1/2 that's multiplying that. So to get rid of that, I'm going to multiply both sides of the equation by 2. And so this is going to cancel, and this is going to cancel. And so at this point, what I have is the tangent of this negative 2x plus 5 pi over 4. And this equals, over here I just have my negative 1. So here's where we're going to use our inverse tangent function and the cancellation property that we talked about earlier. So I'm going to take the inverse tangent of each side. So let's start over here. I'm going to say that I have the inverse tangent of this guy right here. So this would be the tangent of negative 2x plus 5 pi over 4. And then this guy over here on the right, you're going to do the same thing. So I'm going to take the inverse tangent of this negative 1. Now again, we have our property where we said that the inverse tangent of the tangent of x, in this case, x is just this guy right here. So this is what's on the inside. We would say that this is equal to x as long as x is greater than negative pi over 2 and less than pi over 2. So we're going to use this property here. And basically, we're going to say that this guy and this guy are going to undo each other or cancel each other, however you want to think about that. And so I'm just going to be left with this part right here. So I'm going to say this is negative 2x. Let me move this down a little bit more. And then plus 5 pi over 4. And this equals the inverse tangent of negative 1. Now, most of you know that's negative pi over 4. But just in case you don't, again, you can always go to the unit circle and think about these things. So for the inverse tangent function, again, you're working from negative pi over 2 to pi over 2 with those values being excluded. So I'm going to make sure that I stop a little bit short there. So those guys are not included. Again, the negative pi over 2 and the pi over 2. And you're just asking the question, where in this interval here am I going to have a tangent value that's going to be negative 1? Well, a lot of you can see that at 7 pi over 4, you have a sine value that's negative square root of 2 over 2 and a cosine value that's square root of 2 over 2. So if you had the tangent of 7 pi over 4, you're dividing opposites, so that's equal to negative 1. Now, we can't put 7 pi over 4 because, again, we have to rotate clockwise here. So you've got to go like this. So this would be negative pi over 4. And, of course, that's coterminal with 7 pi over 4. So the tangent of 7 pi over 4 is equal to the tangent of negative pi over 4, and that equals negative 1. So if I took the inverse tangent, so the inverse tangent of negative 1, that's going to give me this negative pi over 4. Okay, so coming back to this point, what we want to do is solve for x. So now I have this guy that I want to isolate. So let's subtract 5 pi over 4 away from each side of the equation. So of course this is going to cancel. And now I'm going to have negative 2x is equal to, let's write this as negative pi minus 5 pi over the common denominator of 4. So this right here, negative pi minus 5 pi is negative 6 pi. So this is going to be negative 6 pi over 4. Now to simplify this, if you think about 6 and 4, there's a common factor of 2. So 6 divided by 2 is 3, and 4 divided by 2 is 2. So let's go ahead and write this as negative 3 pi over 2. So this is negative 3 pi over 2. Now as a last step, again, I want to isolate x. So what I want to do is think about the fact that negative 2 is multiplying x, so you can divide both sides by negative 2. Or since you have a fraction here, it's probably going to be a little bit easier if you multiply both sides by negative 1/2. So multiply both sides by negative 1/2. So of course you could write this as negative 2 over 1. And this right here would cancel and become a 1. And so you would have x is equal to negative times negative is positive. And then basically you would have 3 pi over 4. So that is only one solution, and that's part of the issue with this technique here. So you have x equals 3 pi over 4. So let's go back up to the top, and let me write that x is equal to 3 pi over 4. So I know that this guy right here is in quadrant 2. You're going to find that you actually have a solution in quadrant 1, 2, 3, and 4 with this problem. And the way I know that is I would look at the period of this guy, so I know how often these solutions are going to repeat. Again, the standard period for tangent is going to be pi. So when you look at y is equal to the tangent of x, well, the period for that guy is going to be pi. But if you have y is equal to something like the tangent of bx, well, then the period is now going to be pi over b, but that's when b is positive. In this case, you're going to have a negative here, so you can adjust the formula and say pi over the absolute value of b. So for this case, you have this negative 2 that's multiplying x. So the period for this guy would be pi over the absolute value of negative 2, which would be pi over 2. So that's going to be the period. Let me get rid of this. So let me put this like this, and let me put that the period is pi over 2. And actually, let me grab this real quick. It's going to come down here to the unit circle and rewrite things. So x is equal to 3 pi over 4. Again, this is in quadrant 2, and I'm going to put that the period. So the period is pi over 2. I think you can do it on the unit circle the first time just so you can get a visualization of what's going on. So I know that solutions repeat every pi over 2. So here I'm going to be at 3 pi over 4. So what I want to do is actually subtract away pi over 2 and find my solution in quadrant 1. A lot of you know that's going to be pi over 4. Well, let's go ahead and do the work here. So we have 3 pi over 4 minus pi over 2. Let's go ahead and write this as 2 pi over 4. So we can have a common denominator. So minus 2 pi over 4. And so this would give me, again, pi over 4. So that's a solution in quadrant 1. Now, if I want the solution in quadrant 3, then what I would do is actually take my 3 pi over 4. So 3 pi over 4. And I'm going to add 2 pi over 4. And that's going to give me 5 pi over 4. So that's going to be right here. And then in quadrant 4, of course, it's going to be 7 pi over 4, but let's just go through it. We would have the 5 pi over 4, this guy right here, and we're adding our pi over 2, or 2 pi over 4. So we have 5 pi over 4 plus 2 pi over 4. So that's 7 pi over 4. So those are your solutions in that interval that I gave. If we have x being greater than or equal to 0 and less than 2 pi, well then x is going to be equal to pi over 4. And then you have 3 pi over 4. And then you have 5 pi over 4. Let me scooch this down a little bit. And then you have 7 pi over 4. Then in terms of the general solution, if you did want that, although it didn't ask for it, you could start with pi over 4. So start with something like pi over 4. And then you could just add pi over 2 to get to the next solution, and then add pi over 2 to get to the next solution, and then add pi over 2 to get to the next solution, and add pi over 2 to get to the next solution, and that will continue forever and ever and ever. So pi over 4 plus your pi over 2 times n, where n is any integer. All right, one thing that I find helpful, especially for beginner students, is to look at a graph of an equation after you solve it. So you can go to Desmos. So I would say that you have 1/2 and then tangent of negative 2x plus 5 pi over 4. And then you have this negative 5 here. So let me write minus 5. I'm going to add this to both sides. So I'm going to add 11/2 over here. And then this would be equal to 0 because I added it over here as well. So this right here, this negative 5, that's negative 10 over 2. So this is negative 10 over 2. And negative 10 plus 11 is going to be positive 1. So this right here would be plus 1/2. So the way you would key this into Desmos is you would say that y is equal to this. And of course, if I plug in a 0 for y, now I'm just finding my x-intercepts, or the x values that make the y value 0. So I have the graph set up for us. Again, this is y equals 1/2 tangent of negative 2x plus 5 pi over 4 plus 1/2. So if you want to key that into Desmos, again, if I plugged in a 0 for y, now I'm looking for the x-intercepts. So where are the x values that make the y value 0? And of course, you're going to see this is consistent with what we found. So here you have your pi over 4, your 3 pi over 4, your 5 pi over 4, your 7 pi over 4. So that's in the interval that we solved in from 0 to 2 pi, where 0 is included and 2 pi is excluded. And then you would continue with this pattern forever. So you can keep just adding pi over 2 to your solution to get to the next one. So 7 pi over 4 plus pi over 2, or you could say 2 pi over 4, that's 9 pi over 4, then 11 pi over 4, then 13 pi over 4, then 15 pi over 4, then 17 pi over 4, so on and so forth. All right, let's go ahead and look at another example. So here we have 40 sine of beta minus 3, then plus 1 is equal to 6. Again, we want to solve this over the interval from 0 to 2 pi, where 0 is included and 2 pi is excluded. So we're going to have 40 and then sine of this beta minus 3, and then plus 1 is equal to 6. So let me go ahead and grab this. Let's come down to a fresh sheet here. And again, my goal to start is to get the sine of this beta minus 3 on one side by itself. So I want to isolate that. So in order to do that, I'm going to start by subtracting 1 away from each side of the equation. So this would cancel. And so now we're going to have 40, and I'm going to put times the sine of this beta minus 3, and this would be equal to 6 minus 1 is 5. Again, I want to isolate this right here. So you have 40 that's multiplying that. So all I'm going to do is divide both sides of the equation by 40. So of course, this is going to cancel. And now you're going to have the sine of this beta minus 3 is equal to, when you think about 5 divided by 5, that's 1, and 40 divided by 5 is 8. So this is 1/8. Now, I've got to get this guy by itself. And in order to do that, I've got to get rid of this guy right here. So I'm going to use my property from earlier. Remember that if you have the inverse sine, so the inverse sine of the sine of x, this equals x, as long as x is within the domain of the restricted sine function. So we would say for x being greater than or equal to negative pi over 2 and less than or equal to pi over 2. So here I'm just going to take the inverse sine of each side and use this rule here. So let me actually get rid of this. And I'm going to say that I have the inverse sine of this guy right here. So the sine of my beta minus 3. And this equals, again, I'm going to do that over here as well. So the inverse sine of 1/8. So at this point, we know that this will undo this. So those are going to cancel, and I'm left with my beta minus 3. And this equals my inverse sine. So my inverse sine of 1/8. Now at this point, you can give one solution for beta. You could just add 3 to both sides of the equation. And so this right here is going to cancel. And you're going to say that beta is equal to the inverse sine of 1/8 and then plus 3. So this is only one solution. To get the other solution, what you're going to have to do is think about your angle in quadrant 2 that has a sine value of 1/8. So what do I mean by that? Remember that if you have the inverse sine of something that's positive, so this is a positive argument, you're going to get something in quadrant 1. And actually, you're going to get this angle right here. Let me try to trace over this as best as I can. So that angle right there, if you're working with radians, that's going to be, let me put the inverse sine of 1/8 is about 0.125 in terms of radians. If you want to work with degrees, it would be about 7.18 degrees. So that's going to be for that angle right there. Let me just put this in so everybody knows what that is. So this is going to be about 7.18 degrees or 0.125 radians. Now, where is the sine value also going to be 1/8? Well, again, in quadrant 2, where I have a reference angle of 7.18 degrees or 0.125 radians. So you want this angle right here as well. So this angle right here as well, which again would have that same reference angle. So if I go down like this, this would be about 7.18 degrees or 0.125 radians. Now, how do I get this angle right here? So this is the angle. If I look at it, well, all I have to do is take the straight angle, which is pi, and subtract away this part right here. So you could do that by saying that you have your beta is equal to pi minus the inverse sine of 1/8. So again, that's taking this piece out, and then plus 3 like that. So let me go ahead and grab this real quick. And so we have these two guys here. And basically all I'm going to do is combine them into one little nice solution. So I'll just put a comma here. You can also use solution set notation if you want. Now, if you wanted to give the general solution, then basically all you'd have to do is say this guy plus 2 pi n where n is any integer, and then this guy plus 2 pi n where n is any integer, because your solutions are going to repeat every 2 pi. Now, if you want, let me go ahead and grab this real quick. Let me paste this in. If you want to verify these solutions, again, you can sketch the graph of this guy. The way I would do it is, I would say that you have y is equal to 40 sine of beta minus 3. And then I would subtract 6 away from each side. So I would say minus 5. So basically, if you subtract 6 away from each side here, you would have this part right here is equal to 0. I'm replacing the 0 with y, so I can graph this guy. And again, if y is 0, you're looking for the value for beta, or you could put an x here if you want for graphing purposes. So you're looking for the value for x such that the y value is 0. So you're looking for the x-intercepts. Now, in terms of approximating this, again, the inverse sine of 1/8, that's going to be about 0.125. And then if you add 3 to that, you're going to get about 3.125. So let's say that beta is about 3.125. So if you key this into your calculator, you're going to get about 6.01, let's just say 6. So 6.016 like that. Let me just grab this real quick. So coming down to the graph, again, you can sketch this on Desmos. This is one of the solutions we found, so about 3.125. This is another one, so this is about 6.016. So that's all in the interval from 0 to 2 pi, where 0 is included and 2 pi is excluded. And of course, if you wanted other solutions, if you wanted to give the general solution, everything is going to repeat every 2 pi. So if you take this solution and you add 2 pi, you're going to get to this solution here. If you take this solution and you add 2 pi, you're going to get to this solution here. All right, let's change things up. And now we're going to look at some problems that involve solving equations where you have an inverse trigonometric function involved. So here we have 3/4 times the inverse cosine of x over 2, and this equals pi over 4. Now for this type of problem, what you want to do is isolate your inverse cosine function. So I want inverse cosine of, in this case, x over 2, on one side and I want a number on the other. So let's go ahead and just copy the problem. So 3/4, I'm going to put times the inverse cosine of this x over 2, and this equals pi over 4. If I want to isolate this guy right here, we'll have 3/4 that's multiplying this guy. So what I'm going to do is multiply both sides of the equation by the reciprocal of 3/4, which is 4/3. Remember that a number times its reciprocal will always give you 1. So when I multiply 4/3 times 3/4, those guys are going to cancel and give me a big fat 1. So now the left side is just what I want. It's the inverse cosine of this x over 2, and this is equal to, over here, the 4s would cancel, and so you would have pi over 3. Now, at this point, you could probably solve this by inspection. You can just look at this and say, well, the inverse cosine of 1/2 would be pi over 3, so I know x is going to end up being 1. It's a really easy equation. But if you didn't know that, what could you do to get your solution? Well, there's two strategies you could use. The first thing is you can go back to what we talked about earlier with the cancellation property. So if you have something like the cosine of the inverse cosine of, let's just say x. Right now we have x over 2, but let's just say x. This would be equal to x as long as this guy is within the domain of the inverse cosine function. So as long as x is greater than or equal to -1 and less than or equal to +1. Now, we're just going to use that here, and then I'll show you an easier way to do it. So I'm going to take the cosine of each side. So the cosine of the inverse cosine of x over 2 is equal to, I'm going to take the cosine of this side as well, so the cosine of pi over 3. So at this point, I'm just going to cancel this with this. These guys will undo each other, and you're going to have x over 2 is equal to, the cosine of pi over 3 we know is 1/2, and at this point, you know that x is 1, right? The denominators are equal, so you could, if you wanted to, just multiply both sides by 2. Let's just go ahead and clear the denominators away to make this official. So this guy would cancel with this guy, and this guy would cancel with this guy, and you get x is equal to 1. An alternative approach, if you get something like this, let me get rid of this right here, is to do this in a simpler way. So you'll probably see this technique in your textbook. You know that if you have the cosine of pi over 3, you get 1/2. So this is the angle, this is the cosine value. Then you also know that the inverse cosine of 1/2, so that's the cosine value, this is going to give you the angle, again, between 0 and pi, where 0 and pi are both included, where that cosine value is 1/2, so this is pi over 3. So if I look at this, the inverse cosine of x over 2 is equal to pi over 3. Well, this is your cosine value, and this is the angle. So all I really have to do is say, well, that means that the cosine of the angle, pi over 3, is equal to, again, this is the cosine value. So this is x over 2. So you can kind of shortcut that process and just set it up this way, just using the basic definition for cosine and inverse cosine. So once I look at this, I know that the cosine of pi over 3 is, again, 1/2. So this becomes 1/2 is equal to x over 2, and that just becomes x is equal to 1. Now with these problems, I always suggest checking them. You'll get a lot of problems that they throw at you with no solution here, or they get really tricky. So always check your problems here. So what I would do is plug in a 1 for x and see if I get a true statement. So you get 3/4 times the inverse cosine of 1/2 is that equal to pi over 4. So the inverse cosine of 1/2 is going to be pi over 3. So you would have 3/4 times pi over 3. Is that equal to pi over 4? Yes, it is. If you cancel this with this, you would have pi over 4 is equal to pi over 4. So x equals 1 is a valid solution. All right, so again, I'm going to recommend that in this particular section, you look at the graph of everything just so you can confirm things. So I went ahead and just rearranged the equation so I could get y equals 3/4 times the inverse cosine of x over 2, and then minus pi over 4. So the equation was 3/4, and then cosine inverse of x over 2, and that was equal to pi over 4. So I just subtracted pi over 4 away from each side. So that would give you minus pi over 4, like this, and that would be equal to 0. So again, all I'm doing is I'm plugging in a 0 for y, and I'm saying for which x value am I going to get a y value of 0? So where's the x-intercept? If you look at the graph, where you're going to see that occurs right here, where you have a 1 for your x value and a 0 for your y value, so the ordered pair 1, 0. And again, that just confirms our solution that x is going to be equal to 1. All right, let's take a look at another one. So here we have 1/2 times the inverse cosine of x over 4. This is equal to pi. So in this particular case, again, I'm trying to isolate the inverse cosine function first. So here, the inverse cosine of x over 4. So let me just write 1/2 times the inverse cosine of x over 4. And this would be equal to pi. Now, if I want to isolate this guy, I need to get rid of this 1/2 that's multiplying it. So I'm just going to multiply both sides by 2. And so we're going to see that this right here is going to cancel with this right here. So now I have my inverse cosine of x over 4 That's on the left. It's isolated. And this equals pi times 2 is just 2 pi. Now let's stop for a moment and think about this. Is there going to be a solution for x? Is there something that I can plug in there, divide by 4, and then take the inverse cosine of that and get 2 pi? No, because the range of the inverse cosine function is from 0 to pi, with 0 and pi both being included. So this right here is impossible. So we would say that there's no solution. Right? So there's no solution. Again, if you want to look at this graphically, if you started with 1/2 times the inverse cosine of x over 4, and again, this was equal to pi, so let's put equals pi. Well, I'm going to subtract pi away from each side, so now I'll have minus pi equals 0. Well, again, I'm just plugging in a 0 for y, and I'm saying for which x value am I going to get a y value of 0? So where would I cross the x-axis or get an x-intercept? And you can see that this graph does not cross the x-axis. Basically, it goes from here to here. It's never going to cross the x-axis, so there is no solution. All right, let's take a look at a problem that's a little bit more tedious. So here we have the inverse cosine of 3/5 minus the inverse sine of x, and this equals 0. So if you get a problem like this, what I would do is I would isolate the inverse sine of x. So in other words, right now you have minus the inverse sine of x. So I would add the inverse sine of x to both sides of the equation. So let me just show that real quick. So I'm going to add the inverse sine of x on the left, and I'm also going to add the inverse sine of x on the right. So this would cancel away. So what I would have here is the inverse cosine of 3/5 is equal to the inverse sine of x. So I'm actually going to write this one on the left. That's just my preference. So I'm going to write the inverse sine of x is equal to the inverse cosine of 3/5. Okay, I'm going to come down to a fresh sheet so we have a lot of room to work. So what I'm going to do is actually take the sine of each side. So I'm going to say that I have the sine of the inverse sine of x, and this equals, I'm going to take the sine of the inverse cosine of 3/5. When I think about taking the sine of, again, the inverse sine of x, these guys will undo each other as long as x is within the domain of the inverse sine function. So from -1 to +1 with both being included. So x is equal to the sine of the inverse cosine of 3/5. What is the inverse cosine of 3/5? Again, that's an angle in quadrant 1, because this guy is positive, where the cosine value is going to be 3/5. So what I can do is say that I'm going to let something like theta be equal to the inverse cosine of 3/5. So again, this angle theta is going to be in quadrant 1 because the inverse cosine of something that's positive is going to give me something in quadrant 1. So I'm going to say that theta is in quadrant 1. Additionally, we know that this right here is the cosine value. So I can say then that the cosine of this theta is going to be 3/5. So what am I really trying to find for x here? Well, it's the sine of, again, the inverse cosine of 3/5. Well, the inverse cosine of 3/5 is theta. So really, I'm just trying to find the sine of theta. So you could really write this as x is equal to the sine of theta. How do we figure out what the sine of theta is? Again, if I know the cosine of theta is 3/5, and I know theta is in quadrant 1, this is really easy to figure out. So this right here is your adjacent, and this right here is your hypotenuse. Remember, for cosine, it's adjacent over hypotenuse. Again, you could also say that this is your x over your r. For the sine of theta, this is going to be your opposite over your hypotenuse, or you could write that as your y over your r. Well, I know that the r, or the hypotenuse in this case, is 5, so I can just put that in there. And again, you could just use your Pythagorean theorem to figure out what y is, or the opposite. A lot of you already know it's going to be 4, because this is a 3, 4, 5 right triangle. But again, you can always make a sketch. Now, for this one, it's very easy, so maybe you don't need a sketch, but I'll just go ahead and make one for completeness. So the adjacent is going to be 3. So you could say this is your x here, so x is 3. Your hypotenuse is going to be 5. So I'm going to say this is your r is 5. And of course, the opposite, or your y, is going to end up being 4. But when we first solve the problem, we don't know that. So what you would do is say that you have x squared plus y squared is equal to r squared, just coming from the Pythagorean theorem. And so we know x is going to be 3. So 3 squared is 9. And then plus y squared. Again, at this point, y is unknown. And this equals, we know r is 5, so 5 squared is 25. So what I would do at this point is subtract 9 away from each side of the equation. This cancels, you get y squared is equal to 25 minus 9 is going to be 16. And at this point, I would say that y is equal to the principal square root of 16, which is 4. You would use the principal square root here because you're in quadrant 1 and y values are positive. So coming back here, this would be a 4. So x equals the sine of theta, and the sine of theta is 4/5. So you can just say that x is going to be equal to 4/5 here. Now, how would you check something like this? Remember that theta is an angle whose cosine value is 3/5 and whose sine value is 4/5. So coming back up here, again, if you plugged in a 4/5 there, you'd have the inverse cosine of 3/5 minus the inverse sine of 4/5. Does that equal 0? So essentially what you have is, let's just say this is theta. Well, this would also be theta. It's the same angle, right? So the cosine of this angle is 3/5, and the sine of this angle is 4/5. So it's just theta minus theta is equal to 0. So you get 0 equals 0. So this 4/5 is a valid solution for x. Again, you can always go to Desmos and verify this solution graphically. So if you do something like y equals the inverse cosine of 3/5 minus the inverse sine of x, again, if you plugged in a 0 for y, I'm asking for which x value am I going to get a y value of 0, and that's going to occur at 4/5, 0. So this right here is your x-intercept, again, where y is 0. So that confirms our solution that x is going to be 4/5. All right, now let's look at something that's very tedious overall. I'm just going to tell you that you're definitely going to get problems like this in your textbook, and they take quite a while to solve, especially if you're doing this the long way. I'll also tell you that for most of these problems, there's an associated identity that you can use to greatly speed up your work. I would suggest for the first few times that you solve this type of problem, that you do it the long way so you can get a full understanding of what's going on. And then later on, when you come across these problems again, you can just use the identities and go a lot faster. All right, so let's look at the inverse sine of x minus the inverse cosine of x, and this equals pi over 6. So what should we do first if we get a problem like this? Pick one of these guys. So it could be the inverse sine of x or the inverse cosine of x, and you're going to isolate that on one side. So in this case, I'm going to isolate the inverse sine of x, and to do that, I'm just going to add the inverse cosine of x to both sides of this equation. So I'm going to go ahead and show this as canceling. So now I'm going to write this as the inverse sine of x is equal to, over here I'm going to have the inverse cosine of x, and then plus pi over 6. Now I'm going to end up taking the sine of each side, but before I do that, let me just grab this real quick and let me paste this in. I want to write this in a way to where it's crystal clear what we're doing and what everything means. So I'm going to make a little substitution. You've seen me do that already. So the inverse cosine of x, we know that that's an angle from 0 to pi, where 0 and pi are both included, where the cosine value is x. So in other words, I can let something like theta, or in this case, let's just use beta. So let's let beta be equal to the inverse cosine of x. So then what I can say is that the cosine of beta is going to be equal to x. I know that in terms of beta, right now, just looking at this, beta is going to be from 0 to pi, where 0 and pi are both included. That's coming from the range of the inverse cosine function. So let me say that beta is greater than or equal to 0 and less than or equal to pi. So I'm just going to change this from the inverse cosine of x to beta. So I'm going to erase this and just put this right now as beta. Okay, let's put this over here like this. Now there's something else that you have to consider. Let me actually grab this and slide it down right here. If I have the inverse sine of x, that's going to give me something from negative pi over 2 to pi over 2, where both of those guys are included. So that tells me that this right here, this beta plus pi over 6, has to be greater than or equal to negative pi over 2 and less than or equal to pi over 2. I'm going to put this in terms of beta being in the middle of that guy. So to do that, I'm just going to subtract pi over 6 away from each part of this guy. Over here, let me just add negative pi over 6. That would be the same thing. So basically, this would cancel. And over here, I'd want to get a common denominator. So multiply this by 3 over 3. And over here, I'd multiply this by 3 over 3 as well. So I would end up with negative pi plus negative 3 pi over the common denominator of 6. So that's negative 4 pi over 6. So this would be negative 4 pi over 6. And of course, each guy here is divisible by 2. So 4 divided by 2 is 2. So this would be negative 2 pi over 6 divided by 2 is 3. So let me erase all of this and put this as negative 2 pi over 3. And let me erase this. And over here, let's think about what we have. So this would be 3 pi minus pi over the common denominator of 6. So this would be 2 pi over 6. So 2 pi over 6. Each is divisible by 2. So 2 divided by 2 is 1. 6 divided by 2 is 3. So this is pi over 3. So this is pi over 3. Let me actually write this up here. And I'm going to write this a little bit more concisely. And let me come back up here. And let me paste this in here. And I'm just going to arrow to that guy right there. So we know that both of these would actually have to be true. Because beta is equal to the inverse cosine of x, I know that beta has to be greater than or equal to 0 and less than or equal to pi. But then it would also have to be true that beta is greater than or equal to negative 2 pi over 3 and less than or equal to pi over 3 because of this right here. So the inverse sine of x equals this beta plus pi over 6. So what you actually have to do is put these two guys together using the keyword and. So you're trying to find the intersection of the two. So if you consider these guys together, so I'm going to use the keyword and here. So beta is greater than or equal to 0 and less than or equal to pi. So that would look like this graphically. So here's 0 and here's pi. Again, that's about 3.145. Let's just say it's about right there. So this would be about pi right there. So this is what that looks like if you were to graph that inequality. Then for this one, beta is greater than or equal to negative 2 pi over 3 and less than or equal to pi over 3. Well, let's say that this right here is about negative 2 pi over 3. And let's say that this right here is about pi over 3. Just in case you're curious, negative 2 pi over 3 is about negative 2 point, let's say 0.9. And pi over 3, that's about, let's say 1.05. So graphically, this would look like this right here. So this right here, if you want to look at that inequality, so something like that. So if I want the intersection of the two, again, I'm looking for values that are going to work in both. In other words, it would have to satisfy this one and this one. So when I set that up, I'm running out of room, but let me just do it over here. I would say that beta is greater than or equal to what? Well, consider that over here, you have a 0, and over here, you have a negative 2 pi over 3. Well, it's got to be 0. It's got to be the one that's more restrictive or further to the right, because it's got to work in both. If I had a value that was, let's say here, that was to the left of 0, but to the right of negative 2 pi over 3, well, it would work in this one, but it wouldn't work in this one. So I'm going to have to choose 0 here, and then I say it's less than or equal to. Well, for this one, I want the one that's further to the left, right? Because it's going to be more restrictive and include fewer values. So I want the pi over 3. In other words, if I had something like, let's say 2, that was to the right of pi over 3, well, it works in this one, but doesn't work in this one. So it's got to work in both. So I'm going to choose pi over 3. Okay, let me come down here, and I'm going to paste this in. And I'm coming back to this in a second. And let me grab this, and let me come down here and paste this in. So we're going to need this identity. That's why I have that set up already. So what I'm going to do now is take the sine of each side. So I'm going to take the sine of the inverse sine of x, and this is equal to the sine of beta plus pi over 6. When I think about this guy right here, again, from the cancellation property that we talked about earlier, this will undo this as long as x is in the domain of the inverse sine function. So from -1 to +1 with both being included. So let's go ahead and say that x is equal to this guy right here. So the sine of beta plus pi over 6. Now, I'm going to erase this, and now we're going to use this sum identity for sine to simplify this. So what I'll do is say that this is x is equal to, again, if you have the sine of a plus b, it's equal to the sine of a times the cosine of b plus the cosine of a times the sine of b. So this would be the sine of the first guy, which is beta, and then times the cosine of the second guy, which is pi over 6, and then plus the cosine of the first guy, which is beta, and then times the sine of the second guy, which is pi over 6. Now, I know most of you know this, but if you go to pi over 6 on the unit circle, the x-coordinate is the cosine value, so that's square root of 3 over 2, and the y-coordinate is the sine value, so that's 1/2. So coming back up here, I can replace the cosine of pi over 6 with square root of 3 over 2, and I can replace the sine of pi over 6 with 1/2. So this right here is 1/2. Now, we also know what the cosine of beta is. So the cosine of beta, again, is going to be x. So this right here is going to be x. All right, so we're just going to plug some things in. So we have x is equal to, I'm going to go square root of 3 over 2 times your sine of beta, and then plus, here you're going to have 1/2 times the cosine of beta, which is x. So this is just x over 2. So this right here is x over 2. Now you have a common denominator. So what I'm going to do is actually say x is equal to the square root of 3 times the sine of beta plus x over the common denominator of 2. So the question now is, what is the sine of beta? So that's the holdup. So what is the sine of beta? So again, this is the opposite over the hypotenuse. Do we know what the hypotenuse is? Remember, the cosine of beta is equal to your x over 1, right? Because x can be written as x over 1, and this right here is your adjacent, and this right here is your hypotenuse. So I know the hypotenuse is 1, so let me put that there. Now, what about the opposite? Can I figure that out? Remember that we said that beta is greater than or equal to 0 and less than or equal to pi over 3. So I'm just going to sketch a triangle in quadrant 1, and it would look something like this. So your adjacent is just going to be x, your hypotenuse is going to be 1, and you're going to find through the Pythagorean theorem that the opposite is going to be the square root of 1 minus x squared. So again, if you want to go through this, let's say that we label this right now generically as y. So we would say that we have x squared. So I'm just calling this length right here x, so it's x squared. Plus, I'm going to have this guy right here. Let's call that y. So y squared is equal to this guy right here, your hypotenuse. We know that's 1, so 1 squared. You're going to solve this for y. So you're just going to subtract x squared away from each side of the equation. I'm just going to erase this. And then to solve for y, you want the principal square root of this guy right here. So 1 squared is just 1 minus x squared. And the reason for that is, again, your y value is never going to be negative because beta is greater than or equal to 0 and less than or equal to pi over 3. So you use the principal square root here. So this right here is what you're going to get for your opposite, the square root of 1 minus x squared. Let me actually move this over. I don't think it'll fit. I'm just going to say that this is the square root of 1 minus x squared. Let me make this a little bit longer here. So this is over 1. So what I would do now is plug this right here in for that sine of beta, and then we would just solve for x. What I want to do is say that x is equal to the square root of 3, and then times, again, for the sine of beta, I have the square root of 1 minus x squared. If you want, you can combine those now. I think it'll make it a little bit easier to understand. Again, if you have the square root of a times the square root of b, we know this is the square root of ab. So the square root of 3 times the square root of 1 minus x squared would be the square root of 3 times the quantity 1 minus x squared. And if you distribute that 3 into each guy, you would have the square root of 3 minus 3x squared. So again, 3 times 1 is 3, and then minus 3 times x squared, that's 3x squared. Let me make this a little bit better here. And let me erase this and also erase this. So then we would say plus, you have this x here, and then this is over 2. Now, I want to grab this guy right here, and let me come down to this sheet here. The reason I'm keeping this here is because we're going to end up squaring both sides of our equation, and we want to remember that our angle beta, which represents the inverse cosine of x, that is greater than or equal to 0 and less than or equal to pi over 3, so I know that my x values here are greater than 0. So just keep that in mind. So for this one right here, I'm going to multiply both sides by 2. Let me put a little border and section this off. So multiply over here by 2. And of course, this is going to cancel away. And so now we'd say that we have 2x is equal to the square root of 3 minus 3x squared, and then plus x. At this point, I would subtract x away from each side of the equation. And so this right here is going to cancel. So 2x minus x is x. So x is equal to the square root of 3 minus 3x squared. Now, I want to square both sides. So what that would give me, let me come down here a little bit, is x squared is equal to the square root of 3 minus 3x squared. And again, I'm squaring this as well. So just squaring both sides of our equation. And that's going to give me x squared is equal to, so you're left with that radicand there. So 3 minus 3x squared. Let me make this 3 a little bit better there. So at this point, I just want to add 3x squared to both sides of the equation. This is going to cancel. And so you have x squared plus 3x squared. That's going to give me 4x squared. And this equals, over here I just have 3. Now, if you want to solve for x, you divide both sides of the equation by 4. This would cancel. You're going to get x squared is equal to 3/4. Now, here's where we need to think. Remember, with the square root property, we would say that x is equal to plus or minus the square root of 3/4. So this turns into plus or minus the square root of 3. So the square root of 3 over 2. Do I need the plus or minus here? No, because again, I cut it off, but we said that beta, which was our inverse cosine of x, is greater than or equal to 0 and less than or equal to pi over 3, which told me that x is going to be greater than 0. So what this tells me is that I don't need the negative of the square root of 3 over 2. That guy is not going to work. It's going to be an extraneous solution. It's something that was produced because we squared both sides of our equation. So you just get x equals the square root of 3 over 2. All right, so for these problems, again, I always recommend you check them. So let's put x is equal to the square root of 3 over 2. Let's just make sure that it works. Again, if you were to try to check x equals the negative of the square root of 3 over 2, the extraneous solution there, it's not going to work. Remember that x values would be positive when we're dealing with this angle beta. So what I would think about here is, what is the inverse sine of this square root of 3 over 2? A lot of you know that it's going to be pi over 3. We'll go to the unit circle and grab it. And then what is the inverse cosine of square root of 3 over 2? Most of you know that's pi over 6. So let's put this as pi over 3. Let's put this as pi over 6. Let's go to the unit circle real quick, just in case you need it. So again, for the inverse sine of square root of 3 over 2, I'm working from negative pi over 2 to pi over 2. And I'm looking for a sine value of square root of 3 over 2. So that's going to be right here, right here. And the associated angle, again, in this interval from negative pi over 2 to pi over 2 is going to be pi over 3. So that tells me that the inverse sine of the square root of 3 over 2, again, is pi over 3. And then for the inverse cosine of the square root of 3 over 2, again, with this one, now I'm working from 0 to pi. Both of those are included. So from 0 to pi. And again, where do I have a cosine value of square root of 3 over 2? Well, that's going to be right here at pi over 6. So this would end up being pi over 6. All right, so now let's just plug in. So the inverse sine of square root of 3 over 2 is pi over 3. So that is pi over 3. And then you'd have minus the inverse cosine of square root of 3 over 2. That's pi over 6. Does this equal pi over 6? Well, if I get a common denominator here, I'd multiply this by 2 over 2. And so that would give me 2 pi minus pi over the common denominator of 6. Does that equal pi over 6? Yeah, 2 pi minus pi is pi. So this would be pi over 6 is equal to pi over 6, which is a true statement. So that solution x equals square root of 3 over 2 is a valid solution. Again, you can always verify this graphically. So you can set this up as y equals the inverse sine of x minus the inverse cosine of x minus pi over 6. Where did that come from? Again, if you have your inverse sine of x minus your inverse cosine of x is equal to pi over 6. Well, if you subtract pi over 6 away from each side of the equation, this would become minus pi over 6 is equal to 0. So all I'm really doing here is plugging in a 0 for y, and I'm asking for which x value am I going to get a y value of 0. So again, that's going to be your x-intercept. So here that occurs at square root of 3 over 2 comma 0. So that tells me the x value is square root of 3 over 2. So this confirms my solution that x equals square root of 3 over 2. In this lesson, we want to talk about solving trigonometric inequalities. All right, let's go ahead and look at the first problem. So this will be a really simple example just to get started. So we want to solve for x is greater than or equal to 0 and less than 2 pi. And so we have 4 minus the sine of x is greater than 7/2. So how do we solve something like this? In this particular case, it's a very simple example. So you could isolate the sine of x on one side and then have a number on the other. And then you can go to the unit circle and get your solution that way. I'm not going to actually do that because I want to build up the concept that we're going to use for the harder examples. So what I'm going to actually do is make the right side 0 to start. So I'm going to say that I have, let's just reorder this, the negative of the sine of x and then plus 4. I'm just going to leave a space here and put this is greater than 7/2. Now, if I want the right side to be 0, I just need to subtract 7/2 away from each side of the inequality. I would want a common denominator. So let me multiply 4 over 1 times 2 over 2. And let me put this minus sign down here. So at this point, I'm going to write that I have the negative of the sine of x. And then basically, this 4 times 2 is 8. So this would be 8 over this 2. So 8 over 2, that's the same thing as 4. We're just getting a common denominator. And 8 over 2 minus 7 over 2, we do 8 minus 7, which is 1, over the common denominator of 2. So that's just 1/2. So this is plus 1/2, and then this is greater than 7 halves minus 7 halves is obviously 0. At this point, what I would do is get rid of this negative that's in front of the sine of x. I'm actually going to write this as -1 times the sine of x, so it's crystal clear what we're doing. I'm just going to multiply both sides of the inequality by -1. Remember, if you do that, you have to flip the direction of the inequality symbol. So let me write -1 times this -1 times the sine of x, and then plus, you're going to have your 1/2 times -1. This is going to get flipped. So right now it's a greater than. Because we're multiplying both sides by a negative, it's going to become a less than. And then you have 0 times -1. So -1 times -1 is +1. So this is just the sine of x now. And then you have 1/2 times -1, that's -1/2. And then this is less than. 0 times anything is 0. So I'm going to grab this real quick. Okay, so at this point, I'm just going to come to the unit circle and put a little border here. Now this is an easier example, so of course you could just figure out, well, where's the sine of x less than 1/2 just by adding 1/2 to both sides. I'm not going to do that because again, I want to build up the method that we're going to use with the more challenging scenarios. But once you have everything down in terms of what method to use when, you can go ahead and solve it that way. It's no problem. So I'm going to write down that we want to find the critical values here. And how do we do that? Again, you replace your inequality symbol with equals. So you would have the sine of x minus 1/2 is equal to 0, add 1/2 to both sides, and you get the sine of x is equal to 1/2. So basically, the solutions there, if we're working in that interval, let me write that out so we know, we're working from 0, and 0 is included, out to 2 pi, and 2 pi is excluded. Well, your solutions there, you're going to have pi over 6, you have a sine value of 1/2, and then also 5 pi over 6, you have a sine value of 1/2. So when I write down that the critical values are going to be where x is going to be pi over 6, and then 5 pi over 6. The reason we want to know that is we want to know where this guy right here, the left side of this guy, is going to be 0. So basically that acts as a boundary for us, and we're going to be able to set up some intervals on our number line, or you can also do it with a table, or you can do it on the unit circle. You could split this up and say, okay, well, one interval is going to be from 0 to pi over 6, and I'm going to exclude everything for right now. So basically you'd have an interval from 0 to pi over 6. So that's one of them. And then another interval you would take from pi over 6. Let me do this in a different color. So from pi over 6, and I'm going to exclude everything again. So pi over 6 to 5 pi over 6, both are excluded. So let me write another interval is pi over 6 to 5 pi over 6, both being excluded. And then a final interval here, you would take from 5 pi over 6 going to 2 pi, again, with both being excluded there. So let's say a final interval would be 5 pi over 6, going out to 2 pi, both excluded. And I have that written more neatly with a little table. Again, if you want to use a number line, it's really up to you. So all you have to do is pick something in each interval and test it and see if it works. So you can say true, false, something like that. You can also just figure out the sign. So basically, is it positive or is it negative? So coming back up, that's really easy to do. In this first guy here, so between 0 and pi over 6, is this guy going to be positive or negative? Well, basically, it's going to be negative. So let me put a negative sign there. And then between pi over 6 and 5 pi over 6, would this guy be positive or negative? Well, it would be positive. And then in this interval right here, between 5 pi over 6 and 2 pi, is it positive or negative? Well, it's going to be negative. So coming back, we want to put that it's negative here, it's positive here, and it's negative here. So if you want to put a solution together, you would say that it's going to work here, it's not going to work here, and it's going to work here. In other words, we're trying to figure out where is the sine of x minus 1/2 less than 0. So I'm trying to figure out where it's negative, because that would mean it's less than 0. So here it works. So let me put this in as x being greater than or equal to 0. I'm going to go ahead and include 0 because that's in the interval we're solving over. Again, when I set up my table, I exclude things just to make it simple. So x would be greater than or equal to 0. And you would have less than pi over 6. And then this part right here, it's positive, so we don't want that. Over here, you're going to have this interval. So 2 pi is excluded and 5 pi over 6, they're both excluded. So you're going to say x is greater than 5 pi over 6 and less than 2 pi. So just put this together. Let me slide down a little bit. So let me actually just grab this and move it here. and then grab this and move it here. And I'm just going to use the keyword or. That's all you have to do. Another way you can do this is you can put it in interval notation. So you can put a bracket with 0, and then you're going to go out to pi over 6, and that's going to be excluded. So you use a parenthesis, and then the union with, you're going to use a parenthesis with 5 pi over 6 because it's not included, and you're going to go out to 2 pi, and of course that's excluded, so you're going to use a parenthesis. So this would be your solution. X can be anything that's greater than or equal to 0 and less than pi over 6, or X can be anything that's greater than 5 pi over 6 and less than 2 pi. Okay, you can always look at these things on Desmos if you're a little bit confused or you want a visual confirmation of your solution. So we have y equals the sine of x minus 1/2. Remember, we were solving the sine of x minus 1/2 is less than 0. So all I'm doing here is asking where the y value is going to be less than 0, again, in that interval that I'm solving over. So if I look at 0, which is the start of the interval I'm solving over, you can see that you have a y value that's less than 0. So that's going to continue up to the point where you're not at pi over 6. So anything less than pi over 6. So again, that's where you get the zeros included up to and excluding pi over 6. Then the union with, if you look at anything greater than 5 pi over 6, 5 pi over 6 itself doesn't work because that's where you're at 0. But anything greater than 5 pi over 6 going up to and excluding 2 pi, because that's excluded from the interval we're solving over, that's going to work as well. So you'd put a parenthesis and then again 5 pi over 6 and then out to 2 pi with a parenthesis. Okay, let's take a look at a problem that's a little bit more challenging. So again, we want to solve for x is greater than or equal to 0 and less than 2 pi. We have negative 2 cosine squared x is greater than or equal to 1 plus 3 cosine of x. So again, I want to make the right side 0. In this case, I'm going to start off by actually making the left side 0 because it's easier, and then I'm just going to switch it around. So I'm just going to add 2 cosine squared x to both sides of my inequality here. So this right here would cancel and give me 0 on the left. So you would have 0 is greater than or equal to, let's write this out in front. So 2 cosine squared x, and then plus 3 cosine of x, and then plus 1. Okay, let me slide down here a little bit. Now, what I'm going to do is just rewrite this. So you can basically say that 2 cosine squared x plus 3 cosine of x plus 1 is less than or equal to 0. So that's how I'm going to set it up. If you want to solve it like this, that's fine as well. So I'm going to say this is 2 cosine squared x plus 3 cosine of x plus 1 is less than or equal to 0. All right, at this point, you want to find your critical values. So let me put a little border here and just say that we want the critical values. And again, how do we figure out what the critical values are? Well, basically, you replace this inequality symbol with an equal symbol. So I'm going to solve the equation 2 cosine squared x plus 3 cosine of x plus 1 is equal to 0. Now this guy is quadratic in form. So when you get something like this, generally speaking in a trigonometry class, you can factor it. Sometimes you do have to use the quadratic formula, but generally speaking, you're going to be able to factor. So let's go ahead and set this up because we can solve it with factoring here. So this is a 2, which is a prime number. That tells me this is 2 cosine of x, and this is cosine of x. So that's easy. The last guy here is a 1. And this guy is positive. So 1 is either 1 times 1 or negative 1 times negative 1. But because this guy is positive, I know this is a plus 1 and this is a plus 1. If you want to check it, you do your outer. So that's plus 2 cosine of x. And then your inner is plus cosine of x. So 2 cosine of x plus cosine of x is 3 cosine of x. So you're good to go with the factorization. So at this point, we would use the zero product property. So I would say that 2 cosine of x plus 1. So this factor here, set that equal to 0. Let's go ahead and solve that real quick. I'm going to subtract 1 away from each side of the equation. That cancels. You get 2 cosine of x is equal to negative 1. Divide both sides by 2, and you're going to get that this cancels. So the cosine of x equals negative 1/2. So let me write that the cosine of x is equal to negative 1/2. And then the other guy is the cosine of x plus 1 equals 0. So let me put or. We have the cosine of x plus 1 is equal to 0. You can subtract 1 away from each side of the equation. That cancels. So you get the cosine of x is equal to negative 1. So let me grab this real quick. And let me come down to the unit circle. So we should know these off the top of our head at this point. But just in case you don't, we know that cosine is negative in quadrants 2 and 3. And I'm just looking for where I have a cosine value of negative 1/2. So that's going to be right here. So there's your cosine value of negative 1/2, and that's 2 pi over 3. So then also here's 4 pi over 3, cosine value of negative 1/2. Then for cosine of x being equal to negative 1, well, I have a cosine value of negative 1 only at pi. So let me put here that we're solving over the interval from 0 to 2 pi. So that's clear. And then basically your solutions are x is equal to, you have 2 pi over 3, you have pi, and then you have 4 pi over 3. Now, these solutions are the critical values, and basically we're using this to split the number line up into intervals. So basically, I'm going to exclude everything here. I know a lot of people like to include 0 because it's included in the interval that we're solving over, but just to keep things simple, I am going to exclude everything, and then we'll put things together at the end. So for one interval here, I'm going to go between 0 and let's say 2 pi over 3. So that's one interval. Then another interval, so we're going to go between 2 pi over 3 and pi. And then another interval would be between pi and 4 pi over 3. And then for the final interval here, we'll say between 4 pi over 3 and 2 pi. So again, I'm not going to include any of those guys. Okay, so once again, I'm going to come to a little table. That's what I like to do to organize my information. So you saw that I set these intervals up on the unit circle. So I have between 0 and 2 pi over 3, then between 2 pi over 3 and pi, between pi and 4 pi over 3, and then between 4 pi over 3 and 2 pi. So when you're testing things, don't ever pick the critical values themselves. Just leave those alone. When we think about 0 and 2 pi, that's coming from our interval. So again, we're solving over the interval from 0 to 2 pi. Where 0 is included and 2 pi is excluded. And again, a lot of you are going to ask, well, why did I not include 0 here? You can if you want. This is personal preference. When I set this up, I just exclude everything. And then once I'm done and I'm putting the solution together, that's where I'm going to think about what's included and what's not included. So again, this is up to you. Let me drag this up here out of the way. And then basically, I'm just going to write my inequality. So we have two different forms we can use. So the unfactored form is 2 cosine squared x, and then plus 3 cosine of x, and then plus 1 is less than or equal to 0. So this is the form I would work with if I was using a calculator. Again, you could just pick something in each interval, plug it in and see if it works. And then the form I would use if I'm not using a calculator is the factored form, because it's just easier to work with that if you're not using a calculator. So this was 2 cosine of x plus 1, and then times the quantity cosine of x plus 1. Okay, let me get rid of this unfactored form. Again, you can use that if you want. I'm just going to stick with this one. So we know that a positive times a positive or a negative times a negative is a positive. And we know that a positive times a negative and a negative times a positive would be a negative. I'm going to tell you that this right here, so this right here, this factor, based on what we can plug in, is always going to be positive. So I'm just going to put a plus right here. So basically, if this guy right here is negative, then the whole thing will be negative. And if it's positive, then the whole thing will be positive. Now, let me stop for a minute, because some of you will say, well, why is this factor always positive? I want you to think about the cosine function in general. So if you have the cosine of x, or you could write y equals the cosine of x, the range for that guy, as we know, is going to be from -1 to +1. And so you get this -1 here when you plug in a pi for x. Well, we can't plug in pi here because it's a critical value, so you're not going to be able to use that. So basically, when I think about the cosine of x, well, the smallest I can make this is if I plug in a pi for x and I get a -1, -1 plus 1 would be 0. But it's not going to be 0 because I can't actually choose pi, so it's going to have to be positive here. So I know that. When I look at this factor over here, now I have, let me put this as a little border, we have 2 cosine of x plus 1. So just ask yourself the question, where would it be negative? You can solve a very simple inequality for that. So just say, where is this less than 0? Subtract 1 away from each side of the inequality. That cancels. You're going to get 2 cosine of x is strictly less than -1. So this is less than -1. Divide both sides by 2. And so basically the cosine of x, if that's less than -1/2, then this right here would be negative. And so the whole thing would be negative. And this guy would be satisfied, because if this side right here is negative, or if it's 0, we'll have a true statement. So let's go back up and see where the cosine value is less than -1/2. So that looks like this interval right here. So that would make this negative, and then this interval right here. So right here, so that would make this negative. All right, so coming back to the table, we know that this guy right here would be negative, and this interval right here, so between 2 pi over 3 and pi, and then this interval right here, so between pi and 4 pi over 3. So let me put that in there. So we would satisfy our inequality there, because this side right here would be negative, and that's always going to be less than 0. So in this interval here and this interval here, this factor would be positive, and so the whole thing would be positive, and so that's never going to be less than 0 or equal to 0. You can put a plus here and a plus here to show that. Okay, so to put the solution together, you would think about where this works. So because it's a non-strict inequality, and we allow for the possibility of this guy to be equal to 0, well, 2 pi over 3, pi, and 4 pi over 3, those are all going to work. So if you started off by just listing these in terms of the table, you could start with x is greater than or equal to 2 pi over 3 and less than or equal to pi, and then say or. You could look at this one. So you have x is greater than or equal to pi and less than or equal to 4 pi over 3. Now, of course, you wouldn't write it like this because of the keyword or. What's going to happen is this is just going to be x is greater than or equal to 2 pi over 3 and less than or equal to 4 pi over 3. So let me tighten this down like this. Let me get rid of that and put a less than or equal to here and just drag this over there like that. So this would be your solution. And if you want to list the interval notation, you're going to put a bracket next to 2 pi over 3, and you're going to go out to 4 pi over 3, and you're going to use a bracket there as well because both of these are included. So once again, if you want to look at this on Desmos, just to get a visual idea of what's going on, you can type in y equals 2 cosine squared x plus 3 cosine of x plus 1. And essentially we had the inequality 2 cosine squared x plus 3 cosine of x plus 1 is less than or equal to 0. So you're basically asking, where are the y values either 0, so at your x-intercepts, or less than 0? So if you look for your x-intercepts, again, we already know where that's going to be. You have your 2 pi over 3, you have your pi, and your 4 pi over 3. And then basically you're saying, where is it either there or less than 0? So you can sketch between these guys, and you're going to see it's going to be less than 0. So between those guys. So if you're looking for where it's either 0 or less than 0, you're going to take this section right here. So from 2 pi over 3 going up to and including this 4 pi over 3. So that's why we said the solution was, again, from 2 pi over 3 going up to and including 4 pi over 3. So that's going to be your solution in the interval that we're solving over from 0 to 2 pi, where 0 is included and 2 pi is excluded. All right, let's take a look at one more of these. So we want to solve for x is greater than or equal to 0 and less than 2 pi. We're given cotangent squared x minus 3 cosecant of x plus 3 is greater than 0. All right, so for this one, we're going to use a little identity to clean things up. You'll notice that the right side is already 0, so we're good to go there. One thing that I would note, if you're working with something that's not sine or cosine, you have to think about where your guy is undefined. So if you think about the cotangent squared x and the cosecant of x that you have, let's come down to the unit circle and remind ourselves, if you have something like y equals the cosecant of x, where is that undefined? Remember that the cosecant of x is equal to 1 over the sine of x. So basically, this guy right here cannot be 0. So where is your sine value 0? It's going to be right here at 0, and then right here at pi. So in the interval that we're solving over, the x cannot be the angle 0 or pi, because again, that would be undefined because you'd have division by 0. So let me put here that the domain, and typically we'll list this by saying that basically it's the set of all x such that x is not equal to pi n, where n is any integer. So 0, pi, 2 pi, 3 pi, something like that, because again, you get division by 0. Then if you think about the cotangent of x, so y equals the cotangent of x, and I know we have cotangent squared x, but basically you can extend this to that. Well, when we think about the domain here, so what is the domain here? Well, basically it's going to be the same, right? Because we have the cosine divided by the sine, and so the sine value cannot be 0. So that's going to happen at 0, then pi, then 2 pi, then 3 pi, so on and so forth. So basically it's the same thing. So it's the set of all x such that x is not equal to pi n, where n is any integer. Okay, now if you had, again, cotangent squared x, the same thing would apply because you're just squaring this, so you still can't have division by 0. So that would still apply there if you had y equals cotangent squared x. All right, let's get rid of this. We're going to say that at 0 and pi, this guy's going to be undefined. So I'm going to keep this highlighted for now. And actually, we might do better by just saying undefined. So undefined, and just putting a little note here. So I'm going to put 0 and pi, and that's going to be for in the interval that we're solving over. I'm just going to paste this in here, and I have a little identity set up for us already. So we know that the cotangent squared x is equal to cosecant squared x minus 1. So essentially, this right here matches this right here. So I'm just going to take this right here, and I'm going to plug it in for this right here. So that's all I'm going to do. So let's say that we have cosecant squared x minus 1. Again, this gets plugged in for this. Then minus 3 cosecant of x, and then plus 3 is greater than 0. So you have this negative 1 and then plus 3. So negative 1 plus 3 is positive 2. So let's go ahead and write this as cosecant squared x. and then minus 3 cosecant of x, and then basically plus 2, and this is greater than 0. So at this point, you would want to find your critical values. So the critical values, now this is quadratic in form, and you can solve it with factoring. So let's go ahead and replace this with equals. So you have cosecant squared x minus 3 cosecant of x plus 2 is equal to 0. Now, I would note that, again, with the critical values, you're also finding places where it's undefined. And we know that it's 0 and pi, like we talked about earlier. So you can throw that in the mix now, or you can put it in later, whatever you want to do. But I'm just going to put it in there now so we don't forget. So here what I want to do is factor on the left. So let me go ahead and set this up with some parentheses. Very easy to factor this. So this is cosecant squared x. So it's cosecant of x times cosecant of x. So very easy. This is 2, which is only going to come from either 1 times 2 or negative 1 times negative 2. This is negative right here, so this has to be negative 1 and negative 2. Let me make that a little bit better. If you check, the outer here is negative 2 cosecant of x. And the inner here is minus cosecant of x. Well, negative 2 cosecant of x minus cosecant of x is negative 3 cosecant of x. So this is the correct factorization. Okay, let me slide down here a little bit. And essentially, you want to find cosecant of x minus 1 equals 0. Add 1 to each side. You get the cosecant of x is equal to 1. Most of you know that's going to be at pi over 2. But we'll go to the unit circle in a moment. Then we have or. We have the cosecant of x minus 2 equals 0. Add 2 to both sides. So the cosecant of x is equal to 2. So that's going to be at pi over 6 and 5 pi over 6. Again, let's just go to the unit circle and let me paste this in here. So I have my undefined right there of 0 and pi just so we don't forget. So the cosecant of x equals 1. Again, if you don't know this, you can just convert it over into a sine problem. So we know that the sine of x is equal to 1 over the cosecant of x. So basically, the cosecant of x is 1. So this would be 1 over 1. So where is the sine of x equal to 1? Well, basically, you're going to be at pi over 2. That's where your sine value is 1. So for that one, you can go ahead and say that basically your x is going to be equal to pi over 2. Now, for the other one, you have cosecant of x equals 2. Again, you can convert that over into a sine problem. So you can say that the sine of x is equal to 1 over the cosecant of x. And the cosecant of x is 2. So the sine of x would be equal to 1/2. And where does that happen? Well, that's going to happen right here at pi over 6, and then right here at 5 pi over 6. Let me get rid of this. And actually, we don't need this anymore. We can actually get rid of this information. We're just going to list everything out. So from solving our equation, we have, and I can put this in order. So let's go pi over 6, and then we have pi over 2, and then we have 5 pi over 6. So this right here comes from solving the related equation. And then this right here, this comes from us determining where things are undefined, again, in that interval. So basically, you're going to split your, you could say number line or unit circle, again, however you want to think about that, up into different intervals. So you're going to have one that's between 0 and pi over 6. So that's going to be this part right here. So you think about something in there. And then the next guy would be between pi over 6 and pi over 2. So between pi over 6 and pi over 2. And then you're going to do between pi over 2 and 5 pi over 6. And then you're going to do between 5 pi over 6 and pi. And then you're going to do between pi and 2 pi. So that's the big one right there. In the previous example, you saw me use the factored form, but I'm just going to tell you for something like this is going to be very slow if you do that. So you can use the factored form and determine whether it's going to be positive or negative and do it that way. If I get this type of problem, personally, I'm just going to use a calculator. And so I'm just going to go through and set up a little table. This is how I like to do it. Again, nothing will be included here. So between 0 and pi over 6, between pi over 6 and pi over 2, between pi over 2 and 5 pi over 6, between 5 pi over 6 and pi, and then between pi and 2 pi. Now, I've already picked something to make this a little bit faster that's in that interval. You can pick anything in that interval you want. Just don't pick the endpoints themselves. Just pick something between. So I pick pi over 12 here, and you punch that into your calculator. You'll get about 5.34. Again, I'm rounding this. It doesn't matter. You're just trying to figure out if it's positive or negative, and so this is positive. So this guy, if you plug in pi over 3, you're going to get something that's negative, so about negative 0.13. So this is negative here. If you plug in the 3 pi over 4, you're going to get something that's about negative 0.24. So again, this is negative. Then if you look at 11 pi over 12, which would have a pi over 12 reference angle, you're going to see that you get that 5.34 again, so approximately, and this is positive. And then lastly, I'm going to pick this 5 pi over 4. If you plug that in, you're going to get about 8.24. So this is positive. So we want to know where this guy is greater than 0. So anywhere where it's positive, we're good to go. We have to be very careful about our endpoints here. So we know that they're not going to satisfy the inequality in terms of where this guy is 0, but you also have to worry about where things are undefined. So that's where this gets really, really tricky. So let me come down here and let me guide you through this so that you don't make a mistake. So you could say between 0 and pi over 6, this guy is going to work because it's positive. Do I want to include pi over 6? No, because that would make it 0. So that doesn't work because it's a strict inequality. Does 0 work? No, because that's where it's undefined. So again, normally you're solving from 0 to 2 pi, and basically you would include 0 and exclude 2 pi. But here, 0 is where you're going to be undefined, so you have to exclude that there. That's why I never include 0 when I do these types of problems, and people always complain, but then you run into a situation like that, and you maybe have 0 included or something like that, you're not thinking about it, and then you get the wrong answer. So that's why I exclude everything all the time. So basically for this one, you would say that x is strictly greater than 0 and less than pi over 6, so neither would be included. Skip this one and skip this one. Now you have between 5 pi over 6 and pi. Would 5 pi over 6 work? No, because it makes it 0, and that wouldn't be included. It's a strict inequality. Would pi work? No, because in this case, it's undefined at pi. So it's undefined at 0, pi, 2 pi, all those things. So basically, this is x is greater than 5 pi over 6 and less than pi. So it can't be pi itself. So then over here, you're going to have a positive again, but once again, pi cannot be included and 2 pi cannot be included. So you're going to say that x is greater than pi, and it's going to be less than 2 pi. Now, let me put the keyword or in here. I'm going to try to squeeze that in everywhere. And then let me come down here and write this more neatly in case you're trying to put this down for your notes. So basically, x is greater than 0 and less than pi over 6. Then you're going to say or. So you're going to say that x is greater than 5 pi over 6 and less than pi. Now, this is strictly less than here, so you cannot combine those two like a lot of people want to do. Pi cannot be included because it's undefined at pi. So don't put that in there. Let me come down here a little bit and say or. So we'll have another one of those. We'll say x is greater than pi and less than 2 pi. So that's kind of a lot. But when you solve an inequality like this, sometimes it gets ridiculous. And if you solve one that's harder, sometimes it gets really ridiculous. If you want to do the interval notation, it's not that bad. So you're going to say from 0 to pi over 6. Again, both are excluded. And then the union with, you're going to do from 5 pi over 6 to pi. Again, that's both going to be excluded. And then the union with, looks like maybe I can't fit this. Let me drag it down here so maybe I can fit it. So the union with down here, you would go from pi to 2 pi. Again, both are excluded. All right, so once again, if you want to go to Desmos and see this visually, you can type in y equals cosecant squared x minus 3 cosecant of x plus 2, and you'll visually be able to see all the things that I was talking about. So basically, you're asking, where's this guy going to be greater than 0? So where are the y values greater than 0? Well, if you start here at 0, notice that this guy can't be 0. Because again, if you plugged in a 0 here, this is going to be undefined. So anything that's greater than 0 is going to work. And this is going to be going up to and then excluding this pi over 6. So when you hit pi over 6, this guy is actually going to be 0. So that would be excluded. So that's where you're getting that 0 to pi over 6 with both excluded part. And then the union with, if you look at it, here I'm going to be below 0, at 0, below 0, at 0. So once I get to 5 pi over 6, I know that's hard to read. That's another x-intercept that we found. And basically anything greater than that, going up to and excluding pi, we're going to be above 0 again. So we're going to say 5 pi over 6 going out to pi. But pi, of course, will not be included because you can see that this guy is going to have a vertical asymptote at x equals pi, right? These guys are going to approach an x value of pi, but it won't be able to actually touch it because it's undefined there. So then you have the union with, you would say anything that's larger than pi. So anything that's larger than pi, well, this is going to work again. You're going to be on this green graph right here, and this is going to work up into the point to where you get to anything less than 2 pi. So again, that's where you're undefined again. So from pi to 2 pi with both being excluded. So if you want to go to Desmos and check this out, you can visually see our solution. So anything between 0 and pi over 6. And then also you could say anything between 5 pi over 6 and pi. And then lastly, anything between pi and 2 pi. So all of those areas would work in the interval that we're solving over, which was from 0 to 2 pi with 0 being included and 2 pi being excluded.